Hello everyone. So in this video we will discuss the basics of signal. So even if you know the basic of signal, just watch the video completely. You can watch it on 2x or you can watch it skipping the video, but just watch it completely because there would be something that you don't know and that would be very important. Okay, so just watch it, just try to watch it completely. Okay, so what is a step signal? So in case of step signal, what actually happens is, what do we know? We know about DC, right? DC is like this. Let's just call DC 5 volts. So that means it is coming from minus infinity to infinity for complete part, right? But in case of step signal, it is only from 0 to infinity. Okay, so if it is written as AUT, that means you are getting A for t greater than equals to 0, not greater than equals to 0, I should write for t greater than 0, and 0 for t less than 0. Actually at t equals to 0, we can't really define it. Some people write a by 2 because this is how the graph will look like. For t less than 0, it is 0, right? For t less than 0, it is 0, and for t greater than 0, it is a, right? From 0 to it will go to a. So this is what a step function mean. Okay, what does a step function mean? You are coming from minus infinity, it is 0 0 0 0 0 0, suddenly you get a 0, all of a sudden you are getting a. Okay, so this is your time t equals to 0. So if it is written AUT, that means first you are having 0 value, then suddenly you are getting a value. If, like, let's just assume your VT is 5 UT. If your VT is 5 UT, that means previously there was no voltage in your circuit. Suddenly you are applying a 5 volt. Like your circuit was like okay, but suddenly you see 5 volt, right? So this is what it means. Okay, so t equals to 0, you are suddenly giving a input. Okay, let's see impulse signal. Okay, so we will see the deep meaning of impulse signal. First, let's just see what it is. So xt is a delta t. This is written. This is the impulse signal. So at t equals to 0, it gives you infinite magnitude, and at t equals to, for not less than 0, it is always 0. So it is defined only at t equals to 0. If it is written delta t, that means it is defined only at t equals to 0, and it will give you infinite magnitude. So what is this a? This a is the area. Okay, and the magnitude is infinity. So how do you show it? You show it like this. Okay, and you write a here. So this a represents the area. Okay, we will see the deep meaning. Okay, this a represents the area. So what is the unit of a? Unit of a will be, that will be unit of xt, okay, multiply by unit of t. Basically this a is written, we actually write it like this, a delta t. Okay, so if it is written a delta t, that a shows the area. And what is the area? Unit of xt into unit of t. Okay, let's just see the actual meaning of impulse signal now. So what is impulse signal? At t equals to 0, you will have infinite magnitude, like very large. The value of xt is very large at t equals to 0, but after or before t equals to 0, there is nothing. Okay, at t equals to 0, you are applying very large amount of voltage or very large amount of input, but before and after there is nothing. Okay, so this is what impulse signal is. And if this shows a value, that is not magnitude, that is the area. Okay, so what do we actually mean by that? Let's just see. So actual meaning of impulse signal. So let's just assume there is a circuit and you have to deliver 4 coulomb charge. There is a circuit and you have to deliver 4 coulomb charge in that. So you know that your q is integration of it into dt, or you know that like your it is dq by dt, right? Your it is qt by dt, right? So your q is integration of I to dt from minus infinity to infinity. So you have to give 4 coulomb charge, right? You have to give 4 coulomb charge. So what you can do, this is my time span of 1 second, right? This is 1 second. So for 1 second, for 1 second, I am giving 4 ampere current. 4 ampere current. So my Q will be 4 into 1. That means 4 coulomb. So basically this area is what? This area is 4, right? This area is 4. So that represents 4 coulomb. What is the unit? Like I shouldn't write 4 coulomb. I should write 4 ampere into second. Unit of IT is ampere, unit of time is second. So that means it is 4 coulomb. Okay. Now let's see what I can do. Now what I am doing, I am decreasing the time. Okay. Decreasing the time. So now I will give some amount of current for half second only. So for giving 4 coulomb charge, how much current I should give? Tell me. I have decreased the time span. I have decreased the time span. So how much current I should give? 8 ampere, right? I should give 8 ampere current, so that 8 into 1 by 2 equals to 4 coulomb charge. Decreased the time span. Decreased the time span. That means increased the value of xt. Now I am decreasing the time span more. Now what is the time span? Time span is only 1 by 4 second, right? Here the time span is only 1 by 4 second. Let me make it more clearer. So here the time span is only 1 by 4 second, right? So how much magnitude do you require now? Tell me, what should be the magnitude to give the same 4 coulomb charge? How much magnitude should be there? 16, right? 16 ampere should be there, because 16 into 1 by 4, that means 4 coulomb. So as I am decreasing the time span, I have to increase the magnitude. First my time span was 1 second, my magnitude was 4 ampere. To give the same amount of charge, in 1 second I am giving 4 ampere. In half second I am giving 8 ampere. In 1 by 4 second I am giving 16 ampere. Now what if I take my time equals to 0 in no time? 1 second 4 ampere, half second 8 ampere, 1 by 4 second 16 ampere, right? Time is 0. That means IT will go to infinity. Very less. IT will go to infinity, but area is the same, 4 coulomb. So if I have written IT equals to 4 delta T, IT equals to 4 delta T. So what does that mean? What will be the unit of this 4? 4 delta T, what will be the unit of this 4? This 4 is ampere into second. That means it is coulomb, right? That 4 is coulomb. That means you are giving 4 coulomb charge in no time. That means you are giving 4 coulomb charge in no time. Okay, here what was happening? You are giving 4 coulomb charge in 1 second, right? You are giving 4 coulomb charge in 1 second. Here what was happening? You are giving 4 coulomb charge in half second, and here you are giving same 4 coulomb charge in 1 by 4 second. So as you decrease the time span to give the same amount of charge, the magnitude of current is increasing. So in this case, you are giving 4 coulomb charge in no time, right? You are giving 4 coulomb charge in no time, but the magnitude of current will increase very largely. So this is what infinite current mean. If I am saying my IT is 10 delta T, that means I am giving 10 coulomb charge in no time. If I am writing my VT is 5 delta T, what does that mean? Just think about it. VT is 5 delta T. I have told you one thing, EMF is equals to d phi by dt, right? That means voltage is equals to d phi by dt. Phi is the flux, right? Phi is the flux. That means I am giving 5, what is the unit of flux? Actually, I also forgot, I need to check. Yeah, so actually unit is not our matter of concern here. So basically it is like I am giving 5 amount of flux in no time. If Vt is 5 delta T, that means I am giving 5 amount of flux in no time. Just as It is equals to dq by dt, that is 5 delta T, that means you are giving 5 coulomb charge in no time. Are you getting it? Are you getting it? Why charge only? Because it is ampere into second. Ampere into second will give you charge. In the similar way, if I am writing Vt equals to 5 delta T, that means it is volt into second. Volt into second will give you flux. That means I am giving 5 amount of flux in no time. Are you getting it? If I am writing, let's just assume I am writing something, let me think. Just assume I am writing something xt equals to 5 delta T. Xt has a unit of kg. It doesn't really seem fine, but yeah, any unit it has. Okay, so like what is this 5? This 5 will have a unit of xt into unit of t, right? 5 will have unit of xt into unit of t, right? So basically you are giving 5 amount of that value in no time. So here you are giving 4 coulomb charge in no time. Are you getting this point? I hope you have understood this point. Okay. So this is the actual meaning. Like the magnitude is infinity. Why the magnitude is infinity? Because you are giving it in no time. That's why the magnitude is infinity. Okay. If you are giving slowly, like in 1 by 4 second you were giving, so the magnitude was 16 ampere. If it was 1 by 8, the magnitude would have been 32. If it was 1 by 16, magnitude would have been 64. But if it is 0, the magnitude is infinity. So you are giving very large amount of current. Why so? Because you are giving 4 coulomb charge in no time. Like It is equals to dq by dt, right? So this dq is 4 coulomb. You are giving 4 coulomb charge in no time. Time is 0. Value will be infinite. 4 coulomb charge in no time. dt is 0. 4 coulomb charge in very less time. So the value will be infinity. So the value is infinity. But if it is written 4, that means it shows the area. And area means it is showing ampere into second. So this is the actual meaning. Are you getting it? Okay. So this was the most important part that I wanted to know you all. Okay. I wanted all of you to know. Okay. So let's just see our third signal, that is ramp signal. We will come back to this point again when we study the differentiation. Okay. So we will discuss it more. I will discuss it more. So first let's see ramp signal. What is ramp signal? Ramp signal is simply the straight line passing through an origin. Okay, with a slope. So if it is written ART, that means it is the straight line passing through the origin with a slope of A, but the difference is that it won't be there for t less than 0. It will always be there for t greater than 0. So for t less than 0, it is always 0. Okay, it is always 0. For t less than 0, it is always 0. Okay, and the slope is, this is the slope. So the slope is a. Okay, basically if art is written, that is at into ut. If there is some, if somewhere ut is written, that means they are eradicating the part before t less than 0. Let us assume written 5 ut. That means it is basically the multiplication of 5 and ut. So this value will be multiplied with 0. So this will be 0 only. After that, this value will be multiplied with ut. Ut is 1. So it will become 5 ut. So that means if somewhere ut is multiplied, that means the value before t equals to 0 is gone. So for value for t less than 0 is gone. Only for value t greater than 0 it is there. Okay. This is what it means. Okay. So let's just see the differentiation of a step signal. So if you differentiate a step signal, you will always get a what? Impulse signal. Why so? Why so? Because again I have written the example of the charge and the current. Okay. So what is happening here? So 0 0 0, okay, everything was 0. It is basically dq by dt. It is dqt by dt. Okay, so previously it was all 0. Suddenly at t equals to 0, from here to here if you go, you are suddenly having 5 coulomb charge, right? So at t equals to 0 minus to 0 plus. So from t equals to 0 minus to 0 plus, you are having 5 coulomb of charge, but the time is 0 only, right? From 0 minus to 0 plus, the time is 0 only, and the magnitude is infinity. If infinite magnitude is there, that means there will be impulse, right? If infinite magnitude is there, that means there will be an impulse, and this is the impulse. Okay, so this is the impulse, and we will write it as 5 delta t. This value shows the charge, shows the charge, shows the charge. Okay, this 5 shows the charge. Are you getting this point? Now differentiation of ramp signal will give you step signal. Okay, just like differentiation of step signal is giving you an impulse, differentiation of ramp signal will give you a step. Have you understood this point? From 0 to 5 we are going in no time, that means there will be an impulse of 5 delta t. Okay, I hope you have understood this point. Okay, and differentiation of ramp signal will give you step signal. Yeah, so this is the simple derivation. Okay, no, like very simple derivation. So this is my ramp signal ART. I can write it as AT into UT, right? Because what is the graph of T? The graph of T is like this. But if UT is written, that means this part will be gone. This part will be gone. Only this part will be left. This part will be gone to 0. So A into T into UT I have written. Okay. Now I will differentiate it. A is the constant. It will be outside. But now there are two signals. Okay. Never take this as one signal only. Like many times I have seen, like people write, what is the differentiation of this? They will forget this. Differentiation of this will be 1. So your final answer is UT. That is correct, but luckily the method is wrong. Okay, the final answer is correct, but luckily it is correct only. Okay, the method is wrong. Okay, why so? Because there are two time domain signals, T and UT. So if you differentiate both of them, A into, what is the, we are applying U into V rule. T as it is, differentiation of second. What is the differentiation of UT? Differentiation of UT is delta T plus second as it is UT. What is the differentiation of T? That is 1. So this is what you get. Now what is the value of T into delta T? Tell me. T into delta T. This is your T, right? And this is your delta T. Delta T only exists at T equals to 0, right? Delta T exists at T equals to 0 only, right? Delta T exists at T equals to 0 only. What is the value of this function at T equals to 0? It is 0. So T into delta T will always give you 0. Are you getting this point? T into delta t will always give you 0. Why so? Because at t equals to 0, delta t only exists at t equals to 0, and at t equals to 0, this function is 0. So t into delta t will always give you 0. Are you getting this point? Delta t exists at t equals to 0 only, and at t equals to 0, your function t is 0. So it will give you 0 value only. Okay. So finally your answer is AUT. So basically if you differentiate it, this is the graph and slope is A. If you differentiate it, you will get as final value as this step. Okay, 0 was there, differentiation of 0 is already 0. Differentiation of 0 is already 0. After that you will get a step. Okay, the value of that step would be A. So basically RT will be replaced with UT. So you can write this thing, d by dt RT is equals to UT. Okay, d by dt RT is equals to UT. A is constant, that is outside. Okay, so now basically if you go from impulse to ramp, if you integrate them, like ramp, differentiation of ramp is step, differentiation of step is impulse. So if you integrate impulse, you will get step. If you integrate step, you will get ramp. Are you getting this point? Integration from 0 to t delta t ut, sorry, delta t dt by ut, delta t dt will give me ut from 0 to t. Why I am writing, I can write minus infinity to t y 0 to t, and here you can also write from minus infinity to t ut dt will give me rt. Okay, so this is for integration. For differentiation we have already written. Okay, now we are generating a step signal. Okay, we will generate a step signal. How we will generate? Because we have always DC. What is DC? DC is this. We have 5 volt DC battery. That means it will always give you 5 volt. But now you want the circuit to give 5 volt at a particular time only. बैटरी मार्केट से खरीद के लाए वो हमेशा 5 वोल्ट देगी, बट एक पर्टिकुलर टाइम पे तुम्हें 5 वोल्ट चाहिए. यू नीड 5 वोल्ट एट ए पर्टिकुलर टाइम. सो हाउ विल यू गेट दैट? What you will do, you will turn on the switch at t equals to 0 only. You connected a battery, but you turns on the switch at t equals to 0 only. So what is happening here is that, like before t, this can be a ground, this can also be a ground, this should be given actually, this is a ground. Okay, and the network doesn't have any energy source. So what is happening? For t less than 0, what will happen to v naught? V naught t will be 0 volt, and for t greater than 0, what will happen? This will be shorted, so complete 5 volt will come across v naught t, right? Where v naught t is 5 volt. So this is what v naught t will be 5 ut. This is your tap signal only, right? So v naught t is 5 ut. From 0 to 5 ut goes. This is your v naught t. Okay, from 0 to 5 volt. Are you getting this point? Now this is one interesting problem. So tell me what will happen here. So for t less than 2 seconds, this is grounded and this is also grounded. For t less than 2 seconds, your v naught t will be 0, and for t greater than 2 seconds, your v naught t will be 5 volt, right? So basically how will your graph look like? How will your graph look like? This is 2 seconds, right? This is 2 seconds. So for t less than 2 seconds, v naught t is 0. For t less than 2 seconds, v naught t is 0. And for t greater than 2 seconds, it is 5 volt. it is 5 volt. Understood? For t less than 2 seconds, it is 0, and for t greater than 2 seconds, it is 5 volt. So how will you write it in terms of ut? Can you think of it? How will you write it in terms of ut? Try thinking of it. Pause the video and try thinking of it. Okay. So how will you write? If you have already studied signal system, it will be easy for you. But those who haven't studied the signal science system, I want them to write. It will be 5 ut minus 2. Got it? How did I write it? Look, it will start from t equals to 2 only, no? What will be the value at t equals to 1? V naught 1. It will be 5 u of minus 1. What is the value of u of minus 1? Ut is what? Ut is 1 for, sorry, yeah, ut is 1 for t greater than 0 and 0 for t less than 0. That means u of minus 1 will be 0. And this is what you expect, right? This is what you expect, right? What will be the value at t equals to 3? T equals to 3, v naught 3. That will be equals to 5 u1. That means 5 volt. And this is what you expect, right? U1 is 5 volt. So there is one thing, one common concept that you study in signal system. If you have already studied signal system, it would be easy for you. So whenever there is a right shift in the signal, my ut was from 0 to infinity. Whenever there is a right shift, you subtract it, t minus 2. If there was a left shift, you would have written t plus 2. Okay. So if there is right shift, that means u t minus t naught. And if there was a left shift, you could have done u t plus t naught. Okay. So just make the graph and then you will be able to realize. Okay. So just I can think of a question. Okay. One backup question. Write yt in terms of impulse signal. Impulse signal. Now what is your yt? Yt is something like this. Yt with t, and this is your yt. It is written 5. Okay. And this is t equals to 2 seconds. What is your yt? Tell me. What is your yt? This is just a backup question. Okay. Not a main question, just a backup question. Tell me, what is yt? It is 5 delta t minus 2. Because delta t is at t equals to 0. If there is a right shift, I would do t minus t naught. If there was a left shift, I would have done, okay, I can do one more thing. I can put a 4 here, t equals to minus 2. So tell me, it will be plus 4 delta t plus 2. Because there are two signal. One is at delta t is always at t equals to 0. But if there is a left shift, sorry, if there is a right shift, I would write 5t minus 2. If there is a left shift at this side, I would write 5t plus 2. Okay. So whenever there is a left shift, जब भी उल्टे जाते हैं हमेशा पॉजिटिव कर दो. उल्टा जाना पॉजिटिव नहीं है, बट जब भी उल्टे जाते हैं, नेगेटिव की तरफ जाते हैं तो पॉजिटिव कर दो, और पॉजिटिव की तरफ जाते हैं तो नेगेटिव कर दो. ठीक है, उल्टा करो अपने. ठीक है, इस केस में केवल. ओके. सो व्हेनेवर यू आर गोइंग टुवर्ड्स नेगेटिव, जस्ट ऐड देम अप. व्हेनेवर यू आर गोइंग टुवर्ड्स positive, just subtract them up. Okay. Okay then. Can you tell me what will be V naught T here? What will be V naught T? First, understand the switching position. So for t less than 0, tell me what is happening. For t less than 0, this will be open circuited, right? This will be open circuited, and this will be short circuited because at t equals to 0 it is opening. In the previous video we have studied this concept. It is written like this, that means it is opening at t equals to 0, that means it is closed before t equals to 0, right? That means it is closed before t equals to 0. Closed before t equals to 0. This battery remains there, that doesn't really matter. This battery is here only, but that doesn't really matter. क्या हो रहा है यार? This is grounded, this is grounded. So this 0 would come up here. So your V naught T is 0 volt. And for t greater than 0, what is happening? For t greater than 0, what is happening? This switch will be open, this switch will be closed. This will be your direct V naught T. So basically this node is 5 volt, this node will also be 5 volt. This node is 0, so this node is 5 volt, so V naught T will be 5 volt. So your final V naught T is 5 UT, right? Are you getting this point? So your final V naught T is 5 UT. So that's how you can generate a step signal. Okay, just a switch will make you generate a step signal. Okay, if the switch was open, like in the previous example, switch was open, so V naught T was 0. Just as it is closed, V naught T is 5 volt, like this. Open switch, V naught T was 0. Just as it is closed, V naught T is 5 volt. So this is how you will make it. Okay, so you will make the switch such as it turns on at t equals to 0 only. Okay, so in the example it will be used. Now this is a very important concept that is not taught anywhere. That's why I will put a great concentration here. Okay, so what is the frequency content in a step signal? Let's just take an example of sinusoid signal. This is my sinusoid signal. It's not looking like an uniform waveform. Okay, it doesn't look like a uniform waveform, but you can assume it, right? Let's just assume there is a sinusoid signal that has a frequency of omega. What is the frequency? Number of cycles per second. Let's just assume in t time, how many cycles are there? One cycle. For this waveform, how many cycles are there? One cycle. Now what I do, I increase the number of cycle in the same time only. How do I increase it? I increase it like this. Okay, it will be very tough to make it uniform. I'm not increasing the magnitude. Okay, okay, magnitude remains same, but frequency increases, right? This is my signal, my frequency is omega. Now if this is my signal, my frequency is greater than omega, because in the same time I am having more number of cycle, right? Let's just assume if this is t only, so in this period I am having how many cycles? 4. Okay, here I was having only one cycle, here I am having 4 cycles. Not 4 actually. Is it 4? 1, 2, 3, 3.5 it is. Okay, so basically your frequency is increasing, right? If you make it like this, so if this was the waveform, your frequency was omega. If this is the waveform, your frequency is increasing, right? If I increase it more like this, if I do like more like this, right? So frequency is increased more, right? Frequency is increased more. So frequency is greater than omega. Now what I do, like here we were having 0 only. Before this we were having 0 only. Okay, 0 only. Okay, let's just call this waveform as, if this was a sine omega t, let's just call this as a sine omega 1 t, and this one as a sine omega 2 t. So what is happening? Omega 2 is greater than omega 1 is greater than omega. Why so? Because in a second there are more number of cycle. If there are more number of cycle, that means frequency is higher. Now what I do, this is 0 0 0, like it is going up to its maximum value in some time, right? Like it, like this waveform was going to its maximum value in this much of time, right? This waveform was going to its maximum value in this much of time, right? This waveform is going to its maximum value in this much of time, right? It is taking some time. Now what I do, I make the maximum value in no time. Previously it was 0, and then I suddenly go to its maximum value. I reach its maximum value in no time. So tell me, what will be the frequency content? What will be the frequency content here? Infinity. Why so? Because there is a sudden jump. Because there is a sudden jump in the value. Sudden jump in the value. Okay, that means for a step signal, omega equals to infinity at t equals to 0. So here we have omega equals to infinity, but at DC omega equals to 0. This is the DC part, right? Basically, if it is reaching to its maximum value in this much of time, it has some frequency. In this much of time, it has lower frequency. In this much of time, it has lower frequency. But it is reaching in no time, that means it has infinite frequency. Are you getting it? More time, more frequency. Lesser time, sorry, more time, lesser frequency. If time is lesser, that means more frequency. If there is no time, that means infinite frequency is there. From 0 to 5, from 0 to some value, whatever we say a, from 0 to a, it is reaching in 0 second. That means infinite frequency. Are you getting this point? Because there is a sudden jump, that means in step function there is a sudden jump, that means in step function there is infinite frequency at t equals to 0. Okay, so this you need to keep in mind. So whenever there is a sudden jump, let's assume we are going from 0 to a, that means there is infinite frequency. If we are going from a to 0 in no time, you are a, suddenly it's 0, that means there is also infinite frequency. Are you getting this point? Very, very important point this is. Okay, so this is the basics of signal that is required in circuit analysis. Okay, like there are a lot more concept about signals that we will study in signals and system whenever we study that topic. So I will teach that topic as well very deeply. I will teach signal system very deeply as well, very intuitively I will teach. Okay, and here also you are getting the concept. I hope you are enjoying the videos. Okay, so a kind of different analysis we will see, and when we study the first order RC circuit, you will just see that it is very different. First order RC/RL. Okay, we won't use Laplace anywhere, we won't use equations, we will just see how the circuit behaves, and you will be able to solve those 5 minute or 10 minutes question within 30 seconds. That I can guarantee, and that too with full confidence. And no tricks are there. It is pure concept. No tricks, nothing. Pure conceptual thing we will talk about. Okay, so I hope you are enjoying the concept. We talked about the frequency content, how there is a sudden jump, that means there is infinite frequency. Then previously we talked about how we actually generate a step signal, because this will be used in the questions, like they will open the switch, they will close the switch, that means there is step signal or not. Because teachers or students don't really take notice like what is happening. They take DC and step same. Many of the students I have seen that they say that DC and step are same. No, in DC there is no infinite frequency. In step there is infinite frequency. There is a sudden jump, and there is what does the sudden jump mean? Sudden jump means in no time you are giving that much of value. and if you differentiate it, it will give you impulse. That means very large amount of some value. It can be very large amount of current. So whenever there is large amount of current, what happens in the circuit? So all these things we will study very, very deeply. Okay. So all I need is your support. We need your support. Just share the notes with everyone or share the videos with everyone. We will study very, very deeply, and we are taking very less time. You would see like there will be hours of lecture, but there is nothing fruitful. We are just taking the thing that is more important to you and delivering it in very less time, also very deeply. So I hope we are doing a very good job. So I expect I expect good response from your side. Okay, just share it with everyone. Just tell them that watch these videos, and it will be very helpful for all of you. And also we show the differentiation and integration of step function, impulse function, signals, impulse signals, step signals, and ramp signal, and we studied about them very deeply. What is an impulse? Impulse means you are giving some value in no time. Because of that, you are having an impulse, and this value shows the area. Area means the unit of this will be ampere into second. Okay, ampere into second is charge. Okay, it can be flux as well. Okay, it can be charge as well. Okay, so these things we studied. How do we, what is the actual meaning of impulse signal? All these things we studied. Okay, so in the next video, what we will study? We will study about differential equation. Okay, so if you already know differential equations, you can completely skip the next video. No, not completely, because there will be something that I will be teaching you that is different. Okay, so don't completely skip the video. Just watch it like quickly. Whatever whatever new you learn, you can note it down. Okay, so but just watch it completely, or you can read the notes as well. So just watch the next video completely, like quickly you can watch it. We will just see the mathematics of differential equations. Okay, so in the next video we will study that. Okay, then thank you. Hello everyone. So in this video we will start from the in-depth analysis of capacitor. Then we will go to zero order circuit. Then we will go to first order circuit. We will see all kind of RC circuits. Then we will go to inductor. Then we will see RL circuit. Then we will see RLC circuit. So that's how we are going to complete our transient. So first start with our capacitor. Okay. So this is the basics that we have already studied, but let's assume you don't know anything. So let's start from the very basics. So let's assume we have a capacitor with initial voltage of V0. A capacitor is there and initial voltage of V0 is there. So what is the initial charge it is having? Q equals to CV, right? But since it is having V0 voltage, so I will write CV0. And what is the initial voltage? That is V0. A capacitor with V0 voltage, that means it is having CV0 charge and initial voltage of V0. Now what I am doing, I am forcing some current into it. I am forcing I0 current into it. Just I brought a capacitor with some initial voltage already there. Okay. Now what I am doing, I am forcing some current into it. So what will happen? It will charge, right? So what will happen? It will charge. It will charge and gain voltage. How it will charge and gain voltage? That I will write. So your VCT would be, initial voltage is there, forget about it, just write it down. Initial voltage V0 is there. Now it will gain charge and gain voltage. So how it will gain voltage? 1 by C integration I dot dt. So what is I? I is I0. So I0 into dt. And since it is close at t equals to 0, so the current is coming from t equals to 0 only. So this is how it will gain charge. Are you understanding this point? Are you understanding this point? Initial voltage, if I am giving some current, that means it is gaining some voltage. If I am taking some current out of it, that means it will reduce its voltage. So we will see that in the further part of the lecture. So just I wanted to tell you one thing. If I am giving current to the capacitor, it will charge. That's it. And if I give voltage to the inductor, it will charge and gain some current. That we will see later on. But for capacitor, if I am giving current, it will get charged and gain some voltage. Okay. So if you are giving some current to the capacitor will charge and gain some voltage. Now there are some basic properties of capacitor. So capacitor is a charge storing element. Like it stores the charge. What is the charge? Q into CV0, right? So this is the initial charge, and because of the current, it will gain more charge, right? So it is a charge tolling element, and when there is a finite current, not impulse. What do you mean by impulse current? Impulse means infinite. I told you impulse means infinite, but the area is finite. So if there is a finite current flowing through the capacitor, so this is the property the capacitor follows. What is that property? Vc of t minus equals to Vc of t equals to Vc of t plus. What does it mean? That means that the capacitor doesn't change its voltage instantaneously. What does it mean? That let's assume I at t equals to 0 minus I have 5 voltage. So if there is finite current flowing through the capacitor will have the same voltage at t equals to 0 plus as well. Instantaneously the voltage will not change. Okay, only when there is a finite current. That's a very important point. When there is a finite current. Okay, so what do you mean by that? The capacitor doesn't change its voltage instantaneously instantaneously, but it can change its current. Okay, this property is valid only for the voltage, not for current, but it can change its current instantaneously. Okay, instantaneously. Okay, doesn't change its voltage instantaneously, but it can change its current instantaneously. Okay, so this is the property of capacitor that you need to know. Okay, in case of inductor, what will happen? It can't change current instantaneously, but it can change voltage instantaneously in case of inductor. But in case of capacitor, it can't change voltage instantaneously, but it can change current instantaneously. Okay, so like I hope you have understood the concept. Vc at 0 minus is if 5 volt, then Vc at 0 plus will also be 5 volt. But if the current at 0 minus is 1 ampere, that doesn't mean the current at 0 plus would be 1 ampere only. So it can be different. Okay, I can write it like example as well. Vc 0 minus is equals to 5 volt. That means Vc of 0 plus will also be 5 volt. And if IC 0 minus is 1 ampere, that doesn't mean IC 0 plus will also be 1 ampere. Okay. Now, in all the RC circuit, we will talk about two conditions, initial and final. Why so? Because we know this is the solution of first order equation. So in RC circuit, we will see what is first order equation, that we will see. But at most of the time we will encounter this equation only. So in this equation, to write down the final equation, we just need to know the final value and the initial value. That's it. So we will again and again talk about initial condition. Initial condition, that means y equals to 0, and final condition that we call steady state as well. Y equals to infinity, steady state. Okay. What do you mean by infinity? Infinity is steady state only, right? So we will talk about these two conditions. So what is the initial condition? So let's just assume our capacitor is having V0 voltage. Okay, let's assume our capacitor is initially having V0 voltage. So how you can replace the capacitor? So we can make it as a battery of V0 voltage. This is not generally for initial condition. From here to here, this is not for initial condition. From here to here, we will go to initial condition. Okay, so this is a general. So whenever you see a capacitor with some initial voltage, you can replace it like this. Okay, this is A, this is B. A is connected at higher potential, A is connected at higher potential, B is connected at lower, B is connected at lower. So you can take out the voltage and make the capacitor. Okay, and now this capacitor is having 0 voltage. We have already taken out the voltage. Now this capacitor is having 0 voltage. So at initial condition, what you can do? You can replace the capacitor with its initial voltage. That's it. Okay, you can replace the capacitor with its initial voltage. So this is the initial condition. At initial condition, what you do? You replace the capacitor with its initial voltage. Okay, and in most of the situations there will be no charge on capacitor. Okay, in most of the situation we will see that the capacitor is having zero initial voltage, no initial voltage is there. So what will you do? If no initial voltage, that means V naught equals to 0. If V naught equals to 0, that means short circuit, right? If voltage is 0, that means short circuit. If current is 0, that means open circuit. I have told you. Current 0 means, I can again write it. Current 0, that means open circuit. And voltage 0, that means short circuit. Okay. So the capacitor will be replaced with a short circuit. Okay. At initial condition. So now, what do you mean by steady state of capacitor? That means t equals to infinity. Okay, this is t equals to infinity. And what do you mean by initial condition? That is t equals to 0. So what do you mean by steady state? First, let me explain you the meaning of steady state. Steady state is like, this is the final thing. Nothing else will happen. Just I told you the example, right? The ball is traveling down, right? Ball is traveling down. So at one time ball will stop, right? So this is a time where ball is stopped. Let's assume the ball is stopping at t equals to 5 seconds. At t equals to 6 seconds, it will remain here only. At t equals to 1000 seconds, it will remain here only. So this is the steady state of the ball. The ball has stopped here. So this is what do we mean by steady state. Now in case of capacitor, what is happening? In case of capacitor, if we are forcing some current, it is gaining some voltage. If we are forcing some current, it is gaining some voltage in case of capacitor, right? This is what is happening in capacitor, right? So what do you see? At steady state, it won't gain more voltage. We are forcing some current, it is gaining some voltage. But at steady state, we want it to stabilize. Let's assume at some time the capacitor is having 5 volt and we call it the steady state. The capacitor is having 5 volt and you are saying that this is the steady state. So what do you mean by that? The capacitor will not gain more voltage. After that, it will always remain at 5 volt. Always it will be at 5 volt. So this is what we mean by steady state. Are you understanding this point? Steady state means the final condition. This is the final condition. Nothing else will happen. Okay. So this is what we mean by steady state. And now, if the capacitor at steady state, the capacitor will not have any further charge. That means it will not develop further voltage. So what do you mean by that? That means the capacitor is having no current, right? Well, in this case, we have made the circuit such that it will always have I naught current. But in some examples, we will see after some times the current flow will stop through the capacitor. If the current flow is stopping through the capacitor, that means it will not charge further, right? When there is current flow stops in the capacitor, it will not charge further. That means the capacitor has reached its maximum voltage. So this is the final voltage. So this is what we mean by steady state. Are you understanding this point? This is a capacitor and a current is flowing. So that means it is already complete. It is charging and charging. But at some point of time, this will develop some 5 volt. Okay, this is developed from 5 volt and there is no more current. Now, this 5 volt will remain there forever. 5 volt was there. Now there is no current. That means it is 5 volt only. If I am bringing some capacitor with some initial voltage of 3 volt, I am connecting no further circuit here. No resistance, no current source, no voltage source, nothing. So it will have its 3 volt, right? It will neither charge, it will neither discharge. So it will have some constant 3 volt. So this is what will happen. If there is no current through the capacitor, that means it will not charge further. And this is the steady state. So at steady state, the capacitor will have zero current. The capacitor will have zero current. That means IC equals to 0, right? If the current is 0, that means open circuit, right? So at steady state, at steady state capacitor is replaced with open circuit. Okay, so this is the capacitor at steady state. This will be replaced with the open circuit. Okay, no matter whatever the voltage it is having, it is not having any current. That means it will be replaced with the open circuit. Okay, this is just an analogy. The capacitor is there in the real circuit. The capacitor is there, but to solve the circuit on paper, we will replace it with the open circuit. Okay, so this is the analysis. And there is one more analogy. What is the analogy? So at steady state, Vc is the maximum value, right? I told you at steady state the capacitor has obtained its maximum value. So this is the max it can go. So what do you what is the equation of IC? That is C dVc by dt. If Vc is max, that means dCV by dt is equals to 0, right? Because let's assume this is some graph. If this is the maximum value, that means at this value the slope is 0. So dCV by dt is equals to 0. That shows your IC is equals to 0. That shows open circuit. So by this analogy also you can understand it. So this is a bit mathematical approach, but this was the intuitive approach. Intuitive, by what do you mean by intuitive? I will be using this word again and again, intuitive. So what do you mean by intuitive? You try to think about the circuit. You don't go mathematical. You try to think about the circuit. So if there is no current, so what is steady state? Steady state means the capacitor should not charge further. When the capacitor will not charge further? When there is no current. If there is no current, that means it will be open circuited. That's it. And this is the mathematical analysis. If Vc is the maximum value, then dVc by dt will be equals to 0. That means IC is equals to 0. So both the analysis you should know. Okay. So what is the summary? What do you do at t equals to 0 and what do you do at t equals to infinity? At t equals to 0, at t equals to infinity. So at t equals to 0, you will short circuit if there is no initial voltage. If there is no initial voltage, and in most of the cases there will be no initial voltage, and at steady state what you will do, you will make it open circuit. No matter how much voltage it is having, at steady state it will always be open circuited. That's it. So this is the summary. Okay. Now we will see a good question. So this is the curve for voltage across capacitor is given. This is the VC curve is given. You need to comment on the IC curve. So how will the IC curve look like? You need to comment on that. So what is IC? IC is C dVc by dt, right? Now comment on this from this curve. From the given curve, dVc by dt is positive or negative? Is it always positive? Is it always negative? Or sometimes it is positive, sometimes it is negative, or sometimes it is negative, sometimes it is positive? You tell me. Is it always positive? Yeah, it is always positive. See the slope here. Something is this. Sorry, this is not the slope. This is the slope. The slope should not cut the curve. At this point, this is the slope. At this point, this is the slope. At this point, this is the slope. Right? So these are the slopes. Right? And all the slopes are positive. What is the positive slope? This is a positive slope. Okay. And what is negative slope? This is the negative slope. Okay. And what is infinite slope? This is the infinite slope. I hope you know this concept. Negative slope, positive slope, and one straight line near to y-axis. Sorry, parallel to y-axis, one straight line, that means infinite slope. Okay. So this is negative, this is positive. Okay. So always the slope is positive. That means your current will always be positive. IC will always be positive. So this is first thing. The second thing what you can see, dVc by dt for the given curve is always decreasing, right? What is the slope here? Let's just assume this is the slope. What is the slope here? This is the slope. What is the slope here? This. If the slope is this, what do you mean? The slope is 0. With respect to x, y is not changing. This is x, this is y. With respect to x, y is not changing. So your with respect to x dx, y is not changing, so your change in y is 0, so that means your slope is 0, right? So if there is this straight line parallel to x axis, that means your slope is 0. So we started with some slope, we reduced and goes down to 0 slope. We started it like this, and slope goes down to 0. So what do you mean by that? dvc by dt is always decreasing. I forgot to remove these. dvc by dt is always decreasing and goes down to 0. And goes down to 0. That means IC always decreases and goes to 0. So I guess now you can draw the curve for IC, right? Can you draw the curve for IC now? IC versus T. So what is that? It goes down to 0. So finally it is going down to 0. So it is also positive. Look, there are two things. My final value is 0 and the value is always positive. So tell me one thing, from where it will start? Can it start from negative value? It can never start from negative value, because it always needs to be positive. And also the final value is 0. So from where it will start? It will start from some value, right? We don't know this value, but it will start from some positive value, right? It will start from some positive value and will go down to 0 and always remains positive. So this is always positive, right? And decreasing as well. I'm not talking about the slope here, okay? I'm not talking about the slope of IC. I'm not talking about DIC by dt. I'm not talking about that. I'm talking about IC. IC is always decreasing. Also, it is always positive. So, did you understand what I tried to deliver here? So, by VC curve, you can surely comment on IC if you know the relation. If your VC, if your slope is always positive for VC, if your slope is always positive, that means your current is always positive. But your slope is reducing, that means your current is reducing. Okay. So what do you understand by this point? That means even if your current is decreasing, now let's go from here to here. Okay. Even if your current is decreasing in the capacitor, still it is gaining voltage, but it is gaining voltage slowly. Just listen to my words very carefully. Even if the current is decreasing, your capacitor is gaining some voltage, but the speed of gaining the voltage is reduced. Are you understanding this point? So even if the current is, let's assume the current is flowing in the same direction. Now the current is positive, that means the current is flowing in the same direction. So whenever the current is flowing in the same direction, no matter the current is high or low, it will always gain some voltage. Okay, why is it so? Just see the equation. What is the equation? That is 1 by c integration I dot dt. If it is positive, no matter if it is 1 ampere or 2 ampere or 4 ampere, if it is positive, it will always gain some voltage. Like if it is 1 ampere, we will get T by C. If it is 2 ampere, we will get 2C by C. If it is 4 ampere, we will get 40 by C. So eventually it is giving it some voltage. So the value of current doesn't, if the value of current is decreasing, that doesn't mean it will lose voltage. If the value of current is negative, that means it will lose voltage. There is high difference between decreasing and negative. Okay, if it is decreasing, it will gain voltage only. Okay, but if it is negative, it will lose the voltage. Now we will see the example and you will understand everything. Okay, so that's why I said we will study it very, very deeply. We will, instead of mathematical analysis, instead of mathematical analysis, we will see the real approach, what is happening in the circuit. Okay, मैथ्स को थोड़ा कम और सर्किट को समझने का ज़्यादा ट्राई करेंगे. सो इट विल हेल्प यू इन लॉन्गर रन एंड यू विल नॉट हैव टू रिवाइज इट अगेन एंड अगेन. वंस यू स्टडी इट, it will be in your mind for your complete preparation. Okay, so that's why I am dealing it very slowly and very deeply. Okay, now you need to write the equation for v naught t, you can say v naught t. So what will be the equation? This is the first circuit given to you, so write it on your own first. Okay, first once I will tell you, then you can write it on your own. So initially it is having 3 volt and t goes to 0, the switch is closed. So this 5 ampere current is flowing in this direction. So 3 volt and the 5 ampere current is flowing in this direction. That means it will increase the voltage, right? So initially it is having 3 volt plus 1 by c integration 5 dot dt. So it will be 5t by c. That's it. Now talk about the second condition. Now the current is flowing in this direction. And what is V naught? Forget about the current. What is V naught initially? Forget about this current. The switch is closed at t equals to 0. Tell me the value of V naught at t equals to 0 minus. Okay. What is the value at t equals to 0 minus? It is minus 3 volt, right? Value of V naught is minus 3 volt. If this is 0, this will be minus 3 volt. Now the current is flowing in this direction. So it is charging the capacitor in this direction. That means your V naught value will increase now. First it was minus 3, now it is charging the capacitor in this direction. That means it will give voltage like this. This was flowing in this direction, that means it was giving voltage like this. And if it is giving voltage in this direction, plus upper side and minus lower side. Lower side is at ground, higher side is at V naught. So we will write plus here. Are you getting this point? Why did I write plus here? Because the current is charging the capacitor in this direction. That means it is trying to increase the voltage. From minus 3 to it will increase, right? Once it is minus 3, then it is increasing the voltage and V naught value will increase. Eventually V naught value will increase. So it will be minus 3 plus 5t by c. Now write for this on your own. What is happening now? What is the direction of current? The direction of current is this. What is V naught t? Initially it is 3 volt. Now it is giving voltage in this direction, in the negative direction. 3 volt, it is giving voltage in this direction. That means it will decrease the voltage, right? Because it is giving voltage in the negative direction. Minus 1 by c I dot dt. Okay, take your time, just see the circuit and you will understand everything. Now write down for this. Okay, so I will just modify it once because it will be the same question then. Now my V naught is changed. Now this is my V naught. Okay, now write it down for this V naught t. Mark it. What is V naught? V naught is not this plus minus V naught. No, V naught is minus plus V naught. Okay, sorry, plus minus V naught. Okay, this is your V naught. Initially it was plus minus V naught. Now minus plus V naught. Okay, so this is your V naught now. So tell me what will be your V naught t? The current is flowing in this direction. That means it is charging capacitor in this direction. Okay, also it is giving voltage like this. But in the previous case we wrote negative here, but now we will write positive. Why so? Why we are writing positive now? Because this is our V naught t only. Whatever the voltage developed across the capacitor from down to up, that is your V naught t only. If we were considering plus minus V naught dash, okay, so I am just taking two examples so it will be more clear to you. I am taking plus minus V naught dash. Okay, so tell me what is my V naught t? So my V naught t is, I am taking V naught t in this direction, negative positive. So positive at lower side and negative at upper side, and this is my V naught t only. So it will be 3 plus 5t by c. And what will be my V naught dash t? For V naught dash t, what is happening? V naught dash t is simply the negative of V naught. V naught dash t is simply the negative of V naught. So it will be minus 3 plus 5t by c. Are you understanding this point? 3 plus 5t by c, and it will be the negative of 3 plus 5t by c. And what, how you can understand it as well, that initially the V naught dash t is minus 3. Initially the V naught dash is minus 3, because if it is 0, this will be minus 3. Then this current is also charging the capacitor in the negative direction, in the from positive to negative, from lower to upper. So it will lose the voltage more. So from minus 3 it will go down to more negative value. Okay. So like if we need to draw the graph, I guess we can draw the graph. Okay. So if we are drawing the graph here for V naught t, so from where it is starting? It is starting from 3, right? It is starting from 3 and it will increase the voltage. Further, it will increase the voltage. Right? Now tell me, what is the value of this slope? Theta. What is the value of tan theta? Can anyone tell? It will be 5 by c. Y equals to mx plus c. Y V naught t is equals to mt plus c. What is m? 5 by c. So this is the slope. Right? This is the slope. Now let's make the graph for this. Okay, I think I should start from here. V naught t. Where are we starting from? Minus 3. Okay. So minus 3 we are starting, and with positive slope we will go. Right. So we are increasing the voltage. Right. From minus 3 to we are increasing the voltage. Now we can draw the graph here as well. So here what is happening? We are starting from 3 and then we are decreasing the voltage. So we will have a negative slope. Starting from 3 and decreasing the voltage. So we are having a negative slope. Okay. And here for V naught t we have already drawn for this value we can draw. For V naught dash t we can draw. For V naught to t, this will be the same graph, right? 3 plus 5t by c. So V naught dash we are drawing. Okay. For V naught dash we can draw. V naught dash. Okay. So it will start from minus 3 and will decay more, right? Now you guys may ask like what is the initial condition and steady state condition here? So my answer would be, this equation is not a first order differential equation, right? This is not a first order differential equation. For V naught t you are getting 3t minus 5t by c. This is not a first order differential equation. So you can't write V naught at t equals to infinity plus V naught at t equals to 0 minus infinity e to the power minus t upon 2. This is only for first order differential equation, and that will come only when the current is changing through the capacitor. Since here the current is constant, so it will always keep on rising. So short circuiting, open circuiting it, that doesn't come in picture, because the equation is not a first order differential equation. So it is always rising. Here also it is always decaying, always rising, always rising, always decaying, always decaying. Are you understanding this point? So that's why we don't consider that initial condition, final condition in this case. Okay, because this is not a first order equation. This is a linear equation, right? So let's start our main analysis. So first we will understand what is a zero order circuit. So if the circuit is having no storing element, what is the storing element? Inductors and capacitors. Capacitors and inductors. Okay. So if your circuit is having no storing element, that means it is zero order circuit. So all the circuits previously we saw, there were resistors and everything was resistor and resistor. So all these circuits were zero order because there was no capacitor, no inductor. So all these circuits were zero order circuit. So this is what we call order of the differential equation is zero. So what do you mean by differential equation? Here if I write the equation of I, what will be the equation of I? I will be 5 upon R1 plus R2. Zero order differential equation. That means it is not even a differential equation. This is a linear equation. Also we can say zero order differential equation. Okay, because there is no differentiation term here, right? No differentiation has been done here. Now secondly, if we want to write for V naught, what will be V naught? V naught will be 5 R2 upon R1 plus R2. Similar line I can write it for this as well. Zero order differential equation. So this is a zero order circuit. Okay. This is the zero order circuit. Now what is first order circuit? In first order circuit, we will have one effective storing element. Put emphasis on this point. Emphasize. Okay. Put high notice to this point. Effective. Okay. Effective story. Effective storing element. It doesn't mean that if your circuit is having two capacitors, it will be second order. No, it still can be first order. We will see this concept. So that's why I have written one effective storing element. Okay. So the order of differential equation will be 1. So now this is the circuit given R and C. There is 5-volt battery and we are closing the switch at t equals to 0. Now we need to write the equation of VR, VC and I. So first we will write down the differential equation and solve it. So by that you will understand why it is first order circuit. Okay. So first is by writing the differential equation. So first for what we are writing the differential equation. So first we are writing differential equation for current I. Okay. So we are writing differential equation for current I. So first let me make the circuit here. So the circuit for t greater than equals to 0. So circuit for t greater than equals to 0. The switch is closed now, right? The switch is closed. This is R, this is C, this is current. Now tell me what should I write here? Think about it and what should I write here? Shall I write 5 volt? Yeah, I can write 5 volt. But then I have to specify this is the circuit for t greater than 0. For just tell me one thing. Yeah, just tell me one thing. This RC circuit, this combination, will this combination see any voltage before t less than 0? This RC circuit is seeing any voltage before t less than 0? No, because this is open circuit. For t less than 0, this is the circuit. For t less than 0, this is the circuit, right? No voltage is there. The voltage is coming only after t greater than 0, right? So I can write here, I can write 5 ut, right? 5 ut, because the voltage is coming at t equals to 0 only, after t equals to 0. So here I can write 5 ut. Okay. So first, now this is your current I. Now we will write the differential equation. So how we will write the differential equation? 5 is equals to IR. We are writing KVL. Okay. KVL. So voltage 5 is equals to the voltage drop across this. What is the voltage drop across this? That is IR plus the voltage drop across this. Let's just assume this voltage drop is VC. So what is VC? VC is 1 by C integration I dot dt. So 1 by C integration capital I dot dt. Did you understand the case KVL? 5 volt is equals to IR plus 1 by C integration I dt. Differentiating it on both sides. Differentiation on both sides. if I differentiate this 5, this will be 0. R is a constant value. Current can be changing one, so di by dt. Plus, if I differentiate the integration, it will be I by c. Like you know what is differentiation and integration. Let's just assume some value is there. It will cancel each other, right? So it will give this dot. Differentiation and integration are cancelling each other. This will give just this dot. So 1 by c was constant. So differentiating it just giving me I. Okay, simple mathematics. Now we just need to solve this equation. I will write it down in a better way. Do I have another page? No, I don't have another page. So we can solve this equation right now, right? So I will be equals to CF, right? What is your CF? CF is here. Okay, I guess I can solve the equation. So we need to solve R di by dt plus I by C is equals to 0. Your FD is equals to RD plus 1 by C is equals to 0. So D is equals to minus 1 by RC. So your Y will be equals to C1 e to the power minus 1 by RC into T. Did you understand this? You just solve the equation, nothing else. Okay, I guess I need to add a page. Goes. Yeah, so this is your, not Y, this is your I, sorry. So your IT is C1 e to the power T by C1 e to the power minus T by RC. So this is your IT. I have told the method to solve the differential equation in the previous video. We solved the complete analysis of 30 minutes, how to solve the equations and what is the general solution and everything we have solved in the previous video only. So this is how we solve. Y is equals to only CF because your QX is 0 here. So only the complementary function will come, and this is the complementary function, that is C1 e to the power minus T by RC. Okay, C1 e to the power minus T by RC. Now tell me one thing. At t equals to 0, your IT will be C1, right? Now make the circuit at t equals to 0. At t equals to 0, what is happening in the circuit? This is 5 volt. This is R, right? Now what will happen to capacitor? Tell me. At t equals to 0, what will happen to capacitor? The capacitor will be shorted, right? Circuit at t equals to 0. The capacitor is shorted. Capacitor is shorted at initial condition. In the previous analysis, I told you, what did I tell you? That at initial condition, the capacitor acts as short circuit, and at steady state, it acts as open circuit. But we only need for initial condition. So initial condition, the capacitor is shorted. So tell me, what is the value of current? So I of 0, I think I should write I of 0. So I of 0 is 5 by R, and that is equals to C1. So from here, your final equation of IT is coming, that is 5 by R e to the power minus T by RC. So this is your final answer for IT. Did you understand this? IT is equals to 5 by R e to the power minus T by RC. Now you can draw the graph as well. Right? How you can draw the graph for IT? What do you see here? Okay, we will see multiple analysis. Okay, so what do you see here? Initially it is 5 by R, and then it goes down to 0. 5 by R2 at steady state. That means at t equals to infinity, it will be going down to 0. We have seen the graph of exponential, right? Okay. Now, what do you see? This equation you got. This is the equation you got. This is first order differential equation, right? Then what do you understand by this point? That means it is a first order circuit. It's a first order circuit. So for any equation, not just for current I, if I am going to write the equation for VR or for VC or current I, every equation will be first order only. Okay, why so? Because there is only one storing element. Because there is only one storing element, so the equation is going to be first order only. That's for sure. Okay, so now I will write the equation for VC. Now I will write the equation for VR. So there also you will see that the equation is being first order only. Okay, so only one differentiation will be there. Okay, so now I will write the equation for VR. First I will draw the circuit. Five UT. This is your R. This is mainly your VR, right? And this is the capacitor C. So everything here, everything was in current. Now I need to put everything in VR. So how will I do that? So let's start doing this. Okay, so 5 will be equals to VR plus 1 by C integration I dot dt. Let's just assume this is over I. So I think I should need to write capital I. Okay, okay, well and good. Now one thing you can see here is that VR is equals to I into R, right? This I is the function of t, so better I should write I of t dt, right? And this VR is also a function of t because we are writing the differential equation. So all of these will be a function of t. Here you show that the I is a function of t. So also eventually this VR will be also a function of t. So here I can write your VRT is equals to IT into R. Do you agree with me? VRT is equals to IT into R. So what will be your IT? IT will be VRT by R, right? From here you can write 5 is equals to VRT plus 1 by C integration IT is VRT by R into dt. Now what will you do? Differentiation. Differentiating. You will do differentiation. So 0 d by dt VRT plus VRT by RC. Right? So now you can solve this equation. Right? So shall I solve it or you will solve it on your own? I guess I should solve it. So here I will make the partition. We are just, what was our target? To make all the equation. So this is your first order equation, right? First order circuit. I will just write first order circuit. So our target was to make complete equation in VR only. So we just replace IT with VRT by R. So the complete equation is in VR only. So it is like D plus 1 by RC into VRT is equals to 0. So your D will be equals to minus 1 by RC. So your VRT is C1 e to the power minus 1 by RC into T. So this is the equation, right? So I will go and add a page. So your equation VRT is C1 e to the power minus 1 by RC into T. So tell me, at T equals to 0, VR0 is C1, right? Now what will I do? Circuit at T equals to 0, because I need to find the value of VR at T equals to 0. At circuit at t equals to 0, what do you know? At t equals to 0, the capacitor will be shorted. That's the one thing that I know. At t equals to 0, the capacitor will be shorted, and this is R, and this is your VR0, right? And this is grounded. So if this is 0, this will also be 0. This is 0, this will also be 0. And if this is 0, this will be 5, right? So your VR0 will be 5 volt. That is equals to C1. So what do you understand? What is your VRT? So your VRT is 5 e to the power minus t by RC. Just mathematical analysis, nothing else. When we go to the final value, final equation, then what did we do? We just put at t equals to 0, we just need to see the value of VR. So at t equals to 0, the value of VR is 5. So this is the equation that we are getting, that is 5 into e to the power minus t by RC. Okay, so this is the value of VR. And similarly, you need to find the value of VC. I hope you can do it on your own. Still, I will do it, but you should try doing it on your own before seeing the final solution. So this is just a simple differential equation that you need to solve. Just make the circuit and try doing it on your own. Okay. This is R, this is C, this is VC. Okay. So, and this is current 5. Why am I writing 5? This is IT. So what I can do, 5 is equals to IT into R plus VCT, because I need everything in VCT. Okay, so this is my equation. Now what do I know? VCT is 1 by C integration IT into DT, right? This is what I know. So what will be my IT? IT will be equals to C dVCT by dt, right? This is the equation, or I can put by equation 1, right? VCT is 1 by C integration IT into dt, so IT would be C dVC by dt. So by equation 1, 5 will be equals to RC dVCT by dt plus VCT. So this is our differential equation, first order differential equation, first order circuit. Now I can solve it, but here your VCT would be equals to CF plus PI. Like in the previous examples, we saw that your VRT is equals to only CF, right? And here also this is only equals to CF, because this was 0 here. Okay, this was 0 in this equation as well, this was 0, but here this is not the case, this is a finite value, so it will be CF plus PI. Okay, first we need to find the CF. I guess I need to add 2 more pages, I guess. First we will find CF. So first here we will find CF. So it will be DRC plus 1 is equals to 0. DRC plus 1 is equals to 0. So it will be D is equals to minus 1 by RC. So your CF is C1 e to the power minus 1 by RC into T. What about PI? PI will be VCT is equals to 5 upon DRC plus 1, right? Put D equals to 0. All these things I have already explained in the differential equation video. Okay, so it was just the previous video, I guess, so you can go there and watch the video. So from there only we are solving the equation. So if you just take your 15 minutes, you will be able to see how to solve the equation. So put D equals to 0, so your PI will be equals to 5 only. So your VCT is now equals to 5 plus C1 e to the power minus T by RC. Okay, and from here what do you see? At t equals to 0, what do you see? VC0 is 5 plus C1, right, at t equals to 0. Now let me make the circuit at t equals to 0. Circuit at t equals to 0. This is 5 volt. This is your R, and the capacitor acts as a short circuit. It acts as a short circuit, but it is there. So that means this is your VCT, right? This is R. Like the capacitor is there. This is the capacitor. This capacitor C is there, but it is acting as a short circuit. So what is your VCT at t equals to 0? It is 0 volt. That means 5 plus C1 is equals to 0. That means your C1 is equals to minus 5, right? So from here you can write your VCT is 5 minus 5 e to the power minus t by RC. This is your VCT, right? Did I make the graph for previous? No. Did I make the graph for this? No, I did not make the graph for this. So first let me make the graph for VRT. For VRT, what was happening? VRT. VRT, what was happening? It was starting from 5 and going down to 0. It was starting from 5 and going down to 0, right? Exponential response will be there, starting from 5 and going down to 0. Now tell me in this case for VCT what is happening? For VCT, tell me what is happening. It is starting from 0. At t equals to 0, what is the value? 5 minus 5, 0. It is starting from 0 and eventually it will go down to 5. At t equals to infinity, what is the value? 5. So from 0 to it goes down, goes to 5. So from 0 to it is going up to 5 volt. So this is what is happening in the circuit, right? Did you understand it? So what did we do? It was simple mathematical analysis. We won't do again and again. Just for one question, I have given the mathematical analysis. So this is the mathematical analysis. For current I, we wrote the equation and solved it and got the graph. For voltage VR, we got the graph. And for current VC, for voltage VC, we also got the graph. One thing we learned here is that if the circuit is first order, so for all the parameters, the equation will be first order only. If there is one effective storing element, that means the circuit is first order. That means the differential equation for all the parameters will be first order only. So we will write down this point. Okay, I will add a page. What did we understand here is that if there is only one effective storing element, then it means the circuit is first order circuit. Then what does it mean? The differential equation for all the parameters what are the parameters? Current or voltage. Current or voltage. So the differential equation for all the parameters will be of first order only, right? Only one storing element, that means the circuit is first order. That means the differential equation for all the parameter, whether it is current across the resistor or capacitor, whether it is voltage across the resistor or capacitor, all the equations will be first order only. All these facts will be used in the further analysis. So this was the first method where we wrote down the equation and go to the final answer. And here we understood that all the equation will be of first order only. So now we know the solution for first order equation. solution for first order equation, right? We know the solution for first order equation. What is the solution for first order equation? Yt is equals to y of infinity, this is a constant value, let it be, plus y of 0 minus y of infinity e to the power minus t upon tau, and where there tau is the time constant. We call this as time constant. So by using this equation, we will be able to write down the VCT, write down these equations that we got. No, this is the final equation. So in one line only we will be able to write down the final equation, right? In one line only. Here, like in one line only. Okay, these equation we wrote, no, in one line only we will be able to write, because we know if there is one storing element, that means it is first order circuit, right? If there is one storing element, that means it is a first order circuit. And what do you mean by that? If it is a first order circuit, the differential equation will be first order, and we already know the solution of first order differential equation. Okay, and in this part there is one interesting thing, is that this is the steady state part. Steady state, because t equals to infinity shows steady state only, right? So this is the steady state part, and this is the transient part, because it is decaying down to 0. I have explained in the first video only, first video of transient. What is transient? Transient is something that decays down to 0. So it is decaying down to 0. So this is the transient part. So this is the transient part. And this is the steady state part. Right? So this is the equation. Now this term we have introduced. What is time constant? So how to find the time constant of a first order circuit, that we will see now. Okay, so this video will be a bit longer, it can be for 90 minutes. So now we will see the time constant, how to find the time constant. Okay, so this is the general solution of first order equation that we already know. Y of t is equals to y of infinity plus y of 0 minus y of infinity e to the power minus t upon tau, where tau is the time constant. Now how to find the time constant? So what you will do? First thing, nullify the effect of all the independent source. Voltage source will be voltage source will be voltage source will be short circuited, and current source will be open circuited, right? So first nullify the effect of all the independent source, then find the effective storing element. That means if capacitor is there, find the effective capacitance and find the effective inductance. So effective, this is the important point, effective. Okay, then find the equivalent resistance across that effective capacitor, okay, or inductor. Okay, by seeing the method you won't be able to understand, we will take the example, you will be able to understand. So then we will find the effective equivalent resistance across that effective storing element, then we will write down the time constant. So time constant for first order RC circuit will be R equivalent into C effective, and for RL circuit it will be L effective upon R equivalent. Okay, sometimes people take mistake in that, sometimes people are mistaken in that they write R by L, but the actual answer is L by R. Okay, time constant is L by R. How will you remember it? How do you write tau? Tau you write like this, and how do you write L? So these two look similar, right? Tau and L look similar, kind of similar they look, right? Tau and L, they look similar, right? So both of them will be like together, it won't come, like tau will not come in the denominator. Okay, it will always be in numerator. Okay, and this is oh sorry, L equals to 2 by R I am writing, tau equals to L by R, tau equals to L by R. Okay, so that you need to remember. Okay, so this is the time constant. So how do we find? First, nullify the effect of independent source, that means voltage source will be shorted and current source will be open circuited. Then you need to find the effective storing element, then you need to find the equivalent resistance. That's it. Okay, so let's see the example. So what was our given circuit? We are referring to the same circuit. This was our given circuit, right? This is R, this is C. Okay, so we need to find time constant. So what we will do? First thing is that short circuit the voltage source. So if we short circuit the voltage source, this will be R, this will be C. This voltage source is shorted, so R and C will come in parallel like this. C and R. Right? So what do you see? What is C effective here? That is C. And what is R equivalent here? That is R. So what is your tau now? Tau is RC. That's it. Okay. So this is just one example. Okay, we can see more examples, but first I think I should we should be, just a second. First I think we should be solving this question that we were already solving before this one. Okay, in between I had to introduce this term time constant because in the second method it will be used. Okay, so this is the second method, method 2. What was the first method? First method was by solving the differential equation. Now this is the method 2. Okay, this is method second. So first we will be solving for IT. For time constant we will see more example. Okay, no worries, we will see more example for time constant, but for now just hold on to this point. Okay, then we will see more circuit, we will see more examples there. Okay, so now we are going to solve for current IT. Okay, so this will be the final answer because this is a first order circuit. First order circuit. So if it is a first order circuit, we already know the final answer. So this will be the final answer. Now you need to find the value of I of 0 and I of infinity. You already know the value of I of 0, that is 5 by R, because in the previous video we have seen it, but still we will see. Circuit at t equals to 0. So what will be the value of I of 0? This is 5 volt. This is R. This will be shorted. This is R. So your I of 0. So your I of 0 will be 5 by R. Now what will be the value at t equals to infinity? So circuit at t equals to infinity. What will be your circuit at t equals to infinity? Tell me. Here the capacitor is shorted, right? At t equals to infinity, what happens to the capacitor? The capacitor is open circuited, right? At t equals to infinity, the capacitor is, you can write 5 ut here as well. Okay, no worries. The capacitor is open circuited, right? So this is your I infinity. Here the capacitor is open circuited. So your I of infinity will be 0 ampere. Did you understand this point? At t equals to 0, capacitor is shorted, so your current is 5 by R. At t equals to infinity, capacitor is open circuited, so your current is 0. So from here, you can finally write down the value of IT. So your IT would be, infinity it is 0, so 0 plus, at t equals to 0 it is 5 by R minus 0 e to the power minus t upon tau. What is tau for this circuit? Tau is RC. What is the time constant of the circuit? That is RC. T by RC. So what is your IT? IT here is 5 by R e to the power minus T by RC. Did you understand this? Did you get it? Time constant we have already seen here, that is RC. So first we found the value at t equals to 0, that is 5 by R. Then we found the value at t equals to infinity, that is 0. So your IT would be, 0 plus 5 by R minus 0 e to the power minus T upon RC. So IT is 5 by R e to the power minus T by RC. Okay, a time constant is RC. Now for VRT we will solve. So for VRT, so what will be your VRT? VRT will also be VR at t equals to 0, sorry, VR at t equals to infinity, VR at t equals to infinity plus VR at t equals to 0 minus VR at t equals to infinity e to the power minus t upon tau. Here tau is t upon tau. Okay, so here tau is RC. Okay, now circuit at t equals to 0. Circuit at t equals to 0. So what is the circuit at t equals to 0? This is 5 ut, this is R, this is shorted, capacitor is shorted, and this is like this. So this is R, and this is your VR at t equals to 0. So VR at t equals to 0 is 5 volt. Okay, and what about t equals to infinity? Your circuit at t equals to infinity. Circuit at t equals to infinity. So what is the circuit at t equals to infinity? This is 5 ut, this is R, this is your VR infinity, right? And at t equals to infinity, it will be open circuited, right? Now tell me, what is the value of VR at t equals to infinity? What is the current? Current is 0 ampere, right? If the current is 0 ampere, that means the voltage drop across this resistance is 0. That means it is 0 volt. If the current is 0 ampere, that means the voltage across the resistor is 0. That means VR infinity is 0 voltage. So what will be your VRT? VRT will be, this is 0, this is 0, this is 0. So it will simply be 5 into e to the power minus t by RC, right? So this is your VRT. Whenever you see a first order circuit, what you need to do? You need to find the value at t equals to 0, you need to find the value at t equals to infinity. Just write down this equation, that's it. T equals to 0, t equals to infinity, time constant. These three things you need to know, and you can write down the equation, any equation. Okay, you can write down any equation if you just know these three things: t equals to 0, t equals to infinity, t equal and time constant. Okay, so this is what we see here. Okay, now solving for VCT. Okay, so what will be the solution for VCT? It will again be VC at t equals to infinity plus VC at t equals to 0 minus VC at t equals to infinity e to the power minus t upon tau, where tau is RC. Now we will make circuit at t equals to 0. So this is the circuit at t equals to 0. This is shorted. Okay, and this is your VC 0. So VC 0 is 0 volt. And what about t equals to infinity? Circuit at t equals to infinity. That means at t equals to infinity, the capacitor will be open circuited, right? At t equals to infinity, the capacitor will be open circuited, and this will be VC infinity. So tell me the value of VC infinity. Everyone should tell me the value of VC infinity. 0 volt? No, it is 5 volt. Why so? Because if this is 0, this will be 5, and there is no drop across this resistance. So all the 5 will come at VC infinity only. VC infinity will be 5 volt. Resistance is having no drop. So all the 5 volt will be coming to VC infinity only. So VC infinity is 5 volt. So your VCT would be 5 plus 0 minus 5 e to the power minus t by RC. Or you can write VCT will be equals to 5 into 5 will be common, and 1 minus e to the power minus t by RC. This will be the final voltage across capacitor. So this is how you solve the circuit. Okay, just t equals to 0, t equals to infinity, and you should have a good idea of network analysis, basics of network analysis. What is the value? This is 0 because this is shorted. If this is open, then all the voltage is coming here, but the current through the resistance is 0, so the voltage drop across the resistance is 0 volt, right? Here the voltage drop is 0 volt, but if this is 0, this is 5, this 5 will come here. 5 into 1 minus e to the power minus t by rc. Okay, I hope you have understood the concept. So these are the two methods. Now what we will do, we will understand the circuit. What is actually happening in the circuit, that we will understand. Okay, so this was the circuit given to us. 5 ut, I will 5 volt I am saying. This was the circuit given. This is R, this is C. Okay, and the switch is closed at t equals to 0. So what is happening at t equals to 0? The capacitor acts as short circuit. This is the current. That means this is 5 volt, this is R, this is the capacitor that is acting as a short circuit. So this is R. So what is the current flowing? This is acting as a short circuit, right? Shorted. Just listen to me carefully, okay? What is the current flowing now? 5 by R. Now the capacitor is acting as a short circuit, but it is actually there, right? This 5 by R current is flowing through the capacitor. This capacitor is acting as a short circuit, so 5 by R current is flowing. So this 5 by R, and this is your VC, 5 by R, this 5 by R current flows through the capacitor. Okay, this analysis is very, very important. No one teaches this analysis, but if you just understand this, you will be able to solve any circuit. Okay, this 5 by R current flows through the capacitor. Now what will happen? If current is flowing, that means this charges the capacitor, right? This charges the capacitor. That means capacitor start developing the voltage. Are you understanding this point? At t equals to 0, the capacitor is acting as a short circuit. That means 5 by R current is flowing through the capacitor. So the current at t equals to 0 was, 5 by R, that is charging the capacitor. That is charging the cap. Okay, sometimes I will call cap as capacitor. Okay, this is charging the cap. Okay, now what is happening at t equals to, now let's assume after some time the capacitor, the capacitor is charged to 0.1 volt. Okay, now this 5 by R current, because of 5 by R current, because of the current. Okay, now what happened? The capacitor is charged to 0.1 volt. Now this is your 5 volt here, this is your resistance R. Now this capacitor is charged to, 0.1 volt now. After some time, I don't know what is the time. Okay, I don't know what is the time t. At some time t, this is the condition, 5 volt and 0.1. Now what is the current? the current at time t1, at some time t1, the current is 4.9 by R. This current also charges the capacitor, in the same direction, in the same direction. Now this point will come. Although the current has reduced, but the direction is the same, so still it will charge the capacitor. I focused on this point very deeply, right? Even if the current is getting reduced, it still has the same direction. That means it will still charge the capacitor. So, although the current has reduced, but still it is flowing in the same direction that charges the capacitor, with more voltage. Okay, now let's assume after some more time, after some more time, the capacitor is charged to 2 volt. Okay, the capacitor is charged to 2 volt. After some time, the capacitor is charged to 2 volt. So at some time t2, this is the condition. Wait. So at some time t2, this is your 5 ut, this is your resistance R. Now the capacitor is charged to 2 volt. This is R, this is C. Now it is charged to 2 volt. So now what is the current flowing? I of T2. What is the current? That is 3 by R ampere. Right? But still it charges the capacitor. Now what do you see here? I at 0 was 5 by R. I at T1 was 4.9 by R. I at T2 was 3 by R. Vc at 0 was 0 volt. Vc at T1 was 0.1 volt and Vc at T2 was 2 volt. What do you see here? Slowly the current is reducing and the voltage across the current is reducing and the voltage across the capacitor is increasing. At some time t3, your Vc T3 will be nearly equals to 5 volt. So at that time, what will be the current? Tell me. ICT3. What will be the value of ICT3? If your VCT3 is 5 volt, this is 5, this is 5, that means there is no current. So ICT3 will be 0 ampere and this is what we will call steady state. Did you understand this point or not? Let me explain it once again. Okay. This is, I am writing too much of theory because I need you to understand what is happening in the circuit. Initially the voltage is 0, that means 5 by R current is charging the capacitor. Now what happens, after some time the capacitor is developing some voltage. Now if it is developing some voltage, that means some less current will flow, but the current is in the same direction, that means it will further charge the capacitor. Okay, so 4.9 by R current is now charging the capacitor. Now after some time it will develop 0.2 volt, so 4.8 by R will charge. After some time it will develop 0.3 volt, so 4.7 by R will charge. Now let's assume it is developing some 2 volt. Okay, now if it is developing 2 volt, that means 3 by R current is charging. So slowly what do you see, 5 by R, 4.9 by R, 4.8 by R, 4.7 by R, 3 by R, slowly the current is getting reduced and the voltage across the capacitor is increasing. 0, 0.1, 0.2, 0.3, 2 volt. So slowly it will keep on increasing and it will increase till 5 volt. And when it reaches the 5 volt, here we have 5 volt, here we have 5 volt, and the current in the circuit is 0 ampere. So that is the steady state. So what is actually happening in the circuit, that you understand here. Okay. And one more thing I will add here, that is also very interesting thing. This is one point and one more point I will add. I hope I am able to add the page. Okay. So what do you see here? Here we also, I should write also here we see that the current is continuously decreasing, right? So what do you mean by that? Here we see that the current is continuously decreasing. That means more current means more voltage. That means the speed of charging is proportional to the amount of current. Right? If current is more, it will develop more voltage because Vc is 1 by C integration I dot dt. If current is more, it will develop more voltage. Right? If current is more, it will develop more voltage. So speed of charging is proportional to the amount of current. Since the current is continuously decreasing, since current continuously decreases, speed of charging decreases. That means capacitor will develop voltage slowly. Yeah, it will develop the voltage. Okay, it will develop the voltage, but it will develop the voltage slowly. Okay, so this is what you mean by the amount of current. If the current is getting decreased, that doesn't mean it will lose the voltage. Okay, if the current is getting decreased, that doesn't mean it is losing the voltage, but it is increasing the voltage slowly. It is increasing the voltage slowly. So with time dVct by dt is reducing. Are you able to understand this point? The current is reducing. That means it is slowly developing the voltage. The current is in the same direction. That means the voltage will increase, but not like this, not linearly. It will not increase linearly. Okay, it will decrease, it will increase slowly. It will not increase linearly because the current is not constant. The current is slowly getting decreased. That means the voltage is slowly getting, slowly it is getting to the final value. If it was constant, so it would have increased like this linearly. Here we saw, if the current was constant, it was increasing linearly like this. But now the current is not constant, so it is increasing like this. Are you able to understand my point? And it increases to 5 volt. And also what did we see? The current is getting reduced again and with time. That means the current is reduced with time. So we started from 5 by R and it reduces down to 0. So this is the complete full analysis of a one RC circuit. How do you actually see the circuit? First we saw the differential equation, then we saw the time constant, then we saw the general solution of differential equation, then we saw the real analysis, what is happening in the RC circuit. So I hope you have understood what is actually happening in the RC circuit. Shorted 5 by R current. This 5 by R current will charge the capacitor. After some time, the voltage developed is 0.01. Let's assume 0.01. Now the current is reduced. So the current is continuously reducing. The current is not constant. The current is continuously. Let's assume you see the current at this time, that is 5 by R. The next moment it will be 4.9 by R. The next moment it will be 4.78 by R. The next moment it will be 4.68 by R. The next moment it will be 4.5 by R. So the current is continuously decreasing like this. Now since the current is flowing in the same direction, the capacitor is developing the voltage. The current is flowing in this same direction. So the capacitor is developing the voltage, but since the current is reducing, it is developing the voltage slowly. If the current was the same, it would have developed the voltage like this. But since the current is reducing, it is developing the voltage like this and goes to the steady state value. So this is the complete analysis of RC circuit. I hope you have understood the concept very clearly, and I hope you will always remember this analysis. So whenever you see any RC circuit, don't just think T equals to 0, T equals to infinity 2. No, that's good for solving the problem, but you won't be able to remember it for a longer time. If you think about the circuit, you will be able to remember it for a longer time, and you will be good enough with the network analysis, with the uh, analog electronics, and even if you go in M.tech, it will be very, very useful for you. And even in the PSUs, if they ask you questions from network analysis, they will expect this kind of analysis from you. And even in the interviews of MNCs or any other company like TI, NXP, and all those semiconductor company, they also ask the question, and everyone solves T equals to 0, T equals to infinity, and this is what they don't like. They like the real deep analysis, and this is the real deep analysis. Okay, so I hope you have understood the concept. Now in the next video, we will see many more circuit and we will see the complete analysis of those as well. Okay, so let's meet in the next video. If you like the video, please do share with everyone. Okay, thank you. Hello everyone. So we are watching the examples of first order RC circuits. So we have already seen first circuit and we saw that very deeply, very intuitively. Okay, we saw all the methods from writing equations to differential equation to intuitive method. Okay, everything we have seen. Now we will see the second circuit. Okay, so in this circuit there are two switches. Let me call it first one as S1. I think I should use different color of pen. Let's call this one as S1 and this one as S2. So here it is not written in the theory, but I have told you what do S1 mean. S1 is closed before, or I should write S4 t less than 0, and S1 is opened for t greater than 0, and same goes with S2. S2 is closed for t greater than 0, and S2 is opened for t less than 0. So let's make the circuit at t less than 0. So circuit for t less than 0. What do you mean for t less than 0? That means minus infinity to 0, right? So S1 is closed, right? So S1 is closed. This is a 5-volt battery. This is resistance R. S1 is closed, right? And S2 is open. S2 is open. Right? This is open. and this is C, and this is R. Now the switch is closed for a long time, right? Switch S1 is closed for a long time. Why long time? Minus infinity to 0. What is the time? Minus infinity to 0. Infinite time, right? The switch S1 is closed for long time. For long time. And since this switch is open, this R becomes irrelevant, right? This R becomes irrelevant because this is open-ended. Let's assume some current is flowing here. Some current I is flowing here. The same current will be flowing through the capacitor, right? No current will go into this R because this will become open-ended. So this becomes irrelevant. Okay. So the switch is closed. Switch S1 is closed for a long time and it is open. So now what will happen? Now this 5 volt will charge the capacitor. 5 volt will charge the capacitor. Capacitor will get charged to 5 volt, right? This is simply this circuit only. The switch S1 is closed for a long time. Now it will get charged depending on the value of RC. But since we have infinite time, so surely it will be charged for 5 volt. Let's assume RC value is 2 seconds. So tell me how much time it will take it to charge for 5 volt. RC tau value is 2 seconds. So how much time it will take? 5 tau, right? In the very beginning, I told you like 5 tau is the settling time, right? So how much time it would take? 10 seconds. Okay. Now we don't know the value of RC. But whatever the value is, it can't be greater than infinite, right? It can't be greater than infinite, right? Infinite is very, very large. So it can't be greater than infinite. So switch is closed for a very long time. So this capacitor will fully get charged. The capacitor will fully get charged to 5 volt. Charge to 5 volt. So now our capacitor is having 5 volt. Now what we are doing? We are opening up the switch and closing this switch. So now if I say your VC at t equals to 0 minus will be 5 volt, right? VC at t equals to 0 minus will be 5 volt. Do you agree? We are starting from minus infinity and we are going towards 0. Right? So in meantime, somewhere here, it would have been charged to 5 volt, right? VC would have been charged to 5 volt. Now it will remain till 5 volt only. It can't get higher than 5, right? Because only 5 volt is there. So steady state value of capacitor will be 5 volt only. It can't get higher than 5 volt. So at some time it gets 5 volt and remains there, right? So this is the steady state. Steady state is 5 volt. Okay. So VC 0 minus is 5 volt, or what we can draw here is that we can draw something like this. Vc with respect to time t, we are starting from minus infinity, right? So somewhere from here we are starting and it goes till 5 volt. It can be anywhere, we don't know from where it is starting. So it goes till 5 volt and remain there. So from 0 volt to it will charge exponentially till 5 volt and it will remain there. Now circuit for t greater than 0. Now what is happening? This becomes open circuit, right? And now our capacitor is charged to 5 volt. Our capacitor is charged to 5 volt and this switch is closed now. This is R, right? This switch is closed now and this is R. So this is the condition now, right? This is 5 volt. This is R, this is C, and this is open now. So this becomes irrelevant. This side is open circuit. So open circuit means irrelevant. So you can reduce the circuit something like this. You have a capacitor, you have a resistance. The capacitor is having initial 5 volt. That's it. This is the circuit. Okay. Now you can solve the circuit, right? What you do? Vc at t equals to 0 minus was 5 volt. So tell me, Vc at t equals to 0 plus will be 5 volt only. Why so? Because of the property of capacitor. Capacitor, right? Vc0 minus equals to Vc0 plus is equals to Vc0. This is the property of capacitor, but this property is valid only when there is finite current through the capacitor. So before writing this thing, okay, always see the current that is flowing through the capacitor. So tell me, what is the current flowing through the capacitor at, this is the current I we are talking about. Okay, so tell me what is the current at t equals to 0. Okay, this is one thing. Also tell me what is the current at t equals to 0. 0 plus, I can say. What is the current at t equals to 0 plus? Tell me what is the value of I. Look, this is 5 volt here at capacitor. The same 5 volt will be coming towards this side, right? The same 5 volt will be coming towards this side, and the current will be flowing in this manner. If a resistance is having 5 volt across it, what is the current flowing through the resistance? That is 5 by R, and this is finite. So if this is finite, then only we can write this. Are you getting my point? Like those who have studied this chapter before, they would have always written Vc equals to 0, Vc0 minus equals to Vc0 plus. They would have always written this. But that's only true when there is a finite current through the capacitor. Now the same current that is flowing through the resistance, the same current is flowing through the capacitor, right? The current flowing out of the capacitor. The capacitor and into the resistor. Right? The current flowing out of the capacitor and into the resistor. This 5 volt is there, 5 volt coming towards the resistor. That means 5 by R current is flowing. Are you getting this point? Right. So then only you can write Vc0 minus equals to Vc0 plus equals to 5 volt. Okay. So now your voltage is 5 volt. Now some current is flowing towards. Now some current is flowing in the resistor. At steady state, what will happen? Okay. At steady state. At steady state, what happens? The capacitor becomes open circuited, right? There is no current flowing through the capacitor. That's happened. At steady state, no current flow through the capacitor, right? At steady state, no current flow through the capacitor. That means this is the capacitor you are having. This is the resistor. You can make it open circuit as well. CR. The current flowing through the capacitor is 0 ampere at steady state. At steady state, the current flowing through the capacitor is 0 ampere, and this is your Vc. So what is your I? I at steady state, 0 ampere. What is your Vc at steady state? Tell me. Vc is equals to the voltage across the resistor. If voltage across the resistor is what? 0 volt. Right? Did you understand this point? Vc is what? Vc is equals to the voltage. Vc is equals to VR, right? Vc is equals to VR, right? The voltage across the capacitor is equals to the voltage across the resistor. So 0 ampere current is flowing through the resistor. That means 0 voltage is there, right? So in conclusion, what do you write? Simply, what do you see? I0 plus or I0 you can write. I0 you can write, or I0 plus you can write. So I0 plus was 5 by R, and I infinity was 0 ampere. So now can you write the equation of I of t? It would be 5 by R e to the power minus t upon 2. Now tell me the value of time constant. We can find the value of time constant here only. time constant. Right? So how do we find the time constant? We are finding the time constant for t greater than 0. Right? For t greater than 0. We are finding the time constant for t greater than 0. How does the circuit look like for t greater than 0? This is how the circuit look like. Right? What is C effective? That is C. What is R equivalent? That is R only. So what is time constant? That is RC. Okay, and there is one mistake in this final expression. Can anyone mark it out? What is the mistake? 5 by r e to the power minus t upon 2. The mistake is that we will write ut here because we are writing the equation. We are writing the equation for t greater than 0. Equation for t greater than 0. Are you getting this point? Ut means simply t greater than 0. What is ut? Ut is this. We have already seen all these things in basics. This is ut. So we are writing the equation for t greater than 0. That's why we have to apply ut here. Okay, so this is the equation of current. And you can draw the graph. It will start from 5 by r and it will go down to 0. So we will draw the graph as well. So graph of it we will draw. This is the graph of it we are drawing. It is starting from 5 by r, then it goes down to 0. Now tell me what is happening. What is the value of it for t less than 0? Actually, we should have written here. Circuit for t less than 0. What was it? This was I. Right? This was I. But there was no current flowing through these resistors. There was no current flowing through this resistor. Why so? Because this was open circuit. So, for t less than 0, I is 0 ampere. Only the current flowing was here. Only the current was flowing here. And they didn't ask the value of this current. Okay, so no worries about this current. They only ask the value for this current. So there is no current flowing through this loop because this loop is open circuited. This loop is open circuited, so no current is flowing here. So the current is 0 ampere. So first the current is 0 ampere. Then what happens? 5 volt comes and the current suddenly rises to 5 by r and then goes down to 0. So this is what is happening. Okay. Starts from 0. Okay. Then suddenly rises to 5 by r and then goes down to 0. Okay, now let's talk about VCT. Okay, let's talk about VCT. So VC at t equals to 0 plus. What was the value of VC at t equals to 0 plus? Here we wrote, right? 5 volt. And what was the value of VC at t equals to infinity? 0 volt. Here we wrote, right? 0 volt. This is 0 volt. So what is the complete graph of VCT? Okay, before making the graph, we will write down the equation. So your VCT would be, it will also be 5 upon e to the power minus t by tau value is RC. Okay, and also we will use UT. Okay, so beforehand it was like this. It came from some value from somewhere. It came from 0 to 5 volt. Okay, then from 5 volt to it went down to 0 volt. Right, so this is VCT and this is 5 volt. Okay, and some people ask what is the time constant here. Time constant is RC. What is the time constant here? Time constant is RC. If in these problems that we have already seen, where are the problems? Yeah, if in these problems they ask you what is the time constant, tell me what is the time constant for these problems. I guess I have already told this thing. What is the time constant? Look, open circuit the current source. Okay, open circuit the current source. What is C effective? C only. What is R effective? From here, if you see resistance, what is the resistance? I just open circuited the current source. That's what I am supposed to do. Open circuit the current source for finding the time constant, right? For finding the time constant, I will open circuit the current source. Now this is my capacitor C. So what is my C effective? C effective is C. Now what is my R equivalent? Tell me. 0 or infinity. You have two options: 0 or infinity. Infinity. Why so? Because what does open circuit mean? Open circuit means infinite resistance. Short circuit means zero resistance. Open circuit means infinite resistance. So what is the time constant? C into infinity. Infinity. So what is the time constant for all these circuits? It is infinity. And also by concept you can also understand. What do you mean by time constant? The speed of settling down, right? The speed of transient being destroyed. But it is not even settling down. It is always increasing. So when it will settle down? At infinity time. It is always increasing. So the time constant is infinity. Okay. Circuit was having infinity time constant. Okay. Now let's understand the circuit, what is happening. So I guess all of you must have understood what is happening for t less than 0. For t less than 0, what is happening? The capacitor is being charged to 5 volt, right? From minus infinity to 0, the capacitor is being charged to 5 volt, right? Now for t greater than 0, this switch is closed, and this is R and this is C, this 5 volt. Now what happens? This same 5 volt comes across the resistor. This same 5 volt comes across the resistor, right? So what happens? This same 5 volt comes across the resistor. So what happens? I is equals to 5 by R. Now just see the capacitor. What is happening? What is happening? This is the capacitor. Okay. This is charged to 5 volt, right? And this is capacitor C. 5 by R current is flowing out of the capacitor. This is at t equals to 0 plus. At t equals to 0 plus, what is happening? 5 volt, 5 by R current is flowing out of the capacitor. What is happening? 5 by R current is flowing out of the capacitor. Out of the capacitor. So if the current is flowing out of the capacitor, what happens? Capacitor discharges. Capacitor discharges. 5 by R current is flowing out of the capacitor, that means the capacitor discharges. Let's assume at t equals to t1, capacitor is discharged to 4.9 volt. Okay. So what happens at t equals to t1? At t equals to t1, what happens? The capacitor is discharged to 4.9 volt. This is your capacitor that is discharged to 4.9 volt, right? And this is the resistance R, right? So now what is the current? Current at t equals to t1, that is 4.9 by R. What is the other way of showing it? This is a capacitor with 4.9 volt, with 4.9 volt across it, and again 4.9 by R current is flowing out of the capacitor. Now 4.9 R current flows out of the capacitor and discharges it. Now tell me, till what voltage it will continue to discharge? Till what voltage the capacitor will continue to discharge? 5, 4.9, 4.8, 4 volt, 3 volt, 2 volt, 1 volt, 0.5 volt. Again 0.5 R, 0.5 by R current is flowing. If capacitor is having 0.3 voltage, that means 0.3 by R current is flowing. If capacitor is having 0.1 voltage, that means 0.1 by R current is flowing. That means this shows that the capacitor will keep on discharging until the current flowing out of it becomes zero. And when does it become zero? When does it become zero? That means the capacitor will have zero voltage. Okay. Also, what you can see, I won't write it more. Okay. So what you can see, slowly the current is getting reduced, right? The current was 5 by R, 4.9 by R, 4.7 by R, 4.6 by R. That means the speed of discharging it is reducing. Did you understand my point? Initially, the current was 5 by R, 4.9 by R, 4.8 by R, 4.7 by R, 3 by R, 2 by R, 1 by R. That means the current is reducing. That means the speed of discharging is reducing. That means the voltage will go down, but it will go down slowly. So that's why we are having a exponential graph. The voltage is going down, but it is going down slowly. It's not going down like this. Like it's going down slowly like this. So that means the slope is getting reduced slowly. Okay, and eventually it goes down to zero. The slope goes down to zero. Also, the current is getting reduced, so the current also goes down like this. Okay, 5 by R, 4.9 by R, 4.8 by R. That means the speed of discharging is reducing. That means the curve goes down slowly, not like this, not linearly, but slowly. So why the graph is exponential? If someone asks you why the graph is exponential, why not linear? So you can say that the current is changing. Okay, the current is changing with time. If the current was constant with time, we would have a linear graph like this, right? If current was constant with time, but current is not constant with time, the current is reducing slowly. So that's why we are having a exponential graph. Okay, so I hope you have understood the complete analysis, right? So that's how we are dealing all the circuits. Okay, so now onwards, I won't write much. Okay, I will not be writing everything. I will be telling in words, and whatever the equations and everything that we know, that we will be writing. So we won't be understanding the circuits very deeply now. We will just tell what is actually happening. If you want to write, you can write it on your own or just understand it. Okay, so this is the circuit given to you. You have to comment on VC, VR and I guess you can do it on your own. Just try writing down the equation, draw the graphs, okay, and then match it. Also, try commenting how the circuit is working, like what is happening initially, what is happening, then what is happening. Okay, so let's just solve the circuit. Okay, we won't solve by equations and everything. We will solve by the simple thing. At t equals to 0, we have to short circuit it, then we have to open circuit it. Okay, so yeah, no voltage across the capacitor initially. So circuit for t greater than 0. Okay, so what I would do, I would write 5 ut here. Okay, this is capacitor C, this is resistor R, and this is VC, this is VR, and this is current I. What happens at t equals to 0? I will just write down here. At t equals to 0, what happens? Capacitor acts as short circuit, right? This is 5 ut. The capacitor is acting as a short circuit, and this is R, right? So this is your VR, this is your current I, and this will be your VC. So tell me, what is the value of VC at t equals to 0 plus? That is 0 volt. What is the value of VC at t equals to, sorry, not VC. Tell me, what is the value of VC at t equals to 0 first? That is 0 volt. What is the value of VC at t equals to 0 plus? That is also 0 volt. But why? Because the current flowing through the capacitor at t equals to 0 plus is 5 by R. What is the current? 5 volt and resistance R. So current is 5 by R. Since the current is finite, then only you can apply this rule. Okay. So VC 0 plus is 0 volt, I 0 plus is 5 by R, and what is VR 0 plus? That is 5 volt. Right? At 0 plus, the complete voltage is coming. Now, what is happening at t equals to infinity? At t equals to infinity. What is happening at t equals to infinity? At t equals to infinity, what happens? The capacitor becomes open circuited, right? The capacitor becomes open circuited. So this is becoming open circuited. Why it is becoming open circuited? Because it has charged fully and it can't charge more, and there can't be any current through the capacitor. Okay, this is 5 ut. Okay, and this is a resistor R. Now this is your VC and this is your VR, and this is your current. What is the current at t equals to infinity? 0 ampere, right? Because no current should flow through the capacitor, so the current is 0 ampere, right? That means your VR at infinity will be 0 volt, because if the current is 0 flowing through it, so VR at infinity will be 0 volt. What will be VC at infinity? Let's just assume if this is ground, this is 0, this will also be 0. If this is 0, this will be 5, right? So VC at t equals to infinity will be 5 minus 0, that means 5 volt. Are you understanding this point? At t equals to 0, you just short circuited, so your VC is 0 volt, your I 0 plus is 5 by R, and VR 0 plus is 5 volt. And what is happening at t equals to infinity? Open circuited. So current is 0, VR is also 0, and VC is 5 volt. So your VC is getting charged from 0 to 5 volt. Your VC is getting charged from 0 to 5 volt. Your I is, what is happening with I? I is getting from 5 by R to 0 ampere, and what is happening with VR? It is going from 5 to 0 volt. Okay, so we will just write it down. So let's first write about VC. So VC 0 plus was 0 volt, and VC at infinity was 5 volt. Okay, so what will be the equation of VCT? Infinity plus 0 minus infinity e to the power minus t upon tau. Now find the value of tau. So I guess I can write down the value of tau here. Time constant. Okay, tell me what will be the time constant. Just short circuit this voltage source. Okay, I am short circuiting the voltage source. So this capacitor will come like this, and this is the resistor. So what is my C effective? Again it's C. What is my R equivalent? It's R. So what is my time constant? RC. So again my time constant is RC. So what is my final equation? That is 5 into 1 minus e to the power minus t upon tau. Okay. So from 0 to 5 it will rise. VC with respect to time. So from 0 volt to 5 volt it is rising. Okay, well and good. Now next we will write VR. I can write VR. VR at 0 plus. What is happening? VR at 0 plus. VR at 0 plus was 5 volt, then it goes down to 0. 5 volt, and then it goes down to 0 volt. So what will be the equation of VRT? From 5 to 0, 5 e to the power minus t upon RC. Okay, here 2 is RC. Okay, about VR with respect to time t, it is going down from 5 volt to 0 volt. Okay, now what about I? What was happening? I at 0 plus was 5 by R, and I at infinity was 0 ampere. Okay, so what will be the equation of I? That would be 5 by R e to the power minus t upon RC. Okay, so it will start from 5 by R ampere and goes down to 0. It starts from 5 by R ampere and goes down to 0. So this is the equation of I t. Okay, and one more thing, always apply ut, right? Because we are dealing for t greater than 0, right? Okay. Now, this is the final analysis. This is the analysis of the complete circuit. Now, if someone asks you what is really happening in the circuit, understanding the circuit, okay, the point that we mentioned before, understanding the circuit. So, I am not going to write it completely, but I will just tell you, okay, or you should think about on your own first. So, what is happening? Initially, the 5 by R current is flowing. So, this 5 by R current will start charging the capacitor in this direction, right? This 5 by R current will start charging the capacitor. Now, let's assume at t equals to G1, the capacitor is charged to 0.1 volt. Now, if the capacitor is charged to 0.1 volt, tell me what is the value of I now? If the capacitor is charged to 0.1 volt, tell me the value of I. It will be 5 minus 0.1 by R. That means 4.9 by R. If here we have 5 volt, here we have 0.1 volt, that means we will be having 4.9 volt here. That means 4.9 by R. So now, after some time, let's assume the capacitor is charged to 1 volt. So what will be the current? 5 minus 1 by R. That means 4 by R. So slowly the current is reducing and the capacitor is gaining some voltage. When the capacitor gains 5 volt, what will be the current? 5 minus 5 by R. That means 0 by R. That means now there is no current flowing through the capacitor. So the capacitor is charged to 5 volt. The current becomes 0. Also, you can comment on the VR waveform as well, because so slowly VR is reducing. First, when capacitor is charged to 0.1 volt, that means VR was 4.9. When capacitor is charged to 1 volt, VR was 4. When capacitor is charged to 2 volt, VR was 3. When capacitor is charged to 3 volt, VR was 2. Okay, so this is what is happening in the circuit. I'm not going to write it, but I hope you have understood what is really happening in the circuit. Right? Have you understood? We'll repeat once again. Initially, no voltage across the capacitor, so 5 by R current is flowing through the capacitor. The same current charges the capacitor. Let's assume at time t equals to t1, the capacitor is charged to 0.1, and because of the 0.1 voltage, the current flowing in the capacitor is 5 minus 0.1 by R, that is 4.9 by R. Now the current is slowly getting reduced, but the current is having the same direction. That means it will keep on charging the capacitor. So when the capacitor is charged to 5 volt, at that time the current will be 5 minus 5 by R, that means 0 by R. So this is what steady state is. This is what steady state is, and the capacitor will not charge further. So at steady state, the capacitor is having 5 volt, the current is 0, and the value of VR is 0 volt. That's it. This is what is happening in the circuit. Okay? I hope you understood the concept. Now, this is the circuit. You have to comment on VC, VR, and I. I think you should do it on your own. Okay? So, let's just see the circuit. Okay, they have already given UT. So, just see the circuit at t equals to 0. At t equals to 0. I also, you can comment on IC as well. This is IC. Okay. So at t equals to 0, what is happening at t equals to 0? The capacitor will be open circuited, right? Sorry, short circuited. Sorry. Capacitor will be short circuited. This is 5 ut. This is resistor R1 and the value across it is VR. This is R2 and this is the capacitor C. The capacitor acts as a short circuit. So what is actually happening here is that this is shorted, right? The capacitor acts as short circuited. So this is current I, right? And this is current IC. So can you tell me what is happening at t equals to 0? Let's just assume this current is I1, I will call it. This current I will call I1. So tell me what is happening. Tell me what is the value of I1 at t equals to 0? I1 at t equals to 0. Can anyone tell what is the value of I1 at t equals to 0? If the capacitor is short circuited, so will there be any current through the R resistance? No, the complete current will be flowing through the short circuit path only. So I1 will be 0 ampere. What will be the value of I at t equals to 0? Plus you can write. If this is 0, this will also be 0. So the current will be 5 by R1. 5 volt is there. This is 0. This is shorted. So this is also 0. So 5 by R1. Current is 5 by R1. Okay. What is the value of IC at t equals to 0 plus? That will be the same as I at 0 plus. That will be 5 by R1. Okay. Now tell me what is the value of VC at t equals to 0 plus? VC at t equals to 0 plus. This is shorted, so it will be 0 volt. Now tell me VC VR. What is the value of VR at t equals to 0 plus? What is the value of VR at t equals to 0 plus? That is 5 volt. If this is 0, this is 0, this is 5 volt. That is 5 volt. Right? So this is what is happening at t equals to 0 plus. Okay. Now let's see circuit at t equals to infinity. So at t equals to infinity, what will happen? The capacitor will act as a open circuit. Okay. Capacitor acts as a open circuit. Yeah. VC 0 was 0 volt. Actually VC 0 was 0 volt. VC 0 was 0 volt and that is equals to VC 0 plus. Why so? Why so? VC 0 is equals to VC 0 plus because the current flowing through the capacitor is finite. You don't need to see this current. Neither you will see this current. You will see only this current because this is the current flowing through the capacitor. Okay. So the current flowing through the capacitor is finite. The current flowing through the capacitor is finite. Yeah. So this current is finite. Okay. So the current flowing through the capacitor is finite. So VC 0 is equals to VC 0 plus. Okay. Okay. So well and good. Now at t equals to infinity, what is happening? The capacitor is open circuited. Okay. This is R. This is R. Now your capacitor is open circuited. This is actually R1. This is R2. This is R1. This is R2. And this is 5 UT. Right? This is VR. And this is VC. This is IC. This is current I. Okay. So tell me, what is the value of current I at t equals to infinity? Tell me, what is the value of current? This current. Now what is happening? This is open circuited. So the circuit becomes 5 by R plus R1. R1 plus R2, sorry. 5 by R1 plus R2. Because the capacitor is open circuited. So the complete current will be flowing in this loop. So 5 by R1 plus R2. Right? Now tell me, what will be the value of I1 at infinity? What will be the value of I1 at infinity? It will be the same, right? 5 by R1 plus R2. Now tell me what will be the value of IC at infinity? Without even watching the circuit or seeing the circuit, you can tell the current has to be 0 because the capacitor will be open circuited, so the current has to be 0. Now someone may get a doubt that, sir, the current is finite, still there is some current flowing, so how can you say this is steady state? Steady state is in steady state the current through the capacitor is 0, not the current in the circuit. The current in the circuit can flow, but the current through the capacitor is 0. That means this shows steady state. Okay, you don't need to worry about all these things. You just need to worry about one thing, that is the current through the capacitor. At steady state the current through the capacitor will be 0. That's it, nothing else. Okay, only one concept we know. At steady state the current through the capacitor is 0, so the capacitor will be open circuited. Also we know that when there is finite current flowing through the capacitor initially, then vc0 is equals to vc0 plus. Okay, and now tell me, what is the vc value at t equals to infinity? Vc value at t equals to infinity, if someone says it is 5, then he is absolutely wrong. What is the value of vc at t equals to infinity? Tell me. This is open circuited, so the voltage across R2 is equals to voltage across R2 at infinity is same as voltage across the capacitor at infinity. So that will be 5 by R2 upon R1 plus R2. Right? And what is the value of VR at infinity? It will be 5 into R1 upon R1 plus R2. Simply potential divider. Nothing else. Vc at infinity is 5 into R2 upon R1 plus R2. VR at infinity is 5 into R1 upon R1 plus R2. Simply potential divider, nothing else. Let me again explain it. Initially the capacitor is shorted, so the complete current is flowing through the capacitor. So the current through the capacitor is 5 by R1. The current in this I1 is, this current I is 5 by R1. Okay, and this is R2 actually. So current I1 is 5 by, sorry, the current I1 is 0 because the complete current is flowing through the short circuit path. Okay, what was the value of VR? That was 5 volt. What is the value of capacitor? What is the value of capacitor voltage? VC voltage, that was 0 volt. Okay, now coming at t equals to infinity, the capacitor is open circuited, so the current I is 5 by R1 plus R2. The current I1 is the same because this is the only path for the current. So 5 by R1 plus R2. What is the value of IC at infinity? At steady state, the capacitor will act as open circuit, so the current will be 0 ampere. And what will be the VC value? VC value will be simply the VR value, VR2 value, sorry, VR2 value. VC value will simply be VR2 value, and VR2 is 5 into R2 upon R1 plus R2. And what will be the value of VR at infinity? That will be 5 R1 upon R1 plus R2. Okay, so now the capacitor is not completely charged to 5 volt. It is charged to 5 into R2 upon R1 plus R2. Are you getting this point? If R2 was 2R and R1 was R, so VC at so this VC at infinity would have been 2R, no? So it would be 10 by 3, right? So we will write it on the next page. So let's just first draw the graph of VC. Okay, so graph of VC. VC at t equals to 0 plus was 0 volt. VC at t equals to infinity was 5 R2 upon R1 plus R2. So it would be 5 into 2R upon 3R. So it would be 10 by 3 volt. So how will the graph look like? VC versus T, from 0 to, it goes till 0 to, it goes till 10 by 3. From 0 to 10 by 3 it goes. Okay. Okay, equation also I can write. VCT would have been 10 by 3 into 1 minus e to the power minus t upon tau. Now the interesting thing is tau. What is tau now? Now this is interesting. Okay, now what is the time constant? So let's make the circuit. So what we will do? We will short circuit the voltage source. So the voltage source is shorted, right? Then we have this R1 resistance, we have this R2 resistance, and we have this capacitor. I will make the capacitor here. So tell me, what is C effective? C effective is C only, right? Here you can see C effective is C only. What is R equivalent? From where you will see R equivalent? From the capacitor terminal, from here. So from here you are seeing the R equivalent. So what is the R equivalent you see? R1 parallel with R2, right? R1 parallel with R2. That means R parallel with 2R. That will give you 2R by 3. So time constant tau is 2RC by 3. Okay. Let me put it in the box. This was an important point. Okay. So what was the time constant? R1 parallel with R2 into C. R1 parallel with R2 is 2R by 3. So time constant is 2RC by 3. Okay. Understood this point? Time constant is 2R by 3. I have to add a page. I have to delete this one. Now how do I delete this one? Forget it. I will do it here. So next we will comment on, just ignore this page. Okay. Next we will comment on VR. Next we will comment on VR. Okay. So we are commenting on VR. So VR at t equals to 0 was 5 volt, because this was shorted, so a complete 5 volt will coming. And VR at t equals to infinity was 5 into R1 upon R1 plus R2. That means it would have been 5R upon 3R. That means it would have been 5 by 3 volt. Okay. So what will be the final equation of VRT? At infinity it is 5 by 3, plus at 0 it is 5 minus infinity 5 by 3 e to the power minus t upon tau. So it would be 5 by 3 plus 10 by 3 e to the power minus t upon tau. So the graph would look something like this. It starts from 5 and goes down to 5 by 3. It starts from 5. This is your VRT and goes till 5 by 3. Now let's make the graph of I. Okay, let's make the graph of I. So what was our I? This was our I. The current through the resistor R1. The current through the resistor R1 was our I. So what was the value of I R1 at t equals to 0? That was 5 by R. 5 by R1. That means that was 5 by R only. And what was the value of I R1 at t equals to infinity? That was at t equals to infinity, what was happening? The complete circuit was short circuited, so it was 5 by R1 plus R2. Right? So it was 5 by R1 plus R2. Okay. So that means it was 5 by 3R. Right? 5 by 3R. So again, it is also decaying. So okay, I will write down the equation. How will I write down the equation? I R1 t. So at t equals to infinity, we have 5 by 3R. Okay. And at t equals to 0, we have 5 by R minus 5 by 3R e to the power minus t upon tau. It would be 5 by 3R plus 15 minus 10 by 3R. into e to the power minus t upon tau, right? Just writing out the equation, just the mathematics, nothing else. Okay. This is t, this is it. So it is starting from 5 by r and it goes to 5 by 3r. Okay, 5 by 3r. And the time constant is, what is the time constant that we have already found? That was 2rc by 3. 2rc by 3. Time constant is 2rc by 3. Okay, so this is the graph for I. Also, we can draw the graph for IC and I1 as well. Okay, so let's talk about IC. So what was the value of IC at t equals to 0? That was 5 by R1, right? That was 5 by R. What was the value of IC at t equals to infinity? That would have been 0 ampere, right? Let's see the circuit again. Initially it was 0, sorry, 5 by R1. Initially it was 5 by R1, then it goes down to, where is IC? Yeah, this 5 by R1, then it goes down to 0, right? Because this is open circuited, so no current flowing. So 5 by R1 to 0, right? So IC from 5 by R to 0. Okay, and what was I1? Initially I1 at t equals to 0 was 0 ampere, right? Because no current was flowing through this resistor. What was I1? This. Initially no current was flowing, then finally the current was 5 upon R1 plus R2. Finally the current was, I at infinity would be 5 upon R1 plus R2 ampere. Okay, so this is also an, yeah, I forgot to write the equation. So for the previous one, ICT would have been exponentially decaying. So 5 by r e to the power minus t upon tau, and tau is 2rc by 3, right? And here from 0 to this one, so I1t would be from 0 to, you are rising to 5 R1 plus R2, so it is 5 by 3R actually, that is 5 by 3R. From 0 to 5 by 3R you are rising, so this will be your equation. Okay, if you directly can't write it, you can write down that from formula as well. I at infinity plus I at 0 minus I at infinity into e to the power t by e to the power minus t upon 2. You can write down by that manner as well. But what happens in decaying form, it is always 5 by r e to the power minus t upon 2. Just the initial value into e to the power minus t upon 2. Because from some value it is decaying down to 0. And when initial value is 0 and final some value is there, so it is already, it is always final value into 1 minus e to the power minus t upon 2. Okay, final value into 1 minus e to the power minus t upon 2. With time you will be having the practice. Okay, you don't need to mug it up. With time you will be able to write it without writing the equation. So you will think, yeah, exponential decaying, so 5 e to the power minus t upon 2, rising to some value, 5 into 1 minus e to the power minus t upon 2. Okay, yeah, so I1 value would be from 0 to 5 by 3r, from 0 to 5 by 3r. Okay, so this is the complete analysis of this circuit. Okay, so let's just forget this. In the next video we will see the concept of impulse current, what really happens if there is an impulse current across the capacitor. So that I am saying, no, infinite current, finite current, infinite current. So that concept we will see in the next video. So till now we have seen all these circuits. Okay, this circuit we have seen, this circuit we have seen. We are writing down the equation. In the exam, they may give the values, C value and R value. So you can solve the problems. We will solve the problem, but here we are developing the concept. So we will develop so much of concept that problem will be solved in seconds. Okay, I have seen like students struggling a lot in the problems. The main problem is there is that they are not focusing much on the concept. If you focus much on the concept, the problem will be very easy to you. Okay, we will see so much of concept that you will find no difficulty in solving most difficult problem. Okay, so yeah, so this is what is happening. This was the circuit that we have already seen, and then we saw this circuit. So in this circuit, initially the capacitor was shorted, so 5 by R current was flowing, so the capacitor was getting charged slowly. Yeah, if they ask you to explain this circuit, can you think of it? Why it got developed to 5 by R2 upon R1 plus R2 value, not to 5 volt. So if they ask you to explain this circuit, can you explain what is happening? So initially what is happening, 5 by R1 current is flowing through the capacitor. So that current charges the capacitor and it develops some voltage. Now the same voltage developed is developed across the R2 resistance as well. Let's assume the capacitor C is having 1 volt. So the same 1 volt will go at R2 resistance as well. So the R2 resistance will drive 1 by R2 current, right? Let's assume at some point it is having 1 volt. So this R2 is driving how much current? 1 by R2. How much current is coming from here? 5 minus 1. That means 4 by R1 current. So some part of 4 by R1 current is coming. That complete current is not going here. Right? That complete current is not going here. Only 4 by R1 minus 1 by R2 current is going here. Okay. Now let's just assume. Now, just for understanding the problem, what you will do, let's just assume R1 is equals to R2, R1 equals to R2 equals to R. Let's assume. Okay. So tell me at what value the capacitor will get stabilized. Let's assume R1 equals to R2 equals to R. So what will be the steady state value of capacitor voltage? That will be 2.5, right? 2.5. So let's just assume we are having 2.5 voltage here. So what will happen? This same 2.5 will come across R2. So here we will be having 2.5 by R current. Now if 2.5 is there, here we have 2.5, here we have 5. So here also we are having 2.5 by R current. So 2.5 by R current is coming and the same current is drawn by the resistor R2, 2.5 by R. So what is the current flowing through the capacitor? 0 ampere. That means this is the steady state. Are you getting this point? Initially 5 by R1 current was flowing, 5 by R current was flowing. So the capacitor was getting charged. But slowly the same voltage that was across the capacitor, the same voltage R2 was having. So because of that, R2 was also drawing some current. Now R2 is also eating up some current. So the capacitor is not having the same complete current. Okay, this complete current is not being fed to the capacitor. The capacitor is having some less current. And now the capacitor is charging, and at some point 2.5, when there is a 2.5 voltage, at that time the capacitor is having 0 current, and that means that is the steady state. Okay. Also here you will see the capacitor is driving low current, right? Capacitor is having low current, that means it will charge slowly. So also one more thing you get to see here is that, what do you see? The time constant is also low, right? In the previous problem, what was the time constant? RC. The time constant was RC in the previous problem. But here you will see the time constant is low, 2 RC by 3 it is. So 2 by 3rd of RC. Why so? Because the capacitor is driving low current. That's why. So are you getting the practical meaning? Okay, if you don't get the practical meaning, just try getting the practical meaning, because this is very important for you. Okay, and if you just try to play with the equations, then it is also fine. You will be able to solve the problem. But if someone asks you in the interview, so that will be an issue if you just solve by the equations. Okay, they expect you to tell the concepts, like what is actually happening in the circuit. So in the interview they will expect things like that, but in the exam, in the written test, you will be able to get to the final answer by the equations only. Okay, so I have told both of the things, from equation as well, from the concept as well. Okay, so what is actually happening in the circuit. So in the next video we will see the concept of infinite current. Okay, that's very important. Okay, and I have seen like many of the educators ignore this topic, but this is one very important concept that you need to know. We have already seen the concept of impulse, right? What is impulse voltage, what is impulse current, that we have already seen. Now we will see if it is given to a capacitor, what happens. So the infinite current is given to a capacitor. Now what will happen in the capacitor, that we will see in the next video. Okay, so if you find the videos helpful, please do share it with your friends and also like it. Okay, thank you. Hello everyone. So in this video what we will discuss? We will discuss about the infinite current through the capacitor. So till now what I have told you is that the capacitor has a property that it doesn't change its voltage immediately. The voltage it is having at t equals to 0 minus, it will have the same voltage at t equals to 0 plus. Okay, but this is the case only when there is a finite current, right? I told you this thing. I emphasize on this point as well. Finite current. Now what do you mean by infinite current? So I have already told in the basics. What do you mean by infinite? If something is infinite, that means it is impulsive, right? That means just for a moment it came and then went off. It will come and went off. If there is something infinite, it can't be there for all the time. Like it cannot happen that it is there at t equals to 1 and it is there at t equals to 1 plus as well. If it is there at t equals to 1, that means it will be there for t equals to 1 only. It won't be there for t equals to 1 plus. That's why when we make the graph of delta t, we make it like this, right? Just at t equals to 0, not at t equals to 0 plus. At t equals to 0 plus, the value is 0. And that's why we define the delta function like this. What is delta function? Delta function will give the value at infinity only at t equals to 0. Apart from t equals to 0, it is always 0, right? So now what I am doing, I am forcing an impulsive current in the capacitor this time, and I will write down the equation of VCT, because what we have studied that voltage cannot change, right? So tell me one thing, what is the value of VC0 minus? That is 0 volt. Now let's find the value of VCT. Let's find VCT. Okay, VC0 minus, you know. Okay, you don't know this, let's just forget it. Now I will just write VCT. Okay, let's just forget VC0 minus. So I will just write VCT. So it will be 1 by C integration minus infinity to t I of t dt. This is the expression, right? What is the expression of I of t? I of t is I naught delta t, right? I of t is I naught delta t. I naught delta t dt. I naught is a constant term. It can be taken outside. I naught by C minus infinity to t integration of delta t ut. Tell me, what is the integration of delta t? What is the integration of delta t? Integration of delta t is I naught by C ut, right? Integration of delta t is ut. I have told you the integration of impulse will be step, integration of step will be ramp, and differentiation we will go from this side. Differentiation of ramp will be step and differentiation of step will be impulse. So what do you get the expression? The expression of VCT came out to be I naught by C ut. So it came out as step. So now if I make the graph of VCT, so what is happening? How do you make the step graph? 0. For t less than 0 it is 0, and then suddenly it goes I naught by C, right? Now tell me one thing, here IT is I naught delta t, right? So what is I naught? I hope you all will be able to tell me what is I naught. Is it a current or charge? I naught is a current or charge? It is charge. Why so? Because the unit is ampere into second, right? So it is a charge, right? I have told you I naught is not the magnitude, it is the area, and area is current into time. So ampere into second. And what does ampere into second give you? Coulomb, right? Because I is dq by dt. If dt goes here, so ampere into second will give you Coulomb. So this is charge. So what do you mean by an impulsive current? I have already told this fact. What do you mean by an impulsive current? That means in zero time you are giving I naught amount of charge to the capacitor, right? So if I am writing I naught delta t, so what does that mean? You are giving I naught amount of charge, I naught amount of charge in no time, right? So what is the value of charge q? Charge q is I naught. What is the value of capacitor? Capacitor C is C only, right? So what will be the voltage? Voltage V will be Q by C. That means I naught by C. So here you can see what is the voltage? I naught by C, right? And what do you see here? What do you see here? VC 0 minus capacitor voltage is VC. Okay. VC 0 minus was 0 volt. Now what is VC 0 plus? Tell me what is the value of VC 0 plus? VC 0 minus was 0 volt. What is the value of VC 0 plus? That is I naught by C. This was just another way. Okay. I will just call this method 2. Okay. This was just a method 2 to tell what will be the VC waveform. Okay. This was the equation, and this was like you can think I naught amount of charge is given and capacitor is C. So what will be the voltage? I naught by C. So here VC 0 minus was 0 volt and VC 0 plus is I naught by C. So what do you understand here? What do you understand? The capacitor doesn't follow its property of not changing the voltage immediately in case of what? In case of impulsive or infinite current. So what do you understand by that? Whenever there is an infinite current in the capacitor can change its voltage immediately. Okay, so I will write it and I will just pause the video and will write it. Okay. Okay, so I have written a very important point, that is whenever there is an infinite current flowing through the capacitor, it will change its voltage immediately from 0 to some value. Okay, got it? Now let's see this question. We have seen this question in basics of network. If I haven't taught you the concept of transient and concept of capacitor, if I had asked you what is the value of VC2, what would you say? C1 upon C1 plus C2 into 5, right? Right? If you remember the basics, in basics we just divided the potential, considering this has the impedance of 1 by omega c 1 by j omega c2, and this has the impedance of 1 by j omega c1. So we just divided it in the inverse proportion, right? But here we will see what is actually happening. So let's just make the circuit. Let's just make the circuit once again. I am just making both of the terminals as grounded, because if this is grounded, this will be also grounded, this will be also grounded. So like this I am making. This is C1, C2, this is VC1, and this is VC2. And here I will write 5 UT, right? So if you can tell what is VC2, VC2 will be C1 upon C1 plus C2 into 5, right? But let me show you one thing. Now circuit initially. So tell me what will happen initially. At t equals to 0 plus I am talking about, okay? At t equals to 0, sorry. This is the voltage source we are having, right? Now this is shorted. and this is also shorted because both of the capacitors are having no voltages. Even if they were having voltages, they would be replaced with the voltage source. Let's assume if C2 was having 3 volt, it would be replaced with the voltage source of 3 volt, right? And now I will just write 5 here, okay, 5 volt. Now tell me what is the value of current? IC. What is the value of current? IC. That is 5 by 0. No impedance, short circuit path, 5 by 0. That means infinite current, right? So what will happen? Capacitor will change its voltage immediately. Its voltage immediately. How they will change? They will just divide it in inverse proportion. Why is it happening? Because the current is same. In both C1 and C2, the current will be the same. Whatever the current is, infinite current is there. We will find the value of current as well. So we need to comment on VC1, VC2 and IC. I will just make IC. What will be VC1, what will be VC2 and what will be IC. So we need to comment on these three things. So since both of them are connected in series, that means both of them will be having the same current. That means both of them will be having the same charge, right? If both of them are connected in series, that means both of them will be having the same charge, right? So we will just divide the voltage in inverse proportion, or you can see what is the impedance provided by the capacitance. It is 1 by j omega c. So if we just divide it in inverse proportion, it would be j by omega 1 by j omega c upon 1 by j omega c plus 1 by j omega c2. So it would come out to be c2 upon c1 plus c2, right? Just like resistors, we can divide it, right? So I will just write this is method 1 of solving. Why I am not able to make a straight line? C1, C2. By the way, it's Diwali today. Here. Okay, this video will not be uploaded on Diwali for sure. This will be uploaded later on. But today, this is Diwali. Yeah, just wanted to share. So what will be your VC2? Tell me. It will be 5 into C1 upon C1 plus C2 into UT. What is VC1? What is VC1? Inverse proportion. 5 C2 upon C1 plus C2 into UT. Now what will be the current? That I will tell you. Okay. No worries. That I will tell you. Or here only I can tell. What is current? IC. What is current? IC. It can be C1 dVC1 by dt. Right. Just the differentiation. Or it can be C2 dVC2 by dt. Right. So I will just solve this one. C1 into differentiation of this. Tell me what will be the differentiation of, yeah, this is VC1. What will be the differentiation of this? This is just a constant value, right? This is a constant value. So I can write A into UT. What is the differentiation of A into UT? It is A into delta T, right? Differentiation of UT is A into delta T. So simply the differentiation would be 5C2 upon C1 plus C2 into delta T. So what will be your IC? IC will simply be 5 C1 C2 upon C1 plus C2 into delta T. So this is the impulsive current we are having, right? Now we can make the graphs as well. For VC1 we can draw, for VC2 we can draw here, and for IC we can draw here. VC1, this is VC2, this is IC. What is VC1? Initially it is 0, then it went up went like this, right? So this value is 5C2 upon C1 plus C2. Always remember you have to divide it in inverse proportion. Okay. Sometimes I have seen students dividing it in not in inverse proportion but in the proportion. But this should not happen. You should divide it in inverse proportion, right? So it would be 5C1 upon C1 plus C2. And what is the value of IC? This is an impulse. And the value is 5C1 upon C1 plus C2. So this is an impulsive current we are having. So these are the three graphs. So graph I will not make again and again, but I will tell you another method as well. Also you can comment on the graph by seeing the waveform as well. Like if you know the waveform of VC1, you can make the graph of IC as well. How? Just you know the waveform. So you are seeing that from 0 it is charging to some value, right? From 0 to suddenly the voltage is rising. So if suddenly voltage is rising, what will be the differentiation? Differentiation will be impulsive. So if you are given a voltage waveform and they ask you to comment on the current waveform, so you can do that, right? They have given the voltage waveform, so from here to here you can come, because you simply know IC is equals to C dVc by dt. Just the differentiation of the voltage waveform into the capacitance value. Differentiation of voltage waveform into the capacitance value, that is the current of the capacitor. So that you can do, right? Now let's talk about the method 2. Okay, let me add a page. Okay, so let's talk about method 2. Okay, so this was your circuit 5ut C1 and this is C2. Here we will use equations actually. Okay, this is VC1, this is VC2. Okay, one thing you know, C1 C2 are in series, C1 and C2 in series, that means current same, that means current same, and that means charge same, right? If charge is same, that means I am saying Q1 equals to Q2. That means I am saying C1 VC1 is equals to C2 VC2. This is equation 1. What is the second equation? Second equation is 5ut is equals to VC1 plus VC2. So from here you can get the value of C1, right? Value VC1 value would be C2 VC2 by C1 plus VC2. So what will be the value of VC2? Value of VC2 would be 5 into C1 upon C1 plus C2 into UT, right? And what will be the value of VC1? That would be 5C2 upon C1 plus C2 into UT. So by this method also you can solve, right? Right? So this is also one method. Okay. So I hope you have understood my point here. The point I wanted to deliver here is that whenever there is an infinite current flowing, how will you check the current is infinite? By drawing the circuit like this. We drew the circuit here and we got to know that the resistance is 0. The resistance provided by the capacitance is 0. If the complete resistance in the circuit is 0, that means there will be infinite current. So if there is infinite current, there will something happen. And something, what will happen? The capacitor will change its voltage immediately. Okay. So this is the point I wanted to deliver here. Now let's see one more important point. This is a important concept of step function. Okay. So this is a step function, right? This is our step function, right? For t less than 0, what is step function? This is ut. So it is 1 for t greater than 0 and it is 0 for t less than 0. Now we will talk about at t equals to 0. At t equals to 0. So just see one thing, at t equals to 0. At t equals to 0, it will provide you infinite frequency. Why so? Because I have already explained this concept in basics of basics of signal sensing systems. Okay, if you don't know why it is infinite frequency, you just go to the basics of signal system video and you will get to know there. Okay, I will just talk in short, because from 0 to suddenly it is rising to A. If it is rising slowly, that means it has omega frequency. If it is rising some faster, that means it has frequency greater than omega. If it is rising in no time to A, like from 0 to in no time it is rising to A, that means it is having infinite frequency. So if it is having infinite frequency, so if we talk about the capacitance provided by the resistance provided by the capacitance. If we talk about the impedance, I should write impedance provided by the capacitance. Okay. So if we talk about the impedance that is provided by the capacitance, so tell me what will be the value? Zc will be equals to 1 by j omega c. That means 1 by j omega value is infinity c. So I can write nearly 0 or I can write very low, right? So what do you understand? At for step function, I think I should keep it a bit down now. So what do you understand by this point? Note, very important note. Okay. For step function at t equals to 0 or omega equals to infinity, the capacitor provides very low impedance. Are you getting this point? If there is step function applied, that means it has at t equals to 0 it has infinite frequency. Infinite frequency means 1 by j omega c. Infinite means very low. So if frequency is very high at t equals to 0, that means capacitor is providing very less impedance, right? So here the capacitor will provide very less impedance. Now if two resistors are connected in parallel, let's assume one is having a value of 1000 and one is having a value of 1. So what will be the equivalent? It will be near to 1, right? You know it, right? It will be near to 1. What will be the equivalent of this? 1000 into 1 upon 1001. So it will be near to 1, right? So you can replace the parallel combination of RC with a single capacitor. Do you agree to my point? And you can replace this with a single resistor. Why so? Because if 1001 is connected in series, it will be nearly equals to 1000 only. So this is some finite value and this is very low value. So if very low and finite value is connected in parallel, it will be replaced with a very low value. If very high value and some very low value, some finite value and very low value are connected in series, that means it will be replaced with the finite value. So at t equals to 0, you can replace something like this. And further you can replace the capacitor with short circuit depending on the circuit. We will see the circuits, then you will get to know whether I should replace it with short circuit or I should keep it like capacitor only. Okay. So that's why we saw this circuit now, RC circuit, and there was a step input applied. So what did we do? We said that there was zero voltage across it, so we replaced it with the short circuit. This is also a good concept, but there is also one more concept that at t equals to 0, we are having infinite frequency. So because of infinite frequency, this will be replaced with a single capacitor only. This R and C combination, what I wanted to say here is that, let me just redraw it. Okay. Let me just explain it with an example. So what did we do? This was our step function applied. So what did we do in this problem? At t equals to 0. At t equals to 0, what did we do? We just said this will be R will be there and this will be replaced with short circuit. This circuit we made, right? Now what I am saying, at t equals to 0, we are having infinite frequency, and because of infinite frequency, this will provide very less impedance. So this series combination of RC can be replaced with R only. So let's see. This is what we did there. While understanding this circuit, I told you there was no voltage on the capacitor, so you can replace it with the short circuit. That was also a good concept. That is also fine. But also we can see by this thing, if we are applying the step input, that means we can replace the capacitor, we can replace the series combination of resistance and the capacitor with a single resistor only, and this is what we did here. Are you getting my point or not? So the previous circuits that we have solved, you can analyze those circuits with this analysis. Okay. Okay. Now let's talk about steady state at t equals to infinity. So what do you mean by steady state? At t equals to infinity, the frequency is 0. Okay, at t equals to infinity at steady state. This was our this was our step function, right? So at here it is omega equals to 0, steady state. Okay, at steady state you will have omega equals to 0. That means it is nearly equals to infinity. That means very high, right? Very high. So what do you understand by that? What do you understand by very high? Yeah, so that means capacitor provides very high impedance at steady state, right? So if it is providing very high impedance, that means what will happen? The parallel combination of RC will be replaced with a single resistor only, because this is a finite value. Let's assume this is 500 and this is very high. That means this is 1 mega ohm. So will be replaced with the lower value. So what is the lower value? That is resistance, right? And what will happen to this series combination? It will be replaced with the capacitor only, right? It will be replaced with the capacitor only, because this is very high. Furthermore, it can be replaced with open circuit as well, right? But depending on the circuit. So this is an important concept that will be used in the further analysis. So I have told you, at t equals to 0, capacitor, you don't need to mug it up. You will just see step function. Okay, at t equals to 0, infinite frequency. That means capacitor is providing very less impedance. If capacitor is providing very less impedance, that means the parallel combination of RC can be replaced with the capacitor, and series combination of RC can be replaced with the resistor only. And at t equals to at t equals to infinity and steady state, frequency is 0. If frequency is 0, that means the capacitor is providing very high impedance. So parallel combination will be replaced with the resistance only, and the series combination will be replaced with the capacitor only. Are you getting my point? No need to mug it up. This was just a concept. You can think it in real time only. Whenever the interviewer is asking the question, or whenever you are solving it in the exam, you can think it there only. Okay, no need to mug it up. Okay, so while going to the next analysis, next question actually, or next circuit, we will study the basics of Laplace transform. Now why it is important? Look, the interviewer doesn't expect you to solve the circuit by Laplace transform. Also in the exam, if you need to solve it very quickly, you shouldn't use Laplace transforms, because it makes the problem very mathematical. Like, you don't need to think. When we will solve the circuit, you will get to know. If you are solving the circuit by Laplace transform, you won't need to think anything. Okay, you will just replace the circuit and just do mathematical analysis. That's it. But what they expect a intuitive approach, right? And also, if you are doing it for exam or gate exam or anything, there also you will try to solve the question very quickly. So I will tell you both of the method, by intuition as well, or how to solve the problem quickly, also by Laplace transform as well. So you should know Laplace transform as well. Like, if there is very complex circuit that you can't solve, so eventually you will solve it with Laplace transform, because it makes the circuit pure mathematical. So we will study the basics of Laplace transform. So what is Laplace transform actually? So whatever we are doing all this thing in time domain, right? These things, time, everywhere there is time. I think I should write it vc2 t, vc1 t. Okay, because all these are function of time. Okay, I should have written here t. Okay, so all we are doing in time domain only. So what does Laplace transform do? It converts it into frequency domain. That's what you need to remember. Okay, it converts the time domain into frequency domain. Very deep analysis of Laplace transform I will teach you in signal systems, and I will teach you very deeply. Okay, you will understand the real difference between the Fourier transform and Laplace transform, that we will see in signal systems. But here, for network purpose, time domain to frequency domain, that's what you need to remember. And S is equivalent to j omega. Actually it is equivalent to sigma plus j omega, but we will understand this point in signal system. So for network analysis, you just need to know the S is equivalent to j omega. Okay, like, we can't really go deeper into the concept right now. I hope you understand the concept. And in the interview, no one will ask you what do you mean by S plus j omega or anything. In the interview of analog domain and all these kind of things, they don't ask you. Okay, that much deeper knowledge. In signal system, I will teach you. Okay, So as is, s is equals to j omega, and what is the, this is the Laplace transform. Okay, this is the Laplace transform. I should write here Laplace transform of xt. What is the Laplace transform of xt? That is x of s, that is minus infinity to infinity x of t e to the power minus st into dt. Mark it, it is minus infinity to infinity. Okay, it's not minus infinity to t, minus infinity to s. It is minus infinity to infinity, complete in time domain. Okay, and then it is like this is just a way of writing that Laplace transform of xt is x of s. Okay, Laplace transform of xt is x of s. Okay, now let's find the Laplace transform of ut. So I am saying that my xt is ut now. Okay, so Laplace transform of xt will be equals to x of s, right? So what is x of s? X of s is minus infinity to infinity xt e to the power minus st into dt. Minus infinity to infinity. What is xt? Xt is ut, right? Xt is ut e to the power minus st into dt, x of s. Now ut is defined from, this is ut, right? Ut is defined from, this is the value 0 to infinity only. So I can write 0 to infinity, and value of ut is 1 e to the power minus st into dt, x of s, minus 1 by s e to the power minus st 0 to infinity. So minus 1 by s e to the power minus infinity minus e to the power 0. This value is 0, this value is 1. So eventually you are getting 1 by s. So what is the Laplace transform of ut? So from here you can see Laplace transform of ut is 1 by s. Let's assume if there was a constant, let's assume if it was aut. So what would happen? A would come out. Here you would written aut, a is constant, so it would come out of the integration. So a would be outside. So you would get answer a by s. So what is the Laplace transform of aut? It is a by s. Okay, right? So we won't solve for all these in network in signal systems. We will solve for everything. Okay, you can solve it on your own as well. Like for ut, what will you do? You will write t here. Sorry, for rt, for a into rt, what will you do? You will put a outside, and rt will be t from 0 to infinity. From 0 to infinity, it will be t, right? For delta t, what you will write? For delta t, you will simply write delta t, and I have told you the integration of delta t. What is the integration of delta t? E to the power minus st dt. So for the integration, you need to write it like this: t minus 0 e to the power minus st into dt. So it is defined only at t equals to 0. So this 0 will go here. So it will become e to the power 0. So it will give you answer equals to 1, right? So that you can do. Okay. So in that way you can solve. Okay, so I will just write down the final answer. You just need to remember the final answer. What is the Laplace transform of a into ut? That is a by s. What is the Laplace transform of a into rt? That is a by s square. What is the Laplace transform of delta t? Laplace transform of delta t is 1. Okay, so it will be a only. So from delta t to you are going to ut, from there you are going to rt. Okay, so first one is 1, then 1 by s, then 1 by s square. So that's how you can remember. Okay, and I hope you have understood the integration concept. Let me tell it more deeply. Let's just assume you are integrating in this way. Okay, you are just integrating this function, or let's just take 0 here. Okay, how do you integrate a impulse function? I am telling you. Okay, so you will see this is defined only at t equals to 0, right? This is defined only at t equals to 0, and my other function is e to the power minus st, that is something like this. So now if we multiply these two, here there is multiplication. So if we multiply these two, only the value will come. Let's assume the value here is, why to assume the value here is 1 only, right? So value here is 1 only. So I am just putting 0 in this function, right? Because it was defined at t equals to 0 only. So if I put e to the power minus s 0, so I will get this value. So if you multiply these two, let's just assume it is having value a. If you multiply these two, a into this, so what will you get? An impulse of a only. If we were having 2 here, so what would you get? A into 2. So an impulse of 2a. So just your impulse is getting multiplied at the point where it is defined. So it is defined at t equals to 0 only. So I am just putting in the function t equals to 0 and getting this value. So finally you will get 2a delta t. Here your a value is 1 only and this value is also 1. So what you will get? You will get simply delta t, right? So this much of thing, this complete thing can be replaced with 1 into delta t only. So now your function becomes minus infinity to infinity delta t into dt. And now tell me what is the differentiation of, so what is the integration of this? That is ut, or you can simply write 1, right? Because minus infinity to infinity, so you can write it as 1. Okay, so eventually you get the final answer as 1 only, and if there was a constant, so you could write it outside. Okay, so this is what is happening. And why did I write ut as 1? Because when you are talking about the Laplace transform, it is only defined from 0 to infinity in case of network analysis. Okay, if it was defined from minus infinity to infinity, the case would have been different, but here we are defining it from 0 to infinity only. Okay, for right-handed signal only we are defining, so it is let's assume ut as 1 only. Okay, but ut is not 1, because 1 means from minus infinity to infinity it is always 1, but ut means from 0 to infinity it is 1. So there is a big difference, but for now just assume ut is 1, because we are not really going deeper into the concept. We are just understanding whatever that is required. Okay, for network analysis. So for network analysis you just need to know what is the Laplace transform of del t, that is 1. If a is there, so constant will come outside and that will be a into 1. So it would be a only. Now what is the Laplace transform of e to the power minus at into ut? That is 1 upon s plus a. Okay, so this is very important, you need to remember it. What is the Laplace transform of cos a at into ut? Just mark everywhere ut is added. Okay, everywhere ut is added. So what is the Laplace transform of cos at into ut? It is s upon s square plus a square. Okay, and what is the Laplace transform of sin at into ut? It is a upon s square plus a square. So this is the major difference. At for cos you will have s upward, and for sin you will not have s upward. Okay, so that is the major difference that you need to remember. Okay, these two are important as well. When we study LC oscillator, these will be used. Okay, and what is the Laplace transform of x1t plus x2t? That is x1s plus minus x2s. What is the Laplace transform of xt into xt t minus t naught? Laplace transform of xt is x of s. What will be the Laplace transform of t minus t naught? That will be e to the power minus s t naught x of s. Laplace transform of xt is x of s. What will be the Laplace transform of x t minus t naught? That would be e to the power minus s t naught x of s. Okay. Okay, let's move on to the next property. It is actually written the integration. Okay, we are talking about the integration here. So if xt is the Laplace transform of x of s, then it will be x of s by s. Okay, if you know the Laplace transform of this, then you can write down the Laplace transform of complete integration as well. So just integration will bring 1 by s. Okay, now tell me what will differentiation will bring? Differentiation will bring x s. Okay, it will bring s. Okay, integration will bring 1 by s. I will just write it down. Okay, integration will bring 1 by s. Mark the thing that it should be from some value, let's just assume minus infinity, to some value t. Okay, the integration should be like this, and d by dt will bring s. Okay, now d square by dt square, it will be like this: x square x of s minus s x of 0 minus x dash 0. Or I should write small here, because x of 0 means x of 0 minus x dash 0. Why I am writing small? This is, what do you mean by x of 0? What do you mean by x of 0 here? What do you mean by x of 0? X t equals to 0. Okay, not x s equals to 0. Okay, just understand this point. Here we are writing x t equals to 0. Okay, let's just assume we will take an example for this. So I will add a page. So we already know example we are taking. Okay, so before taking the example, let's just see this form. Okay, what is this form? Laplace transform of dnx by dt. Just we are differentiating here once, here twice, and here we are differentiating n times. So just see this formula. You don't need to mug it up. First, s to the power n x of s minus s to the power n minus 1 x of 0 minus s to the power s to the power n minus 2 x dash 0, and then here we are differentiating 9 minus 1 times. Okay, so like if there was two if there was differentiation was done twice here. Okay, here the differentiation was done twice, so eventually we are differentiating only once. And what do you mean by x dash 0? That is also important. Okay, what do you mean by x dash 0? That is dt by dt x of t at t equals to 0. Okay, let's just assume if your xt is 5t. Okay, now someone will ask you what is the value of x dash 0. So what will you do? Tell me. X of 0, what is the value of x of 0? Now differentiate it. X dash 0, that is 0. This is wrong. First you need to differentiate. What is the differentiation of x dash t? That is 5. Now put 0. X dash 0 is 5 only, because it is always 5. So this is the correct answer. Okay, x dash 0 is 5, not 0. If you don't know this thing, you can write it in some box and keep it there. Okay, first you will not put the value. First you will differentiate, then you will put the value. So this is what I am meaning here. First differentiate, then put the value. Okay, and for understanding this, I will take an example. Okay, so Laplace transform of RT, you tell me what is the Laplace transform of RT? That is 1 by s square. Now what will be the Laplace transform of UT? That I need to find. Okay, so what I will do? D by dt of RT is UT. D by dt means s will be added upon s square will be the Laplace transform of u of t. So from here you are getting Laplace transform of u of t will be 1 by s. Okay, okay, so in most of the cases what happens is that these condition will not even come, because there will be no initial condition. Your x of t would be 0 for t less than 0, like there would be no initial condition. Even if there is an initial condition, then only these things will come. Okay, so you will not have to use these examples. Actually you will only have to use this term, the first term only. Okay, if thrice differentiation is done, s square x of s. If 4 times differentiation is done, sorry, x cube, sorry, if 4 times differentiation is done, s to the power 4 x of s. If 5 times differentiation is done, x to the power 5 x of s. Once differentiation is done, x of s into x of s. Okay, so you won't have to use this one further, but just to you should know these basic things, so that's why I am telling. Okay, okay, so now what is the Laplace transform of e to the power minus at into x of t? It will be x of s plus a. We can understand this with an example as well. Like what is the Laplace transform of ut? That is 1 by s, right? What will be the Laplace transform of e to the power minus at into ut? It would be x of s plus a. If x of s is 1 by s, what will be x of s plus a? It would be 1 upon s plus a. Also, you also know e to the power minus at into ut. Here only I told you Laplace transform of e to the power minus at into ut is 1 upon s plus a. Also by property here as well you can see by this property. Laplace transform of ut is 1 by s. So Laplace transform of e to the power minus at into ut would be 1 upon s plus a. Right? I hope you understand this concept. Now this is an example we are taking. No, not the example. So Laplace transform of t into xt, that would be minus d by ds x of s. Okay, this would be minus d by ds x of s. Now here we can take an example. Laplace transform of ut is 1 by s. What will be Laplace transform of tut? Or what you can say, Laplace transform of rt, right? So Laplace transform of tut would be minus s d, sorry, not minus s, it would simply be minus d by ds into x of s, that is Laplace transform of ut. And what is the value of Laplace transform of ut? That is 1 by s. So it would be 1 by s square, right? So Laplace transform of rt is 1 by s square. Just the Laplace transform of this value, t into ut, Laplace transform of this and the differentiation, right? So Laplace transform of this 1 by s into the and the differentiation, that would be 1 by s square and minus sign also. So Laplace transform of rt is 1 by s square. So this is an example only. Okay. Also, why am I taking this example? Because you need to remember this. Okay, if you remember this, it is very good. What is the Laplace transform of t into e to the power minus at into ut? Also, you need to remember from left to right, also from right to left as well. Okay, like if they have given 1 upon s plus a, so you should be able to tell it is the Laplace transform of e to the power minus at into ut. If they are giving a upon s square plus a square, you should be able to tell it is the Laplace transform of cos at into, sorry, sin at into ut. Okay, if it is given a by s, you should be able to write a into ut. Okay, so if this is given, what will be the final answer, that we will see. So differentiation of the Laplace transform of this value, so it would be minus d by ds 1 by s plus a. So what would you get? Final answer as 1 by s plus a square, right? So what is the Laplace transform of t into e to the power minus at ut? That is 1 upon s plus a whole square. Okay, so you should be able to write in the both way. If somewhere it is written 1 upon s plus a square, so what should click in your mind? T into e to the power minus at into ut. If somewhere 1 upon s plus a is written, what should click into your mind? It should be e to the power minus at into ut. If somewhere 1 upon s is written, that means it is ut. Okay, so these things should click in your mind. Okay, so just see the picture once again, it will be all clear to you. You won't need to mug it up. Okay, because you will be using it more and more time in your complete preparation, so it will remain there in your mind. So you just don't need to mug it up currently. If we will solve the circuit, so it will be in your mind later on. Okay, so now we will solve one circuit using Laplace transform only. Okay, but before going to that, we should know how the circuit elements will behave considering the Laplace transform. Let's just assume there is a resistor, so how will I make it in the Laplace transform? Okay, so before going to the analysis, just tell me one thing. What do you mean by Laplace transform? From time to frequency, right? Is resistor anyway dependent on time? Let's just assume you at 1 o'clock, the value of your resistance is R for a step input. If you apply the ramp input at any time at 2 o'clock, the value will be R only. If you apply an input like this, something like this, at any time, your value of resistance will be R only, right? If I am writing 5 ohm, that means 5 ohm for any kind of input. At any time, at any frequency, it will be always 5 ohm. At any frequency, any time, anything, it will always be 5 ohm, right? That means it is not dependent on the time. Resistor is not a function of time, right? So the impedance provided by the resistance, that is equals to R, is not a function of time. So this will be replaced simply by the resistance only. So no changes will be done in case of Laplace transform. Or also you can see here, Vt is equals to It into R, right? So Vt by It is equals to R. That means Zt is equals to R, right? So basically your Z of S is taking the Laplace transform, it will be R only. because it is just a constant value which is not dependent on the time. So the impedance provided by the resistance will be R only. Okay. Now let's talk about the capacitor. Okay. So first we are assuming the capacitor is having no initial voltage. That means Vc 0 minus is 0 volt. Okay. Now let's talk about the equation of Vct, or I can write equation of Ict. So Ict is C dVct by dt, right? So capital I, capital I, capital ICT. So if I am writing capital ICS, it would be C into S Vc of S minus the value at t equals to 0, right? What did I write here actually? Okay, here I wrote it wrong. S x of s minus the value at x equals to 0. Okay, x t equals to 0 minus value x 0. Okay, so this also comes here. Okay, now what is the value of this? This is 0 only. This is time domain. I am writing about VCT. Okay, so this is 0 only, right? So what do you end up with? CS VCS, that is your ICS. So if I am talking VCS by ICS, that means Z of S, that is equals to 1 by S. What is this? This is impedance provided by the capacitor in Laplace transform. Impedance provided by the capacitor in Laplace transform. This is the value, right? Okay. Now the capacitor is having some initial voltage. So what will happen now? ICS would be C, sorry, not C, CS, right? C, yeah, it would be C S Vc of S minus value at, okay, this is Vc we are talking about, Vc, time domain value at t equals to 0. So C S Vc of S, what is the value at t equals to 0? There is something wrong, I guess. Yeah, it's fine, no problem. So it is V naught. So it is having initial voltage of V naught. Okay, so that is IC of S. Let's just forget it. So what will be your IC of S? That would be CS Vc of S minus CV naught. Okay, now I need to find Vc of S upon IC of S, right? So I just need to find the value of Vc of S. So I am writing CS Vc of S is equals to IC of S plus CV naught. Is that fine? It is fine. So Vc of S is equals to IC of S upon CS plus V naught by S, right? So this is the final formula. So what is this? From here what you can understand is that, from this term you can understand is that here your Vc of S upon IC of S will give you 1 by CS. So basically the impedance will be 1 by CS, but along with that we will have a voltage source as well. Are you getting this point? Let me show it in the next page. Okay, I will have to add up a page. Basically this is the summary, that is, if your capacitor C is having an initial voltage of V naught, so what will you do? You will first, what we are doing here, impedance in Laplace domain, So what you will do, you will first take out the voltage source You will first take out the voltage source and get its Laplace transform. Okay, and then just replace the capacitor with 1 by Cs. Just take out the voltage and take the Laplace transform, that means V naught by S. Okay, it is just V naught. You can consider it as V naught into ut, because we are talking about t greater than 0. So you can consider it as V naught into ut. So V naught, what is the Laplace transform of ut? That is S. Okay, so sometimes people forget putting this 1 by S. So you shouldn't forget this 1 by S. Okay, now tell me one thing. Can you apply source transformation here? Source transformation. Source. Okay, this page will go blank only. So I can apply like this. Source transformation. So how will you apply source transformation? Let's just assume if you are having a voltage source of V and a resistance R. So what was the transformation? A current source of V by R in the direction from getting out of positive, right? Current source of V by R and in parallel with the resistance R. So this is the transformation, right? So this is what you will do here, right? So this voltage source, this is a voltage source and this is a resistance. So the current source will be V naught S upon the resistance, that means into Cs. So the current source value will be CV naught. CV naught in parallel with the resistance, that is 1 by Cs. Okay, that is 1 by Cs. So that's how you can replace it as well. If I'm telling A, B, this is A, B. And tell me one thing, what will be ICS? This will be ICS, right? This will be ICS, and here as well this will be ICS. What will be VCS? So this complete circle will be VCS. Okay, I think I should need, or I can, what I can do, I can do this. So this complete circle will show VCS, right? And here also this will be VCS. This will be, this is not looking nice actually. Let's just forget about this box. So you can tell me this will be your VCS, right? VCS, and this will be your VCS. So if you write down, if you want to write down the equation from here, what will you write? VCS by 1 upon CS. Yeah, so that is outward current plus that is IC of S, sorry, plus IC of S is equals to CV naught. Did I write it right? Did I write it correctly? ICS is equals to CSV of S. So IC of S will be in this direction. Let me check it. Yeah, okay. So actually I made the direction wrong, right? This direction is wrong actually, right? Because here what I have seen, that current is getting into the capacitor. VCT is plus 2 minus, the current is getting into the capacitor, right? So the current should get into the capacitor, not flow out of the capacitor. So this will be IC of S, right? This will be your IC of S, right? So from here, what do you understand? VC of S into CS is equals to IC of S minus CV naught. Just as applying simple KCL KVL. So IC of S is equals to VC of S CS plus CV naught. This is the final answer, right? Like this is the final expression. From here as well you can see the expression. So in conclusion, you just need to know how to replace the capacitor with its equivalent in the Laplace transform. Just get the voltage and replace it with the battery of V naught by S and replace the capacitor with 1 by CS. Okay, here also you can write down the equation actually. So your Vc of S is equals to V naught S plus current into this resistance, and that is Ic of S by Sc. So this is what we were getting here. Vc of S is equals to Ic of S by Sc plus V naught S, and this is what we are getting here, right? So in conclusion, you just need to know how to replace voltage V naught by S, capacitance 1 by Cs. Also, what do you know? What is the resistance provided by the capacitance? That is 1 by j omega c. This is the impedance that is provided by the capacitance, right? Impedance provided by the capacitance, that is 1 by j omega c. Just replace j omega with S, that is 1 by c. Now think about inductor. What is the resistance provided by the inductor? That is j omega L. Just replace j omega with S, so it would be Ls, right? So this is the summary you need to remember. This is the important form. Okay, this is the voltage one is an important form. Okay, now talking about the inductor. Okay, so the current that is coming here is IL into T. Let's just write down the expression. VLT is initially no current is there. Like in the capacitor, what did we saw? Initial no voltage. So here what we are seeing, initial no current. So it will be L into DILT into dt. DILT by dt. Okay. So VLT L S ILT, sorry, not ILT, S IL of S minus the initial. Actually, here in the time domain, if I am writing, no, I should have written it in the, not in the capital letter, in the small letter I should write. Why you are understanding my point? No, because if I am writing Laplace transform in capital letter, then I should write this one in the small letters actually, because Laplace transform is written in the capital letter. So I should write in the small letter. So the Laplace transform will be capital capital IL of S into minus IL of 0. So this value will go down to 0 only. So basically you, and this is not VLT. What I am doing, man? This is the Laplace transform I am taking. So VL of S is equals to LS IL of S. So from here VL of S by IL of S, that is equals to Z of S, that is equals to Ls. Okay. So this is the impedance provided by the inductor in Laplace domain. In Laplace domain. So basically, if there is an inductor between A and B, right? So how will you replace it in impedance in Laplace domain? Impedance in Laplace domain. So this L will be replaced with Ls, right? Now if inductor is having some initial current, so what will happen? So similarly we will solve. So this line I am writing VL of S. Okay. So VL of S is equals to S, not S, sorry, it will be L into L di by dt it is. So L di by dt it is. So S IL of S minus IL value at t equals to 0, right? I should have written small IL of t, right? So VL of S is L S I of S minus, what is the value? That is I naught. So it is having initial current I naught, right? So VL of S is L S I of s, IL of s, so y ls IL of s minus Li naught, right? So this is the first expression we get. Also we can, this is one expression, also we can replace it with IL of s, that is VL of s upon Ls plus I naught by s. Two expression we get here. This is the first one and this is the second one. Okay, so by that we can write down our final model. So basically this is the condition A, B, this is an inductor which is having an initial current of I naught. This we are calling, no, this we are calling ILT and this we are calling VLT. So if we want to replace this model, okay, so how will we replace it? So tell me what is the answer? VL of s is L of s into IL of s. That means the impedance provided is L of s. And what is the voltage value? Li naught, right? So the impedance provided is Ls and the voltage value is minus Li naught. Are you getting this point or not? Are you getting this point or not? So how will you write? Inductor is there, I will replace it with Ls. Now if it is having initial current of I naught, so what I will do, first I will see the direction. The direction of what? This one, not this. Direction of this current. The direction of this current is from up to down, right? So I will make a voltage source from up to down minus to plus. If it is going like this, I am not going to make like this. I will make like this. Okay, this is wrong, this is right. Okay, from up to down minus to plus Li naught. Okay, okay. Also it is not Li naught by s. Okay, this is also wrong. Many times I have seen people doing this mistake. Okay, it is not Li naught by s. Okay, now what do you understand by this? If it is Li naught, what do you understand? This is not a step voltage, this is an impulsive voltage in time domain. Here this is Laplace domain. In Laplace domain, if 1 is written, what do you understand in time domain? It is delta t. If 1 by s was written, that means it was ut. So in Laplace domain, Li naught is written. So in time domain, what do you understand? Li naught into dt. So this is the impulse voltage source. Okay, so you shouldn't make Li naught by s. Okay, you should write Li naught only. Okay, so here also we have understood, we have derived, it is Li naught only, not Li naught by s. Okay, so your VL of s is equals to Ls IL into s minus Li naught, and from here as well you can get it, right? So what is your VL of s? This is your VL of s, right? This is your VL of s and this is your IL of s. So this is just an impedance. So VL of s is equals to IL of s into Ls minus Li naught, right? From here you can see VL of s is equals to IL of s minus Li naught, right? So this is your VL of s. Now there is one more way of writing it. What is that? So initially it is having a current of I naught, right? So, and the direction is from down to up. Sorry, from up to down. So it is I naught by s. And what is the resistance provided? That is Ls. Or what I can say? I can simply say that I have applied the source transformation. So voltage source to current source. So voltage source to current source. But direction is minus plus. So I will make the current should get like this, get out like this, right? So I will make the current source direction I naught by s from downward. Or you can see the I naught current, I am coming directly from here to here. So what I will see? I naught current is coming down, right? So I naught by s and the resistance is L of s. Okay. And what will be the VL of S? This will be your VL of S. And what will be your IL of S? That will be this value, IL of S. If you want to write IL of S, what you will write? VL of S by LS plus I naught by S. So this is your VL of S. Okay. So you don't need to mug up anything, right? In the previous analysis, here if we go in this one here if you go, you can see this is a impulse, right? This is an impulse current source, right? This is not a step current source, because in Laplace domain it is looking like CV node. That means it is CV node delta t in time domain, right? So this is an impulse current source. Okay, so from here to here also you can come. So from here to here you can also come, but this is our important point. So mainly we will use this one. Okay, so just take the voltage source out of it, V naught by S, and just replace the capacitance with 1 by Cs. Okay, and in this one as well we will use this one only, mainly in voltage source only, but both are important for this case. You just remember both are important. If you just consider the current source from here to here, if you come okay, from here to here if you are coming, and if we are coming from here to here as well, so from here to this side, okay, if you are coming, so what you will see? I naught S by current source, and the resistance in parallel, that is Ls. Or from here to here if you go, just replace L with Ls and make one battery with the direction current from up to down in the direction of current, battery minus plus. Let me say it once again. In the direction of current minus plus. In the direction of current, battery minus plus. The current is flowing like this, not this current, the initial current, I naught. If the current was initially flowing like this, I naught, I would made in the direction of current, minus plus. In the direction of current minus plus. Okay, in the direction of current minus plus. That's it. I will use this line again and again when we study RL circuits. Okay, so if the current would have been flowing in this direction, I would have made in the direction of current minus plus. If the current is flowing in this direction, I would made in the direction of current minus plus. Are you getting this point? Okay, so this is the Laplace transform. Just make sure that you don't write L naught by S. You only need to write L I naught, sorry. You only need to write Li naught, because this is an impulsive voltage source and this is a step current. Okay, here this is an impulsive current source. Okay, this is an impulsive current source but a step voltage. Okay, so inductor is the friend of voltage, capacitor is the friend of voltage and inductor is the friend of current mainly. Okay, so that's how you can understand. Okay, so now we will solve a simple circuit that we have already seen. This circuit we have already seen. So now we will solve this circuit with Laplace transform. Okay, you need to comment on VCT, VRT and IRT using Laplace transform. Okay, so I will just redraw the circuit. So what will happen? This 5 will become 5 ut, because the switch is closed at t equals to 0. So this will become 5 ut, and this is your R, this is your capacitor C. I will just make it like this. This is ground, this is ground. This is your R, this is C, and this is your IT. This will be your VRT. Let me take here. This is your VRT, and this is your VCT. Now I will make the Laplace circuit. Okay, I will make the Laplace transform now. So what will happen? What is the Laplace transform of 5 into ut? What is the Laplace transform of 5 into ut? That is 5 by S. What is the Laplace transform of resistor? That is R. What is the Laplace transform of capacitor? That is 1 by Cs. Right? Capacitor will be replaced simply with 1 by Cs because it is not having any initial voltage. And VCT will be replaced with VCS. what will happen to VRT? It will be VR of S, and this current is I of S. I will just make a line. So are you getting this point? Every time domain is replaced with the S domain. From time domain to S domain we are going. Okay. Time domain 5 into UT, 5 by S. VR into T, VR into S, VRS. VCT, VCS. IT, IS. Right? And C is replaced with I into I 1 by CS. C is replaced with 1 by CS. So now I will apply KVL. Okay. I will apply KVL. Apply. Okay, it has stopped working. Yeah, so applying the KVL. Okay, so voltage 5 by S is equals to the current into resistance plus the current into the resistance the impedance provided by the capacitor, and that is 1 by CS. So 5 by S is equals to I of S. R plus 1 by CS will be common, so it will be RCS plus 1 by CS. Right? So your I of S would be, here I am again writing this line, 5 by S, I of S is RCS plus 1 upon CS. So your I of S would be 5C by RCS plus 1. Okay. So what you can do, you can write it like this, 5C by RC upon S plus 1 by RC. So your I of S would be 5 by R into 1 upon S plus 1 by RC. So tell me, what will be your IT? IT would be 5 by R e to the power minus T by RC into UT. Right? Okay, wait. This would be your final answer. Why so? Because inverse Laplace, this is inverse Laplace of 1 by S plus A is e to the power minus AT into UT. Right? So this is 1 upon S plus A value is 1 by RC. So A value is 1 by RC. So this is the final answer. And this is what we got when we did it with the time domain analysis. Right? When we did it with the time domain analysis, what did we do? Initially the current is 5 by R, at infinity the current is 0. So 5 by R e to the power minus e to the power minus T by RC into UT. This is what we did, right? E to the power minus T upon tau, and tau value is RC. And if you solve it with Laplace transform, this is what you are getting. Now let's talk about, what should we talk about? VR of S. So secondly we are talking about VR of S. Okay, so what is VR of S? VR of S is R into I of S. So here I think whatever we got the value of I of S, that is equation 1. Now we will just put this value by equation 1. By equation 1, VR of S into, what is the value of I of S? That is 5C upon RCS plus 1. So it would be 5RC upon RCS plus 1. So your VR of S would be 5 upon S plus 1 by RC. So your VR of T would be, small VR of T I should write. Your VR of T would be 5 into e to the power minus T by RC UT. And this is what we got with the time domain analysis. Initially the complete voltage will come across the resistance, and finally the complete voltage will come across the capacitor. So initially VR value is 5 volt and finally it will be 0. So 5 into e to the power minus T upon tau, and tau value is RC. So this is what we did when we were doing the time domain analysis. So same expression we are getting. Now talking about what? Talking about VCS, right? Now we can talk about VCS. what is VCS? VCS is 1 by CS I of S, right? This is your VCS. VCS 1 by CS into I of S. So, impedance into the current, right? 1 by CS, what is the value of the current? That is 5C upon RCS plus 1. That would be 5C upon RCS plus 1. Okay. So, it would become 5 upon S into RCS plus 1. Okay. Now, I will have to break it down in two parts, A upon S plus B upon RCS plus 1. This is a mathematics, right? This is mathematics. You have to break it in two parts, 1 upon S and RCS plus 1, right? Let us assume you are having S upon S plus A. So what you will do? You will break it in two parts, 1 upon S plus A, 1 upon S plus B. Here some coefficient will come, A and B. So this is what I am doing, breaking it into two parts. Okay. So from here, what do you see? A into RCS plus 1 plus B into S, that would be equals to 5. So from here, what do you see? ARC plus B is equals to 0 and A is equals to 5, right? This is what we are seeing here, right? Because S component will be ARC plus B, right? S component will be ARC plus B. Too many mosquitoes, बहुत मच्छर है. So S component will be ARC plus B and constant value will be A only, right? So constant value A is equals to 5 and ARC plus B is equals to 0. So from here, your B is equals to minus 5 RC. So I think I should write in A is equals to 5 and B is equals to minus 5 RC. This is mathematics, okay? You just need to solve the mathematics, nothing else. Okay, so what will be your VCS now? Your VCS would be 5 by S minus 5 RC upon RCS plus 1, or what you can write, 5 by S minus 5 upon S plus 1 by RC, and that is VC of S. Now tell me, what will be your VCT? What is the Laplace inverse Laplace transform of this? 1 by S ut, right? 1 by S ut. And what will be the inverse Laplace transform of this? 5 into e to the power minus t upon RC. Don't forget to put ut. So what will happen? 5 into 1 minus e to the power minus t by RC into ut. That is your VCT. Okay. So this is your final answer, right? So this is what we got when we solved it in the time domain as well. How did we solve it? At t equals to 0, the capacitor will act as short circuit. So your VC would be 0 volt, and at t equals to infinity, it will act as open circuit. So your VC would be 5 volt. So from 0 to 5, it will rise. So infinity value is 5 and 0 value is 0. So 5 into 1 minus e to the power minus t by RC into ut. So this is what we got. Okay. So this is the Laplace domain analysis, but we will prefer using what? Time domain analysis only. That formula we remember, y infinity plus y0 minus y infinity e to the power minus t upon 2 ut. So that is the formula we need to apply. Y of infinity plus y of 0 minus y of infinity e to the power minus t by RC. Okay. And many of the educators solve many of the circuit by Laplace transform, but we will understand those circuit in time domain analysis only. Okay. So from next lecture onwards, we will see those circuits. So whatever the concept that we have already learned, that will be used in those concepts. Okay. The concept that we studied here was these concepts, like replacing the resistance, parallel combination of RC, series combination of RC, right? The concept, this concept, and also the infinite current concept. So all these concepts will be used. Okay. So these concepts are not really taught. This concept is taught of Laplace transform, but to solve the circuit in time domain analysis, that concept is used. So we will solve this circuit in the next video, and we will understand what is how the current is flowing infinite, and if the current is flowing infinitely, so how we should solve the circuit. So everything we will understand, and we will, I will not solve by the Laplace transform, you will solve by the Laplace transform, and you will get to know we are getting the final answer. But if you solve it directly without understanding a concept of infinite current, or without knowing the how to replace parallel RC and series RC, then you can't solve this problem. So many of the educator I have seen, all the educators solve this question using the Laplace transform, but we will solve this question using time domain analysis, and that we will see in the next video. Okay, these kind of circuit in time domain analysis. So every first order circuit will be solved with time domain analysis. You will never have to use any equation, you will never have to use any Laplace transform. Okay, so in the next video we will see that. Okay, so next video will be very important, do watch that video. Okay, thank you. Hello everyone. So in this video we will see the analysis of this circuit. We need to find VC1, VC2, IC1, IC2 and IR. Everything we will find. Okay. So all the concepts that previously that we have studied, all those concepts will be used here. Okay. So just see the circuit carefully. So first thing you will see here is that there are two capacitors. So there are two capacitors. Two capacitors. So people may think it is a second order circuit, right? Second order circuit, because I have told you what is the order of circuit, number of effective storing element. So is this the second order circuit? No, this is the first order circuit. Okay, because I have said effective storing element. Okay, effective storing element. So what will you do? Find effective storing element. Just short circuit the input. If I am short circuiting the input, what will happen? This R will come here. This R and C parallel combination will, one end will go to ground, right? This one end will go to ground, and the other end will be connected to C2. Right? Now what do you see? These two comes in parallel. In parallel. So from here, what do you see? Effective storing element is only one capacitor. Storing element is only one capacitor, right? That is C1 plus C2, because both are in parallel. So what will be your time constant now? C, yeah. So here I will write C effective. So what is C effective? C effective is C1 plus C2. What is R equivalent? From here, what do you see? What is R equivalent? R equivalent is R only, right? So what will be the time constant? Time constant would be C1 plus C2. And from here you understand this is a first order circuit. So in first order circuit there will be only one time constant. If it was second order circuit, there would have been two time constants. Okay, so only one time constant is there, that is R into C1 plus C2. Okay, so first thing we need to find the order. Why we are finding the order? Because the solution that we have seen, y infinity plus y0 minus y infinity e to the power minus t upon tau, that is valid only for first order equation only. So only for first order circuit you can apply that equation. Okay, also the exponential response will be there only for first order circuit only, not for second order. So only for first order it is valid. That's why it is necessary to find the order of the circuit. So first we found the order of the circuit, then we found the time constant. Now we will see what is happening in the circuit. So at t equals to 0, at circuit at t equals to 0. So tell me what is happening at t equals to 0. The capacitor will be shorted because both are having no initial voltage. So both of them will be shorted, and R in series, R in parallel. So R in parallel with some short. So equivalent will be short only, right? Like whatever there is connected, whatever resistance there is connected, and it is shorted. So the complete will be shorted only, right? R parallel with 0. So it will be R into 0 upon R plus 0. So it will be 0 only, right? So it will be shorted only. So what is happening at t equals to 0? That is 5 ut shorted and shorted. This will be shorted and this will be shorted. The complete circuit is shorted. So now tell me, what is the value of current? The value of current is 5 by 0. That means infinite current. And if there is infinite current, voltage, capacitor voltage will change immediately. Capacitor voltage will change immediately. Right? Right? Because of the infinite current. Right? Now, how will you divide the voltage now? Okay, this we are only talking about at t equals to 0, not the complete circuit. Now, how will you divide the voltage at t equals to 0? In the previous question that we took, in this question, we divided in the inverse proportion because only capacitor were there, right? Now, what is happening? Here, we are having capacitor along with the resistor. So, now we can't divide in inverse proportion, right? Because the circuit is having a resistor as well. So, how will we divide? Now, for step input, at t equals to 0, omega is infinity. That means ZC 1 by j omega c, that will be very low. So what does that mean? Your R and C will be replaced with a single capacitor only, right? I have explained this concept in the previous video, right? Because at t goes to 0, very high frequency, because of very high frequency, it is providing very less impedance, and because of very less impedance, this will be replaced with a single capacitor only. So this configuration will be replaced with C1 only, right? So this will be replaced with C1 only, and going ahead, this will be replaced with C2 because there is no parallel anything connected. So this will be only C2. This is acting at t equals to 0 only. At t equals to 0 only. This all is happening at t equals to 0, and here I am having 5 volt at t equals to 0. Okay. And this is your forget about it. This is your circuit, right? This is 5 volt I can write at, because at t equals to 0. So this is your VC1 and this is your VC2. Okay, so although your VC1 for t equals to 0 minus was 0 volt, your VC2 for t equals to 0 minus was 0 volt, but your VC1 for t equals to 0 plus will be what? Tell me. It will be 5 into C1 upon C1 plus C2, and your VC2 at t equals to 0 plus would be 5 into C2 upon C1 plus, sorry, VC1 would be 5 into C2 upon C1 plus C2. And what will be VC2? It would be 5 into C1 upon C1 plus C2, because in case of capacitor, we divide in inverse proportion, right? We divided the voltage in inverse proportion. So this is the value of VC1 at t equals to 0 plus and VC2 at t equals to 0 plus. Because of the infinite current, it is changing its voltage immediately. Okay, and tell me what will happen at t equals to infinity. At t equals to infinity, what will happen at t equals to infinity? The capacitor will act as a open circuit. Capacitor acts as open circuit. Okay. So this is okay. I can write it as 5 because I am just talking about a particular time at t equals to infinity, and this will be open circuited, and this will also be open circuited. Okay, this capacitor is open circuited. This is a resistor R. This would be VC1. This would be VC2. Okay, so tell me what will be the VC1 value at t equals to infinity? Since there will be no current, because this is open circuited, so there will be no current here. So value of VC1 would be 0 volt only, right? The current, this current would be 0 ampere. Here the current would be 0 ampere. So your VC1 would be 0 and Vc2 at infinity would be 5 volt, right? Did you get this point? And here, why didn't we apply that concept at t goes to infinity? We will have omega equals to 0, and what will be the impedance provided by the, why didn't we apply this concept? Because there is no ambiguity, right? At t equals to infinity, if I draw the circuit, it is very simple circuit. I can tell you what is the value of Vc1, what is the value of Vc2, right? At t equals to 0, what was happening? There was ambiguity because it was shorted, and if the complete circuit was shorted, I couldn't tell what will be the value of Vc1 and Vc2. So because there was ambiguity, I had to make the circuit like this so that I can comment on Vc1 and Vc2, right? Because here this is saying 0 voltage and this potential is saying 5 voltage. This is saying here 5 will come, this is saying here 0 will come. So there was ambiguity. So because of that, I had to make the circuit like this. But here in this circuit, this circuit, there is no ambiguity. KCL, KVL, all are fine. Zero current, Vc1 is 0, Vc2 is 5 volt. Everything is fine. So I don't need to apply that concept. You can apply that concept, same answer will come. But I don't need to apply it. Okay. So basically, you know two things here. Vc1 at t equals to 0 plus is 5 C2 upon C1 plus C2, or you can write it 2.5 volt, taking C1 equals to C2. Okay, for simplicity, I am taking C1 equals to C2 equals to C. And what is the value of Vc infinity? That would be Vc1 infinity, that would be 0 volt. Okay, so what do you think? What will be the equation of Vct? Vc1t, that would be 5 C2 upon C1 plus C2 into e to the power minus t upon tau into ut, and that is equals to 2.5 e to the power minus t upon tau ut, right? So this is the final expression. And what is the value of tau? Tau is the time constant, and that is equals to r into c1 plus c2, because c1 c2 both are in parallel, so this is the time constant. So this is the complete analysis for Vc1. Okay, this is for Vc1. Okay, now talking about Vc2. So what was Vc2 at t equals to 0 plus? That was 5 C1 upon C1 plus C2, or we can write 2.5 volt, right? And what will be Vc at infinity? That will be 5 volt. So from 2.5 to 5 it is rising. So how will you write the expression of Vc2t? That will be 5 volt plus value at t equals to 0 minus value at infinity e to the power minus t upon tau. So it would be 5 minus 2.5 e to the power minus t upon tau. So that would be your Vc2t. Okay. Okay. So that would be your Vc2t into ut. Okay. So, and here tau is r into C1 plus C2. Okay, so I guess now you can make the graphs of Vc1 and Vc2. I know there are some things left, IC1, IC2 and IR, that we will see. Okay, so let's make the graph first. Vc1 versus T. So what is happening in case of Vc1? First 2.5 and then going down to 0, right? So we will make the graph like this. Initially it was 0, right? Then suddenly it went up to, because Vc0 minus was 0. Then suddenly it went up to 2.5 and then goes down to 0, right? Then it went up to 2.5, then goes down to 0. So this is 2.5 volt and then it goes down to 0. Right? The time constant is R into C1 plus C2. This is going to be your Vc2 So tell me what is happening in case of VC2. Initially 0, VC0 minus was, VC1 0 minus was 0, then it goes to 2.5, then rises to 5 volt, right? So here it was 0, here it was 0, then rises to 2.5, right? Then rises to 2.5 and then further rises to 5 volt, right? And what is the time constant? That is R into C1 plus C2. So that's the complete analysis for VC1 and VC2. Now you yourself will solve by Laplace transform. Just convert the circuit in Laplace domain. What will you do? This will be replaced with 5 by S. This will be replaced with a single resistor. This will be replaced with 1 upon C1S. This will be replaced with 1 upon C2S. So complete circuit will be replaced and then you need to find the value of VC2 and VC1 using simple mathematics. That's it. Okay. So I will not tell that because Laplace transform is not useful here. Okay. We can solve in time domain only, but for your practice you can solve in Laplace domain as well. Okay. So this is all about VC1 and VC2. Now let's comment on IR. Now tell me what will be IR? IR will be the voltage across the resistor divided by the resistance value. That means VR by R. Now tell me what is VR? VR is VC1 only, right? Voltage across the resistor is equals to VC1 only. No, this VC1 will be going there, right? Do you understand? So what will be your IR? So now commenting on IR, so IR will be simply voltage across resistor divided by resistance R. What is the voltage across resistor? That is VC1 by R. Now just write down the equation of VC1 and just divide it with the R. So our answer would be 2.5 by R e to the power minus t upon tau ut. So that will be the expression of IR, right? That will be the final expression of IR. Right? With tau being R into C1 plus C2, right? So the same graph will be there. For if I need to make the graph of IR, this same graph will be there, right? I am making the graph of IR. Just remove this. So just IR, the value will be 2.5 by R. Okay. So initially there is 2.5 by R current and then this goes down to 0. Okay. Now commenting on IC1 and IC2. IC1 and IC2. Okay. So what will be the expression of IC1? Tell me. So you can see the VC1 waveform, right? VC1 waveform from 0 to some value then decays down. What is IC1? IC1 is the capacitance value into the differentiation of this. Capacitance value into the differentiation of this. Now at t equals to 0, what do you see? From 0 to sudden jump. That means there will be impulse. Then there is graph like this. That means negative slope. So the current value will be negative. Are you getting this point? I am talking about IC1. In IC1, from 0 to sudden jump, that means there will be an impulse. Then what happens? Voltage graph goes like this. That means the slope is negative. That means the current will be negative. So current will go from 0 to from some value to like this. Are you getting this point? Initially the current will be impulsive, then it will decay down to 0. Here you can see in this graph, what do you see? IC. Okay, let's just comment on IC values as well. So this was, sorry, not this. So this was your IC2 and this was your IC1, right? So your IC1 at infinity is equals to IC2 at infinity, that is equals to 0 ampere, right? because this is what steady state is. Because at steady state, the capacitor current will be 0 only, and also in the circuit you can see open circuit, so current is 0. So steady state the current should go to 0, and that will happen here. At steady state the current will go to 0. But the thing is, at t equals to 0 plus, what will be the value? At t equals to 0, what will be the value of current? Impulsive. At t equals to 0, impulsive. What will be the value at t equals to 0 plus? From here, can you make the graph of IC1? Yeah, you can make without the values. Impulsive current will come because there is sudden jump. So impulsive current will come. And then at infinity, it will go down to 0. And also you can see the slope is negative. So the value will be negative. So the graph will go something like this, exponentially decaying from some value to 0. Now what will be the value of this one? That is the task. And now just draw a dummy graph of IC2 as well. Draw a dummy graph of IC2. Just think about it. What will happen? Draw it on rough notebook, then only see it. Okay, then only see the final solution. Draw it in your rough notebook. What will happen? Sudden jump, impulse current. Okay, good, impulse current. Then the slope is positive, VC2, so slope is positive. So the value will be, so voltage value will be positive only. Now where it will be, we don't know. So let's just assume the value is here. So then voltage value will be positive and decay down to finally 0. So this will be the dummy graph, but we need to know the values. Okay, so how will we know the values? So simply by writing the expression. So what will be IC1t? That will be C1 dVC1t by dt. So C1, what is the value of dVC1? That is 2.5 e to the power minus t upon 2 ut. Okay. Now, oh, okay, sorry. Here I need to write d by dt. D by dt. C1 d by dt 2.5 e to the power minus t upon 2 ut. Now, many of the students will differentiate it something like this. What they will do, C1 ut will come ahead. So they will just differentiate this part. So it would be 2.5 by 2 and negative value e to the power minus t upon 2 and ut remains there. Now this is wrong. Okay. Only part that can come outside is 2.5 only. Okay. This is also a time domain function. This is also a time domain function. What I am saying, this is also a time domain function and this is also a time domain function. Both are time domain functions. Time domain functions. Both are time domain function. So you have to apply u into v. So how will you do? 2.5 C1 first as it is e to the power minus t upon 2 as it is. Differentiation of this. What is the differentiation of ut? That is delta t. Then this as it is, differentiation of this. What is the differentiation of this? It would be e to the power minus t upon 2 into ut as it is. Now tell me what will be the value of this? 2.5 C1. What will be the value of this? That would be delta t only. Right? Because I have told you e to the power minus, like anything, any function xt into, okay, I will write it clearly. Xt into delta t can be replaced with x0 delta t. How does that happen? I have already told, right? So xt into delta t is replaced with x of 0 into delta t. I will give you one more quick review. Let's just assume this is your xt. And what is delta t? This is delta t, right? This is delta t. Now you are multiplying both of them. Now what will happen? These values are 0. So all these value will go to 0. Only this value. Let's just assume xt is having a value at t equals to 0. Xt is having a value at t equals to 0. So this will be impulse into a. So this will be your answer, a into delta t. So xt is x of 0 is a. So basically your final answer is x of 0 into delta t. So this is what is happening. X of t into delta t is x of 0 into delta t. So what is x of 0? E to the power minus 0 upon 2. So it will be 1 only. So delta t only there will be. Okay. There will be only delta t minus e to the power minus t upon tau ut. Okay, so let me write it on next page. IC1t. What is the value of tau? That is r into c1 plus c2, right, into ut, into ut. This is the final expression only, no? Yeah. So what do you understand now? Let's make the graph of IC1. In between we will make the graph IC1. So initially we have an impulse of the magnitude is, no, not the magnitude, the area is 2 point like this. The area is 2.5 C1, and here then this is only at t equals to 0. Then we have an step function as well. So we have basically two functions. One is this and the other one is this. It will start from some negative value and eventually at t equals to infinity it will go down to 0. So just add them two. So we will end up with this graph. So it will start from some value that is 2.5 C1 upon R C1 plus C2. Okay. So it will start from 2.5 C1 upon R C1 plus C2 and it will decay down to 0. This is ICT graph. Okay. So are you guys able to understand just the voltage waveform and differentiation? And intuitively, if you need to think just the dummy graph, if you just don't need these values, if you just need a dummy graph, how will you think? You will see this is the voltage waveform. So first impulsive, then negative current, and current going to 0. Impulsive, negative current that is going to 0, right? Because eventually the current is going to 0. Here first in VC, in IC2, what do you see? First impulsive, then positive current that is going to 0. So positive current that is going to 0. Okay. So now we will comment on IC2. Okay. So IC2T now. So what will be IC2T? That would be C2 dVC2 by dt. Okay. So C2 into d by dt into what is VC2? VC2 is 5 into, okay, yeah, there is one error here. This complete function will be into ut, right? So this complete function will be into ut. Okay, this is an error. Okay, like first I wrote 2.5 into e to the power minus t upon tau into ut. So but the complete function into ut. Okay, so it is 5 minus 2.5 e to the power minus t upon tau into ut, right? So what I can do, I can consider this as first function, or instead of that what I will do, I will write d by dt 5 ut minus 2.5 e to the power minus t upon 2 ut. That's how I will write. Okay, I will add more pages. Okay, so that's how I will write. So IC2T, that will be IC2T will be differentiation of this 5 ut, that will be 5 delta t, C2 into 5 delta t. Okay, now I need to apply u into v for this one. right? So minus 2.5 u into v for this one. So first as it is e to the power minus t upon tau, differentiation of second, now differentiation of the second one, and first as it is. I solved it very quickly because we have already solved it. Okay, so it would be 5c2 delta t minus 2.5, inside it will be only delta t minus e to the, okay, instead of that I should write, wait a second, I should write like this, 2.5 c2, this will go to delta t plus 2.5 c2, this 2.5 into c2, and this minus will go to plus e to the power minus t upon tau into tau ut, right? So finally my IC2 t would be 2.5 c2 delta t plus 2.5 c2 upon r c1 plus c2 into e to the power minus t upon tau ut. So if you are differentiating, differentiate with complete concentration, okay, otherwise you will get the wrong answer, okay, because differentiation is different, you can't take ut outside, okay. So u into v you need to apply, okay. So let me make the waveforms. So, waveform for IC2t, okay. IC2t will look something like this. So first an impulse, this shows the area, not the magnitude. 2.5 c2, that is the area, and now an response. So I think I should write it upward. I can write it here, 2.5 c2, and then this value 2.5 c2 upon r c1 plus c2. Okay, forget it, I will write later on this value, and that is decaying down to 0. So this value and that is decaying down to 0, okay. So impulse and then a value that decays down to 0. Okay, and this value is 2.5 c2 upon r c1 plus c2, and this time constant being r into c1 plus c2. So this is the complete analysis of the circuit, okay. First we saw the voltage waveforms. What did we do? Well, first we see that infinite current, that means there will be impulsive current. Because of impulsive current we have to take at t equals to 0, we have to make the circuit like this. So vc 0 plus vc2 0 plus, then we go to know, then we show the circuit at infinity, then we go to know these values, then we go to know the waveform of vc1, then we go to know the waveform of vc2. And because of the vc1, the same current voltage is going across the resistor, so we could write down the value of ir as well. Then we wrote down the value of ir. Then after that we need to comment on IC1 and IC2. Then we go to know IC1 and IC2 will look something like this, because IC1 is C1 into dC1 by dt, and IC2 is C2 into dVC2 by dt, and that's the final waveform we get, okay. One more thing I want to see, if I have in the previous example, in this example, not in this, sorry, not in this example, the very initial example that we took, very initial example, yeah, this one. So did I comment on the value of current? Yeah, I commented on the value of current, yeah, okay. So yeah, I just needed to check if I made this graph or not, so I made this graph, okay. So now let's go to the circuit once again now, okay. So if they were asking what is the value of impulse current, so do you think you need to solve the equation? What will be the value of IC1 at t equals to 0? IC1 at t equals to 0. Do you need to solve this equation? No, you don't need to solve this equation. How? Look, You already know your voltage is going from 0 to 2.5. Your voltage is going from 0 to 2.5. What is the current? Current is IC1 would be C1 into dVC1 by dt. I am only talking about at t equals to 0. Okay. So C1 at t equals to 0, what is happening? The voltage is going from 0 to 2.5. So what will be dVC1? What will be dVC1? 2.5 minus 0, right? By delta t. Time is 0 only. Delta t means impulse. So 2.5 into C1, 0, that will be replaced with delta t. Did you get my point? Look, if you are a gate aspirant and you don't understand these things, it is fine. You can solve by equations as well. But I am trying to tell all these things so that your brain develops. Okay. When you go to analog electronics with all these concepts, the analog electronics will be a cakewalk for you. Okay. Understanding capacitor is very much important for analog electronics. Okay. So we are going very deep into the capacitor. There is no concept. A single concept will not be there that you don't know. Okay. So what I am doing, C1 into dVC1 by dt. So voltage is going from 0 to 2.5. So what will be the value of dVC1? dVC1 shows the change in VC1. So the change in VC1 is 2.5 minus 0. In what time? 0 time. So 2.5 into C1 and this 0 will be replaced with delta t. Like we were writing dq by dt, right? So what we were saying, I am giving I naught amount of flux, I naught amount of charge in 0 time. So what I was writing, I know delta t. So the value of current was I know delta t. So I naught in 0 time. So I was writing I naught into delta t. So here 2.5 into C1 in no time. So the current will be 2.5 into C1 delta t. Are you getting my point or not? You are getting my point, right? So I am giving 2.5 into C1 charge in no time. So my current would be 2.5 into C1 into delta t. Are you getting my point? Okay. And similarly here, similarly the current will be 2.5 C1 into delta t. Okay. Now, what is the value of current at t equals to 0 plus? That is minus 2.5 C1 upon R C1 plus C2. This also you can tell intuitively, but this is out of the scope of GATE students. Okay, there will be much deeper analysis. So I am not putting that video here. Okay, I will make a separate video for placements, guys. Those who are aiming for placements and studying this subject. So for them, I will make a different video. Okay, this value also you can take right intuitively without writing the equations. But this is a very deep concept, so I will just make another video for that. Okay, so those GATE aspirant who needs to see the intuitive analysis of this thing as well, so they can watch that video. Okay, so in the next video only I will put a video there. I will tell the value of IC1 at t equals to 0 plus. That means this value, how we are getting this value. This value intuitively you have understood. Impulsive current, because of that 0 to some value, so impulsive current. So this value you have already understood, IC1. Now this value we will comment in the next video. If you don't even understand this value, equations are there. Very simple concept. By equations we can solve as well. Okay, no hurry. In equation we can simply solve and get to our final answer. Okay, but I just hope that you are also interested in developing your brain. If you are developing your brain, these concepts are very good. Okay, impulsive current, then going like this, then just differentiating and getting through the final answer. Okay, so I hope you understood the concept, and now you need to solve the circuit by Laplace transform on your own. Okay, I'm not going to solve Laplace transform here because the equations will be a lot of equations will be there. Okay, so let's just forget about the Laplace transform. Now let's move on to our next circuit, that is this circuit. Similar circuit to the previous analysis only, very similar. What is happening? This parallel RC combination was there and this was here. So now this capacitor is going here, this parallel combination coming here. Okay, so I guess you should solve the circuit on your own, then only you should watch the final solution. Okay, let's solve the circuit on your own. First tell me what is the order of the circuit. Order, what is the order? Second order? Second order? No. Why so? Because let's see the circuit. Short circuit the input. Okay, short circuiting the input. this will be C1, this will be C2, this will be resistance R. So effective will be this, right? So what will be your time constant? Again the time constant is going to be R into C1 plus C2, right? Time constant is R into C1 plus C2. So it is first order, right? Now what is happening at t equals to 0? You can clearly see what is happening at t equals to 0. This capacitor will be shorted, this will be shorted. So there will be an impulsive current. This is 5 volt. This capacitor is shorted, this capacitor is shorted, right? There will be an impulsive current, right? Infinite current. So capacitor will change its capacitor voltage will change immediately. Will change immediately, right? So how will it change? At t equals to 0, this C1 will be C1, this will be replaced, the parallel combination of R into C2 will be replaced with C2 only, right? At t equals to 0, frequency content is infinity. So what will be the circuit at t equals to 0? This 5 volt is there. This C1 comes here and this C2 remains as it is, right? This is VC1, this is VC2, right? So what will be the value of VC1 at t equals to 0 plus? A similar analysis, nothing different. This parallel combination of RC2 is replaced with the single capacitor. So what will be the value of VC1? That will be 5C2 upon C1 plus C2 into U, not UT. Here I will not write UT. Did I write UT there in the previous analysis? I hope I didn't write UT. Yeah, I didn't write UT because we are talking about a particular time at t equals to 0 only. So why should we write UT? We can write U of 0, that is 1 only. So just forget it. So VC2 at t equals to 0 plus, that would be 5 into C1 upon C1 plus C2. Right? So this will be the value of VC1 0 plus and VC2 0 plus. We will later on talk about the current. Okay. So, and what will be the circuit at t equals to infinity? Circuit at t equals to infinity. That will be this voltage 5 volt. Okay. This this capacitor will also be shorted. Sorry, open circuited, not shorted. This capacitor will also be open circuited, but the resistance will be there. This resistance will be there, right? This is your IR, this is your IC1, this is your IC2. All the currents are 0, right? IR at t equals to infinity, because this is open circuited, so no current is actually flowing. So IR, IC1 at t equals to infinity and IC2 at t equals to infinity. All the currents are 0 ampere. Okay. Now talk about VC1 and VC2. So no one will see the answer, everyone will write first. Okay. So tell me, what is the value of VC1 at t equals to infinity? Is it 5 volt or 0 volt? It's 5 volt, right? Because here we have 0, here we have 0, here we have 5, and no current here, so this will be 0. So 5 minus 0, that means 5 volt. Okay. So VC1 at t equals to infinity is 5 volt. What is the value of VC2 at t equals to infinity? No current in this side, so VC2 at t equals to infinity is 0. Basically no current is flowing, so the same current, that is the same voltage that is there across this resistance R, the same voltage will be there Vc2. So if current is 0, so Vc2 is 0. And here 0 voltage, here 5 voltage. So Vc1 is 5 volt. Understood? Simple concept. 0 voltage, 5 volt. So Vc1 is 5 volt and Vc2 infinity is 0 volt. Okay. So now you can comment on Vc1 and Vc2, right? So for Vc1 at t equals to 0 plus is 5 into C2 upon C1 plus C2. 2.5 volt I can write, considering what? C1 equals to C2 equals to C, and Vc infinity is 5 volt itself. So what will be your, sorry, Vc1? So what will be your Vc1t? That will be 5 minus 2.5 e to the power minus t upon tau ut. Okay. So that expression only I used. I just wrote down the equation directly. Okay. Okay. And what about Vc2? Vc2 at t equals to 0 plus was 5 C1 upon C1 plus C2, that means 2.5 volt, and Vc2 infinity was, what was Vc2 infinity? That was 0 volt. So what will be the value of Vc2t? From 2.5 to it goes down to 0, t upon tau ut. From 2.5 to it goes down to 0. Okay. So this is Vc1 and Vc2. So let's make the graph of Vc1. Okay, from 0 to it goes to 2.5. From 0 to it goes to 2.5, then it goes to 5 volt. 0 to it goes to 2.5, then it goes to 5 volt. Okay. What is the time constant? Similar time constant R into C1 plus C2. Now what is the graph of Vc2? What will be the graph? From first 0, from 0 to it will go to 2.5, then it will decay down to 0 volt, right? From 0 to 2.5 it will go, and then will decay down to 0 volt. What is the time constant? Time constant is R into C1 plus C2. Are you getting this point or not? Okay, so this is Vc1 and Vc2. Now, do I again need to derive the IC1 and IC2? Because what is happening? Are you getting this point? In the previous analysis, what was Vc2 that is becoming Vc1, and what was Vc1 that is becoming Vc2, right? In the previous analysis, if you see, this was your Vc1, this was your Vc2, and we simply differentiated it to find the value of, values of IC1 and IC2. Let's talk about IR now. By the way, we can talk about IR now. What is IR? What is IR? IR is simply Vc2 by R, right? Vc2 by R. This is IR, Vc2 by R. So what is Vc2? 2.5 e to the power minus t upon tau. That is 2.5 by R e to the power minus t upon tau ut. This is your IR, right? I can simply copy this graph, paste it here, right? What will change? Just this is IR and this value will change. This is IR and this value will be 2.5 by R. Okay. Now what we need to comment on? We need to comment on IC1 and IC2. Now again I am not going to differentiate, right? Because we have already differentiated it. So IC1 would be C1 dVC1 by dt, right? So differentiation of this, what is the differentiation of this? It will be similar to what we get as this value. This will be your IC1 actually, right? So this complete value will be your IC1, right? So in the next page, I think I can write. So IC1 is C1 dVC1 by dt. Okay. So this will be your complete IC1. You can again differentiate because previously I have already differentiated. So I'm not going to differentiate it again, right? So this will be your IC1. And here it will not be C2, it will be C1, right? Wait, it will be C2 only. Wait. So what will be that value? So VC, we are talking about IC1. So 2.5 C1 into delta T. So that would be 2.5 C1 into delta T. Goes from 0 to 2.5, but for capacitor C1. So here it would be C1 only. Okay, here would be C1. And what about this? This value, we would be differentiating which function? We would be differentiating this function, right? We would be differentiating this function. So we will be writing C1 into dV1 by dt. So here C1 will come. This will be C1, right? So here C1 will come, right? We are talking about IC1. Let me recheck. Yeah, it's correct only. So nothing, just the differentiation. Just get this VC1 value, this VC1 value, and differentiate it. You will get this expression only. Okay. And now what will be the value of IC2t? IC2, that would be C2 into dVC2t by dt. So what will be the value of IC2t? That will be what expression? IC1 was this. This will be this expression. I think we should box it as well. Okay. Now I will just copy this. So this is the expression of IC1t, but we have to just replace C1 with C2 because we are writing IC2t. 2.5 C2 and C2. So this is the expression of IC1 and IC2t. Okay, and we can copy the graphs as well. Why we should waste time? We can copy the graphs as well. Okay, I will just copy the graph. This is actually the graph of IC2t, right? This is the graph of IC2t. Firstly, an impulse. Firstly, an impulse of 2.5 C2. This is C2 and then decaying down to 0. This is the graph of IC2T. And then this graph is of IC1T, right? Just the scenarios are changed, nothing else has changed. Okay, this is the graph of IC2T. Just this will be replaced with C1, this will be replaced with C1, and this will also be replaced with C1, right? This will be 1, this will be 1, this will be 1. This is the graph of IC1T, this is the graph of IC2T. Just simple differentiation, the same analysis that we did before, but here I am not differentiating again because we have already seen it. Okay, so what is actually happening? The voltage waveform we are already having, then we are simply differentiating. In case of IC1, first an impulse, then positive slope, so positive current. So impulse and then positive current, and then impulse and negative current in case of IC2, because here the voltage is getting decreased, so negative current is there. That means the current will be negative. Okay. So one interesting thing you can see here is that the capacitor which is connected in parallel to the resistor, that is going down to 0. The capacitor which is connected in parallel to the resistor, voltage across that is going down to 0. In case of this, VC2 is going down to 0. It is going down to 0 and it is going down to going up to 5. And in this case, C1 capacitor was connected in parallel to resistance R. So in this case, what was going down to 0? C1 was. So basically the resistance R is discharging the capacitor, and then this capacitor is getting charged. So this is what is happening in the circuit. Okay, do you understand this point? Do you understand? Okay, so this is the complete analysis of the circuit, everything that is required to know. Okay, so these two circuits we have seen. Now we can see one more circuit in the similar way. Okay, so I will just draw that circuit and then we will see the analysis. Okay. Okay, so let's see the circuit. R1C1 or R2C2, both parallel combination now. Okay, and now you need to comment on all the parameters like IR1, IC1, IC2, IR2, VC1, VC2. Okay, for these three cases, R1C1 greater than R2C2, R1C1 less than R2C2, R1C1 equals to, okay, R2C2. It should be R2C2. R2C2. So you need to comment for all the parameters. Okay. So first let's just forget about the conditions. First let's just tell me what is the order of the circuit. What is the order and what is the time constant? Okay. Short circuit the input. Short circuiting the input. R1C1 parallel combination of R1C1. One end will be connected to the ground and the other end will be connected to the parallel combination of R2C2. R1, C1, R2, C2. Right? So tell me what will be the R equivalent? Sorry, not C effective. What is C effective? This C1 and this C2 both are in parallel, right? So C effective is C1 plus C2. And what is R equivalent? C1, C2 will become 1. So R equivalent will be R1 parallel with R2. R1 parallel with R2. So I can write R1 R2 upon R1 plus R2. Did you understand it? This is your R1. This is your R2. And C1, C2 will become 1 only. right? This is C1 plus C2. This is R1, this is R2. So from here you are checking R equivalent. Okay. So what is your tau now? Time constant. That is R1 R2 upon R1 plus R2 into C1 plus C2. So this is the time constant, and it is first order circuit only, right? Because C effective is only one capacitor, so it is first order circuit only. Now we can make exponential graphs. Okay. So first see what is happening at t equals to. Oh no. Wait. I guess I put it on the wrong page. Okay, wait. Okay. So now let's talk about the circuit at t equals to 0. At t equals to 0. So what will be the circuit at t equals to 0? 5 ut. What will happen at t equals to 0? Both will be shorted. C1 C2 will be shorted. So complete circuit will be shorted. The complete circuit will be shorted. So what will be the value of current? Current will be 5 by 0. That means infinity. That means capacitor voltage will change immediately. And how will the circuit be replaced at t equals to 0? Simply by the capacitance values, right? So at t equals to 0, it will be replaced with the capacitance values. So this will be replaced with C1 and this will be replaced with C2, right? So you can write down the values of Vc1 and Vc2 at t equals to 0. Vc1 at t equals to 0 plus would be 5 C2 upon C1 plus C2, and Vc2 at t equals to 0 plus would be 5 C1 upon C1 plus C2. Okay. I think I should keep it in the box. Okay, the currents will be impulsive. And yeah, one more thing, what will be the value of IR1 at equals to 0 plus? Because resistance is a very high impedance with respect to the capacitance at t equals to 0. At t equals to 0, at t equals to 0, omega equals to infinity. That means capacitor is providing very low impedance, right? Or let's just forget it. Okay, just forget this point. We can write down the value of IR1 and IR2 in different manner as well. Okay, so no need to push it. We can write down the values of IR1 and IR2 in different manner. Okay, so this is Vc1 at t equals to 0 plus and Vc2 at t equals to 0 plus. Okay, and current we will later on write. Okay, now let's talk about at t equals to infinity. So what will happen at t equals to infinity? The capacitors will be open circuited, right? So let me make the circuit. At t equals to infinity, the capacitors will be open circuited. This is R1, this is R2. Basically this is Vc1, this is Vc2. So tell me, is there any ambiguity in the circuit at t equals to infinity? Is there ambiguity? No ambiguity. It's very simple circuit, simple resistor divider that is there. Okay, so Vc1 at t equals to infinity is simply resistor divider. 5 into R1 upon R1 plus R2, and Vc2 at t equals to infinity is 5 into R2 upon R1 plus R2, right? So these are the values, Vc at t equals to 0 plus and Vc at t equals to infinity. Now you can write down the equation on your own, right? You can write down the equation on your own, right? Now what I will do, I will just do one thing. This is my Vc1 and this is Vc2. I can write down, I can write this down, write this down as 5 upon R2 upon R1 plus R2 R1, 5 upon 1 plus R2 by R1, right? I am just getting this R1 downward. So 5 upon 1 plus R2 by R1, and for this what I can write, 5 upon 1 plus R1 by R2, right? Just divide R2 in numerator and denominator. In numerator, if I divide R2, 5. If denominator I divide R1 plus R1 by R2 plus 1. So this is what I have written. So, and similarly here what I can write, 5 into 1 plus C2 by C1, and here 5 upon 1 plus, sorry, 1 plus C1 by C2. This would be 5 upon 1 plus C1 by C2, and this would be 5 upon C2 by C1, right? So now considering case 1 where R1 C1 is greater than R2 C2, or what you can write, R1 by R2, sorry, greater, R1 by R2 is greater than C2 by C1. So what is the value at Vc1 at t equals to 0 plus, that is 5 upon 1 plus Vc1 is C1 by C2, 1 plus C1 by C2, and what is Vc infinity, that is 5 upon 1 plus R2 by R1. Now see one thing, or what you can write, R2 by R1 is less than C1 by C2. So which is larger? C1 by C2 is larger. That means this value is larger. That means this value is low. So Vc1 0 plus is lower than Vc infinity. So Vc infinity is the larger value. Are you getting this point? Did you understand this point or not? Which one is the larger value? R1 C1 greater than R2 C2, it is given. So from there you can write R2 by R1 is lesser than C1 by C2. So R2 by R1 is lesser than C1 by C2. So C1 by C2 is larger value. So 5 upon 1 plus C1 by C2. So if this is larger, the lower one is larger. That means the overall is low. So this Vc1 0 plus is lower than Vc infinity. So now I am not going to write the time domain equation. You can write it down on your own, right? The equation you can write down, right? Vc infinity plus Vc0 minus Vc infinity e to the power minus t upon tau. Okay, on the next page we will go and we will just write Vct. What will be the expression of Vct? That would be Vc infinity plus Vc0 minus Vc0 plus, we can write Vc infinity e to the power minus t upon tau, where tau being R1 R2 upon R1 plus R2 into C1 plus C2. Okay, so you can put these values, this value and this value. You can put these values and you can write down the equation. But I am not going to put the values. What I will do, I will just make the graphs. So I will make the graph of Vc1. Okay, I will make the graph of Vc2. Vc1 and Vc2. Okay, so okay, I did not comment about Vc2. So let's just comment about Vc2 now. So Vc2 at t equals to 0 plus was what? So this was for VC1, and here only I can comment about VC2 only. Here only I will comment about VC2. No need to go to this page. Forget about it. So for first condition, R1 by R2, this condition I am talking about. So VC1 at t equals to 0 plus, not VC1, VC2. VC2 at t equals to 0 plus was 5 upon 1 plus C2 by C1. And what was VC2 at t equals to infinity? That was 5 upon 1 plus R1 by R2. So tell me, which value is larger? Look, R1 by R2 is greater than C2 by C1. This value is greater than, that means overall is lower. So that means VC2 0 plus is greater than VC2 infinity, right? So this is one, and VC2 0 plus was greater than VC2 infinity. Okay, so let's just make the graph. For VC1, 0 value was lower and the final value was higher. So the graph will go something like this. So I guess I need to use a different pen. So first it will start from 0, then suddenly it rises to a value. Suddenly it rises to a value, and then suddenly it rises to a value, of this value, and then it goes up to this value. So rises to a value and then goes up, right? So what is this value? VC0 plus, that is 5 upon 1 plus C1 by C2. This is 5 upon 1 plus C1 by C2. And what is this value? That is 5 upon 1 plus R2 by R1. R2 by R1. We are talking about the case R1 C1 is greater than R2 C2. We are talking about this case, right? And what happens in case of VC2? 0 value is larger. So first it rises. So from here it goes, then it rises to some value, okay, then decays down, right? It rises to some value and then decays down. What was the value? VC2 0 plus was 5 upon 1 plus C2 by C1. And this graph I made wrong. Actually it doesn't decay down to 0, right? It's not decaying down to 0. It's decaying down to some value, some finite value, right? So 5 into, so the value was 5 upon 1 plus C2 by C1. 5 upon 1 plus C2 by C1. Upon 1 plus C2 by C1, and this value 5 upon 1 plus R2 by R1. This value is 5 upon 1 plus R2 by R1. Okay, 1 plus R1 by R2 it is, yeah, R1 by R2. 5 upon R1 by R2 it is 5 upon 1 plus R1 by R2. This is for the first case, right? Now for the second case, you know what will happen. For the second case, when R2C2 is, sorry, R1C1 is greater than R2C2. That means R1 by R2 is greater than C2 by C1, or R1 by R2 is greater than C2 by C1, or R2 by R1 is less than C1 by C2, right? two conditions are there, right? Now, what do you think what will happen? In case of VC1, 0 plus would be lesser than, sorry, would be greater than VC1 infinity, and VC2, 0 plus would be less than VC2 infinity. Because values are already there, these values are already there, you just need to check this condition, because R1 greater than R1 by R2 is greater, this value is greater, that means this overall value is lower, that means VC2 infinity is low. Arey bhai, R1 by, okay, wait, R1 by R2 is lesser, this is lesser, yeah, so R1 by R2 is less, R1 by R2 is less, that means this overall value will be larger, so VC2 infinity will be larger. Now talking about VC1 infinity, R2 by R1 is high, R2 by R1 is high, so this overall value will be low, so VC1 is low, so VC1 is low. Array yaar, VC1 infinity is low, yeah, VC1 infinity is low. Just putting down the values, nothing else. Okay, just put down the values that is there, and from there you will get the waveform. So now the waveforms will be something like this. This will be our VC1, this will be our VC2. Okay, so in case of VC1, what will happen? 0, then some value rises to some value, and then decays down to some another value. Decays down to some another value. Okay, so initially what was the voltage? VC1 0 plus was 5C2 upon C1 plus C2. It was 5C2 upon C1 plus C2. What was the value? 5C2 upon C1 plus C2, and then it was VC1 infinity was 5R1 upon R1 plus R2. It was 5R1 upon R1 plus R2, right? And what will happen in case of VC2? Initially 0, then goes up to some value, then to some other value it go, right? Right, this VC2 0 plus was, what was the value at VC2 0 plus? VC2 5C1 upon C1 plus C2. What is the value at infinity? That is 5 R2 upon R1 plus R2, right? Are you getting this point? So we have commented about, and what is the time constant? That we already know, time constant we already know. Okay, so now we have commented about VC1 and VC2 for two cases. Now there is this third case. In case of third, R1 C1 is equals to R2 C2, right? So from here what you can see, R1 by R2 is equals to C2 by C1, and R2 by R1 is equals to C1 by C2, right? Both are equal. So what do you see here? Here you will see that VC1 at 0 plus is equals to VC1 at infinity, and VC2 at 0 plus is equals to VC2 at infinity. So all values are equal. So actually what is happening? this is your circuit. I will just draw the circuit. So this is your circuit, right? So what is happening here is that the values are getting stabilized very quickly, right? So this is your, this I am talking about VC1, and this I am talking about VC2. So if you draw the graph, what do you see? Whatever the value is there initially, so initial it's 0, then initially some value, the same value we will be having at infinity. This is the 0 at infinity, same value, so straight line. It happens only in first order circuit. Okay, 0 infinity, same value, so straight line. Right? Also by equation you can also see, what would you write? V infinity plus V0 minus V infinity e to the power minus t upon tau and ut for whole ut. Now these two are same, so this will go down to 0. So only V infinity ut is left, and that is equals to V0. So same values are there, right? So same value is there. Okay, and the value is, for this it is 5 C2 upon C1 plus C2 equals to 5 R1 upon R1 plus R2, and for this it is 5 C1 upon C1 plus C2 equals to 5 R2 upon R1 plus R2. Now one interesting question I want to ask, what is the time constant of for this case? For these two cases we know the time constant, that is R1 parallel with R2 into C1 plus C2. What is the time constant for these two cases? Everyone should answer, everyone should write it in your rough notebook, then I will tell the final answer. So what is the time constant? The time constant is 0, right? Time constant is 0. Why so? Because it is getting stabilized immediately. From 0 to the value stabilized. So here only we are getting the final value, right? In this circuit, in some circuit here, where has it gone? This one. Here we saw that the time constant was 0. Here as well the time constant was 0 because there was no resistor involved. So time constant was 0 because it was getting stabilized immediately. So it is taking no time to stabilize. So time constant here was 0. So in the similar manner, here as well the time constant is 0. Okay. So time constant is 0 here. Okay. And in this case, IC1 and IC2 would be simply an impulse, right? So you can make the graph and everything. Okay. So now talking about IC1 and IC2. IC1 and IC2. No need to write the values, we will just make the graphs. Okay. So what will be IC1? That would be C1 dVC1 by dt. And what would be IC2? That would be C2 dVC2 by dt. Okay, all the currents we will talk about, not just IC1 and IC2. We will talk about IC1, IC2, IR1 and IR2. All the currents we will talk about. Okay. And what about IR1? What will be IR1? IR1 will be VC1 by R1. What about IR2? IR2 would be VC2 by R2. Right? Okay. Now for the first case, we will not write down the values. Okay, you can differentiate and write down the values. For the first case, R1 C1 greater than R2 C2. Okay, so I will draw the graph of IC1, then I will draw the graph of IC2, I will draw the graph of IR1, and I will draw the graph of IR2. All four graphs I will draw. Okay. Values we will not find. Okay. So first I am drawing the graph of IC1. So for the first case, R1 C1 greater than R2 C2. So this is the graph of VC1. So what is happening? The voltage VC1 is rising. That means slope is positive. So current will always going to be the positive one. Okay. So first we will have an impulse because of the infinite current. First we will have an impulse. First we will have an impulse. Okay. What will be the magnitude of the impulse? The change in the voltage. Change in the voltage from 0 to some value, that is 5 C2 into upon C1 plus C2 into change in voltage into the capacitance value, that is C1. So it would be 5 C1 C2 upon C1 plus C2 delta T. What was the change in voltage? From 0 to 5 C1 plus C2. Now what is the current? That is C1 d Vc1 by dt. So this was the change into C1 delta T. That would be the current. So this is what I have written. Right? This is the current. Then the slope is positive. So it will decay down from this value to 0. Okay. From here to 0. Now let's comment on IC2. First we will have an impulse, right? The same impulse we will be having. The same impulse we will be having, this much impulse. So that will be 5 C1 C2 upon C1 plus C2. The same impulse we will be having, right? Because of the sudden change, we will be having an impulse. The value will be same because the change in VC2 is 5 C1 upon C1 plus C2. So what will be the current? C2 into d Vc2 by dt. So this change is this into the capacitance delta T. So it will be 5 C1 C2 upon C1 plus C2, right? 5 C1 C2 upon C1 plus C2. Now here what do you see? In first case the slope is negative. The slope is negative, right? So it will start from here and will decay down to 0, right? Right? Now the thing is, you don't know this value. You don't know this value. This you can find only by differentiating it. Okay? This value you can find only by differentiating it. Okay? No one will ask you this value in the gate exam or in the written exam. And if they ask you, then you can derive it. But in the interview they may ask you. So for that I will make a separate video. That's out of the scope of gate aspirants. But if you want to know, even if you are a gate aspirant, and if you want to know how do we find intuitively this value, then you can watch that lecture. Okay, the lecture that I will make later on. Okay, so intuitively as well you can tell this video, tell this value, but that is out of the scope of gate aspirant, so I am not telling. Okay, that will be much deeper concept, we will see that. Okay, but the whatever that I am telling, that is helpful for your written test and for gate exam. Okay, but for interview, intuitively you need to tell, so that we will see. So now IC1 IC2, now talking about IR1, and then we will talk about IR2. Okay, so talking about IR1, what will be IR1? It will be simply VC1 by R1 and VC2 by R1. So whatever this voltage is divided by R1, that would be VC1. Okay, not this one, this one. and whatever this voltage is divided by R2, that would be Vc2. So do I need to make it? I don't think I need to make it. Okay, I will make it because it won't look good. If I don't make it, it won't look good. Okay, so IC1 is actually rising like this. Oh, no, not IR2 doesn't go like this. IR2 goes like this. Not to 0, but to some particular value. Right? These values you can write on your own, right? Just the value of Vc1 by R1, that would be this value, and these values you can write. Okay, now let's take the second case, that is R1 C1 is less than R2 C2. Okay, so make the graph for them. So I will just pause it and make the graph, because you already know how will the graph look like. Let's just talk about, okay, let's just talk about IC1 and IC2 first. Okay, no need to pause it. Let's just talk about IC1 and IC2. IC1 T, IC2 T. Okay, so let's talk about IC1. For the second case, first it rises, impulse will be there. What will be the amount of impulse? C1 into the voltage change, right? The amount of impulse will be C1 into voltage change. What is the voltage change? That is 5C2 upon C1 plus C2. Voltage change is 5C2 upon C1 plus C2 into C1. So it would be 5C1 upon C1 plus C2. Then voltage decays down. That means current will be negative. So it will start from some negative value and keep on decaying down. Okay. And you can make it like this. Like how? Like this. Initially it was 0. Initially it was 0. Then it goes to some value and decays down like this. Then here initially it was 0. Arey yaar. Initially it was 0. Then an impulse will be there. What will be the amount of impulse? The change in voltage. What was the change in voltage? The change in voltage. The change in voltage was 5 into sorry, here C1 C2. So what was the change in voltage? Change in voltage was 5 into C1 upon C1 plus C2. It was 5 into C1 upon C1 plus C2 into the capacitance value, that is C2. Okay, then from some value it goes, and since the voltage is getting up, that means if voltage is getting up, that means what is happening? Voltage is getting up, that means the current is positive, but current is positive and decays down to 0. Current positive, that decays down to 0. At steady state, the capacitor current will always be 0. I can't comment about the resistance current. Resistor current I can't comment, but capacitor current will always be 0 at steady state, right? We don't know about the resistor current, but capacitor current will always be 0 at steady state. Okay. So this is the second IC1 and IC2. Then you can draw the graphs of these IR1 and IR2. So these will be similar only, actually. Just the graphs will be interchanged. This will be the graph of IR2, right? And this will be the graph of IR1. And this will be the graph of IR2. Okay. Now for the third case, R1 C1 equals to R2 C2. So tell me, what will be your IC1 for the third case? What will be your IC1 for the third case? And what will be your IC2, IC1 and IC2? Only an impulse will be there, right? This is the third case. Only an impulse will be there because differentiation of this will be 0 only. This is a step function, right? Vc1 is a step. Vc1 is a step. What is the differentiation of step? That will be impulse. Or you can see at t equals to 0 we have a sudden jump, then we have constant. So if Vc is constant, that means current will be 0. So only an impulse current will be there, and that has the magnitude of 5c1 upon c1 plus c2. 5c1 c2 upon c1 plus c2. 5c1 c2 upon c1 plus c2. Five c1 c2 upon c1 plus c2, and here as well 5 c1 c2 upon c1 plus c2. Okay, and for making the graph of IR1 and IR2, simply these values will be there, simply these graph will be there, nothing different, because just we have to divide the values by R, right? I hope I am able to copy it. Yes. IR1 and IR2. So what is the value of IR1? Simply the voltage. What was the voltage? That was 5. What was VR1? Sorry, VC1. What was VC1? That was 5C2 upon C1 plus C2 by R1, right? And what is the value of IR2? That would be 5C1 upon C1 plus C2 by R2. So these are the graphs. Okay. Okay. So these are the final graphs. Are you getting this point? You can write down the values because it will be very big values. So I am not writing down the values. I am just making the graphs. So main target here would be the graphs. Okay. So I hope you have understood all the concept that I am trying to give. Now there will be more concepts. Okay. So we will see them one by one. Okay. Just keep on watching the videos. You are understanding everything. Just write it something in your rough, whatever I am doing, and then you are having a brilliant clear notes and everything. Okay. So if you like the videos, please do share it with your friends. So later on we will see more circuits and more analysis. Then we will see a lot of examples and everything will be clear to you. Okay. So let's meet in the next video. Okay. Thank you. Hello everyone. So now we will study RC circuit with the current input. Okay. Previously we were applying voltage source. Now we will apply the current. So this is the circuit. The switch is closed at t equals to 0. So how you can make the circuit? Basically, you can replace the circuit with the current source, a resistance R, capacitance C, VR and VC. The current source is 5 UT, right? Because it is closed at t equals to 0. So this is given at 40 greater than 0 only. So this is 5 UT. So tell me, what will be the value of VRT? VRT will simply be the current, how should I, let's just call this current as IT. Okay, so VRT will simply be IT into R. It would be 5R UT. Very simple graph, right? What will be VRT? VRT is simply the current. Current will always flow 5 ampere. Through the resistor, 5 ampere current will flow, right? Always 5 ampere current will flow. So, simply the graph will be initially 0, then rises to 5R. So 5R, this is the graph of VRT, right? This is the graph of VRT. Why it is not exponential? Why is it not exponential? First thing is that this is not a first order equation, right? There is no differential equation. The second thing, the current is always same. When we were studying this RC circuit, with the voltage input, what was happening? Initially, the current was 5 by R. Then it was gaining some voltage, let's assume 0.1. The current was getting reduced to 4.9 by R. Then it was getting reduced to 4 by R, 3 by R. Every moment the current was changing. Here, there is always the same current, right? Here the current is same always, right? If this is this 5 UT current is always flowing through the resistor and the same current is always flowing through the capacitor. So now talking about VCT. So what will be VCT? Same current 5 UT always flows through the capacitor. Flows through the capacitor. That means your VCT would be 1 by C integration I dot dt. From where to where? From 0 to time t, right? So 1 by C integration 0 to t 5 ut dt. So it would be 5 by C RT, right? Or you can write it is 5 by C, 5t by C into ut, right? What is the integration of step? 5 is the common, integration of step is the ramp, or you can write it RT, you can write TUT. So basically it is this graph only, but not defined for t less than 0, always defined for t greater than 0, right? So what will be your VCT? Okay, there is no space, so I guess I can make the graph of VCT here only. VCT from 0 to 5 by C. So from 0 to it keeps on rising, right? It keeps on rising like this. And what is the slope? Slope is 5 by C, right? Theta. Slope is 5 by C. Okay. So this is the slope. Okay. Now this is the question. The switch is closed at t equals to 0. You have to find VR, VC, IC, IR. Everything we will comment on that. Okay. Same current is there. We have to comment on VR, VC, IC, IR. Everything we will comment on. Just a second. I guess I will have to change the setup. Yeah. So let's make the circuit. Let me pause it and then make. So first what we will do, we will solve by the equations, then we will see what is actually happening in the circuit. So this is the circuit. So let's just comment on VC first. Tell me what is the value of VC at t equals to 0 plus 0 voltage. So it is 0 voltage only. What will be the VC value at t equals to infinity? Tell me what will be the value. This will be open circuited, right? Capacitor voltage will be open circuited. So this complete 5 ampere current would be flowing here. This will be open circuited, so the complete 5 ampere current will be flowing here. So whatever the voltage, VR voltage you are having, the same voltage will be across VC. At infinity, what is happening is that this is 5 ampere current source you are having. This is the resistor you are having. This is the resistor you are having. This is open circuited. This is open circuited. Right? This is the 5 ampere current source. Now the complete current is flowing here. Right? This complete current is flowing in the same current is flowing in the resistor. So what is the drop here? 5R. Now since there is no drop across this resistor because it is open circuited, so there is no drop across the resistor. So same voltage drop will be across VC only. This is 5R. Okay. Along with that, let's comment on IC as well, because you don't really know what is IC. If IC is constant, if IC is always constant, that means the capacitor will linearly charge. But is IC constant here? Is IC constant? Tell me what is the value of IC at t equals to 0 plus. Write it in your rough notebook, then only you need to see the answer. What is the value of IC at t equals to 0 plus? 5 ampere, 2.5 ampere, 0 ampere. 2.5 ampere. Why so? Because what is happening at t equals to 0 plus? This is a 5 ampere current source. In parallel to that, we have a resistance R. Then another resistance R we are having, and the resistance is, and the capacitor is short circuited, right? Capacitor is short circuited. This is resistor R, this is resistor R, this is 5 ampere current source. So here, this current is your IC current. Resistor R, this resistor R is short circuited. So 5 ampere current is divided into two parts. So IC 0 plus is 2.5 ampere. What will be IC infinity? The capacitor will be open circuited, so it will be 0 ampere. So here the current is not constant. This is at t equals to 0 and this is at t equals to infinity. So what do you see here? Initially the current was 2.5 and at steady state it was infinity. The current is not constant. So we can say there will be exponential response. Here in this circuit, what do you see? Initially the current was 5 ampere and always it will be 5 ampere. Because the same current will be flowing here. Always it will be 5 ampere. But in the previous problem, what do you see? Initially it was 2.5 ampere, then it goes down to 0 ampere. Now, one important thing we have forgot here. What is the time constant of the circuit? By the waveform, you can tell the time constant. What is the time constant of the circuit? Look, the time constant will be defined as per the voltage. Okay. If I am considering this is my output voltage. If I am taking my output at resistor, I will connect two pin, okay, and I am taking my output. So this is what I am telling my output. So I am telling my output as at resistor. So what will be my time constant? Here my time constant is 0 second because it is stabilized immediately, and here my time constant is infinite second because it is never getting stabilized. So in a circuit, the time constant depends on the output from where you are taking. Are you getting my point? The output from where you are taking it. Are you getting my point? Let's just assume I am taking my output from here. So what will I see? From here I will see my R equivalent. What is my R equivalent? That is R, or R effective I will say. What is my C effective here? From here I will see. What will happen to current source? Current source will be open circuited. The current source will be open circuited. So this C will be open-ended. Open-ended C means 0. That means 1 by j omega c. Open-ended means infinite impedance. If it is infinite impedance, that means it has to go to 0. Open-ended means infinite impedance. If impedance is infinite, that means capacitor has to go to 0. So if capacitor is 0, that means C effective is 0. So what is your time constant? Time constant is 0. Okay. So the time constant is 0 second. And if you are taking your output from here, okay, from here if you are taking, so what is your C effective? C effective is C. What is your R equivalent? Tell me what is your R equivalent? From here you will see. So the current source is open circuited. If the current source is open circuited, that means you will see infinite impedance, right? Current source is open circuited, that means you will see infinite impedance. So what is your time constant? that is infinite second. Are you getting my point? Also by waveform you can see it is never going to stabilize, so infinite second is time constant. Here in the waveform you can see it is stabilizing very quickly, so time constant is 0 second. Okay, so depending on the output your time constant can change. Here we are taking time constant at the, here we are taking the final output at the capacitor, so the time constant is infinite second. Here we are taking the output at resistance, so time constant is 0 second. So why in the previous analysis we never saw circuits like this? Let's just take an example. We take this circuit. Okay, we never talked about anything. We just said that, like, we never talked about the output. We just said that the time constant of this circuit is RC. Why so? Let's just assume you are taking your output here. What will happen? You will short circuit this. You will short circuit this. What is your R effective? R equivalent, you can say R. And if it is shorted, that means this C will come in parallel. So basically from here you will see C effective, that is C only. So time constant is RC. From here if you see, from output, this is your output. From here what do you see? C effective is C only. What is R equivalent? Since this is shorted, your R equivalent is R only. So time constant is RC. Are you getting my point? Got my point? That's why we never saw where we are collecting the output. Let's take more examples. This was one more circuit that we have studied. Okay. Let's assume I am taking my output from here. So what will you see? Taking my output from here, this will be shorted, right? This will be shorted. So this R and this R will come in parallel, right? And this C will also come. So R equivalent you are seeing R by 2. C effective is C. So what is time constant? RC by 2. From here if you are seeing, if you are collecting your output from here, so what do you see? C effective is C. What is R equivalent? Both will come in parallel. So it would be R by 2. So it would be CR by 2. Are you getting my point? So in case of current source, you can't really say this is the time constant of my circuit. Okay, first you need to define the output. If you are collecting the output, in case of a current source, if you are collecting the output at some point here, so time constant will be different. Here the time constant will be different. So here in this case you see there are two time constants with respect to the output. So always the time constant is defined with respect to the output where you are actually taking the output. Okay, in this circuit we will see the time constant now. Now for VC and VR we are seeing the time constant. Okay, VC and IC and VC. For IC and VC we need to see the time constant. So where is our IC and VC? This is our output, right? What we will do? We will open circuit the current source. Okay. Now we are talking about the time constant. What we will do? We will open circuit the current source. The current source is open circuited. This is R, and this is capacitor C. Right? These two will come in series. So what is my R? This is my output. Here I am taking the output. What is my R equivalent? That is 2R. What is my R equivalent? That is 2R. What is my C effective? That is C. So what is my time constant? That is 2RC. Okay, time constant is 2RC. So VC is rising from 0 to 5R and IC is decaying from 2.5 to 0. Okay, so if we want to write down the equation of VCT, from 0 to 5R it is rising. So 5R e to the, from 0 to 5R it is rising. So 5R 1 minus e to the power minus t upon 2 ut with time constant being 2RC. And what about ICT? What about ICT? Initially the current was 2.5, then it goes down to 0. So from 2.5 to e to the power minus t upon 2 ut with time constant being 2RC. Okay, so now we can make the waveform of these two. It will be exponential because the time constant is a finite value. If it is 0, then mean it is stabilized very quickly. If it is infinity, that means it is linearly charging. If it is some value, that means it will be exponentially charging. So all your concepts are crystal clear, right? In transient, the concept has to be crystal clear. So every subject that needs the crystal clear concept, I will teach you in the similar manner. Okay. So from 0 to 5R we will rise. What about ICT? From 2.5 to 0 it goes. Time constant is 2RC. Time constant is 2RC. Okay, well and good. Yeah. Now we will comment on what? VR and IR. If we simply comment on VR, we can comment on IR as well. So let's make the same circuit again. Okay, I guess we can make it on the next page. Okay, let me copy in the on the next page. So now we are commenting about VR and IR. Both of them we are commenting about. Okay, VR and IR. Okay, so tell me, what will be the IR value at t equals to 0 plus? What will happen? This capacitor will be shorted. This capacitor will be shorted, so the 5 ampere current will be divided into 2 resistors. So it would be 2.5 ampere. Right? What will be the IR value at t equals to infinity? What will be the IR value at t equals to infinity? This capacitor will be open circuited, so the complete current will be flowing through the resistor. So it would be 5 ampere. Similarly, on VR also you can comment at t equals to 0. What will be VR? VR will be 2.5 into R, so it would be 2.5 R. And what will be VR at t equals to infinity? It would be 5 R. Are you getting the point? Very simple. Capacitor is shorted. The current is divided into two parts, R and R. 2.5 ampere, 2.5 ampere. Okay. The capacitor is open circuited. That means the complete current is flowing through the resistor. Okay. We will also see what is really happening in the circuit, but in the later part of the video. Okay. So now we are just making the waveforms and writing down the equation. So what is the equation of IRT? It is going from 2.5 to 5. So it would be 5 minus 2.5 e to the power minus t upon tau with time constant. Tell me the time constant now. Time constant. We have to comment on the time constant. Current source will be open circuited. So simply a resistor, another resistor, another capacitor. So this is where we are collecting the output. Right? What is R equivalent? R and R in series. So what is your R equivalent? 2R. What is your C effective? Only one capacitor, that is C. So what is time constant? 2RC. Right? Same time constant. Exponential response, same time constant. Time constant is 2RC. What about VRT? What about VRT? It would be the same, just R will be there, nothing else. So 5R minus 2.5 R e to the power minus t upon to ut. Of course, ut will be there with time constant being 2RC. So I will just make one waveform. No need to make both of the waveforms VR and IR. I will just make the waveform of IR. Okay. So for IR waveform, first from 2.52 it goes up to 5 volt. Okay. From 2.52 it is going up to 5 volt and with time constant being 2RC. Okay, well and good. So this is the time constant. So this is the complete analysis. Now let's see what is actually happening in the circuit. I am not going to write it. I will just tell in the theory. Okay, you listen it very carefully. If you want to write, you can write it on your own. So what is happening? Also, first you can think on your own. So let's see. Initially the capacitor is shorted. That means 2.5 R current is flowing. Okay, here 2.5 R current is flowing. Okay, let's do it on a rough page so it will be more easier to understand. Okay, I will erase it later on, but let's just see the circuit. Let's just forget everything and just forget this. So what is initially happening? Initially this 2.5 R current is flowing here. Now this 2.5 ampere current is flowing here. Now this 2.5 ampere current charges the capacitor. Let's assume initially it is 0. Let's assume it is charged to some voltage, that is 1 volt. Okay, let's assume it is charged to 1 volt. So now what will happen? Here we have V volt. Okay, initially 2.5 ampere current was coming, right? Now what is happening? This is driving some V by R ampere current, and this is driving some V minus Vc by R, right? Because of this current, this Vc value is getting increased. If this Vc value is getting increased, that means this current is getting reduced. If Vc value is increased, this V is constant. If this Vc value is increased, that means V minus Vc will be reduced. That means the current will be reduced. So slowly the current here is reducing. If the current here is reducing, from here we have 5 ampere current, that is fixed, and here the current is reducing, that means the current is increasing here. So initially it was 2.5 ampere current here, now it is increasing here, and here initially it was 2.5 ampere current, now it is decreasing. So it will keep on decreasing, it will go down to 0 ampere. Decreasing, decreasing and decreasing, it will go down to 0 ampere. And when it will go down to 0 ampere? When the potential here and here are same. If the potential here and here are same, that means the current in this resistance will be 0 ampere. So when the potential will be the same, when the complete current is flowing here, that means here the potential should be 5R, here also the potential should be 5R. So when both of the potential are equal, that means the current here would be 0. So that means we will replace this with open circuit, then we can find the voltage drop across the resistor, that is 5R. Are you getting my point? So voltage across the resistor is 5R. Here also we have 5R. So current is 0. That means all the current is taken by the resistor. Are you getting my point? So this is the actual analysis. Got it? Understood? Now you can solve this circuit by one more method. The same circuit by one more method. This circuit. What is that method called? Source transformation. Okay. I will just copy the circuit. We'll write method 2. Method 2. Okay. What I can do? I can apply the source transformation. First, this will be replaced with this circuit, and from there I can apply the source transformation. So if I apply the source transformation, so what I am doing, I am converting this current source into the voltage source. So this will be converted, this current source will be converted into voltage source. So what will be the value of voltage source? Current into the resistance, that would be 5R ut, and this resistance will come in series, that will be R. Okay. Okay. Now you can find these values as well. Okay. What are the values? This is Vc, this is, forget it, is this Vr? Tell me one thing, is this Vr? Let's call this value as Vr dash, this value is Ir, this is Ic, Ir dash, this as Ic dash, and this as Vc dash. Okay, Vc dash. So I will ask you one question that I have already explained in the network theorem part. Okay, I have explained this in the network theorem part. So I will ask you one question. So tell me, will this Vr dash
and IR dash is same? Is this IR dash and IR is same? Is this IC dash and IC is same? And this VC dash and VC is same? Which are the statements true and which are wrong? You need to tell me. Okay, just solve it in rough and tell me. Is this correct? No. Is this correct? No. Is this correct? Yeah. Is this correct? Yeah. Why so? The component which is getting converted, you can't find the voltage and current there. Applying the source transformation. I wrote it in a note, right? If you remember, this resistance is getting converted, right? So if this is the VR, you can't convert it and tell me this will be the VR. No, 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 no. This won't be IR. No. This will be different because this is getting converted. So whatever that is getting converted, you can't find the voltage and current across that component after applying the source transformation. Okay, just consider if this is a source resistance, so you can't really find the voltage and current in the source resistance because that is getting converted. So this is not same. If you need to find VR and IR, you have to solve this circuit only. You can't find VR and IR from this circuit. Okay, if you need to find VR and IR, you have to solve this circuit only. From here you can find only the two components, that is IC and VC, because they are not getting converted, right? This circuit is remaining as it is. This complete circuit is remaining as it is. R and C, this is remaining as it is, but this part of circuit is getting converted. Are you getting my point? So these two are correct, IC and VC, but VR dash and IR dash is not correct. Okay, so from here if you need to find VC, how will you find? Simply a RC circuit with 2R resistance in series. So this can be replaced just simply an RC circuit with 5R UT voltage. Simply an RC circuit with the voltage, resistance and a capacitance. Resistance value is 2R, capacitance value is C, and the voltage is 5R UT. So simply from 0 to 5R UT it will charge. So VC value will be from 0 to 5R UT, right? This VC value will be from 0 to 5R, from 0 to 5R it will rise. So where is VC? VCT, it is rising from 0 to 5R. What about IC? Initially IC was 5 by 2R, 2.5 by R, right? Initially IC was 2.5 by R, then it goes down to 0. So here also you can see from 2.5 IC value, where is IC? Yeah, here it is. From 2.5 to 0 it goes. Okay. Yeah, from 2.5 R by 2R, that means 2.5 to 0 it goes. So that's how you can solve the circuit as well. Okay. So by simply applying the source transformation, you can solve the circuit as well. So the problem looks simpler now, right? But you can't find VR and IR from source transformation. Can't find VR and IR from source transformation. VR from source transformation, right? So these two circuits we have studied. Now we will study this circuit. Okay. So first here we will comment on IR, IC and V naught. So let me make the circuit. So this is the circuit. Instead of 5 ampere, I should have written 5 UT, right? So before starting this problem, I want to ask you one question. This is a current source of 5 ampere and this is a short circuit path. Okay. Now tell me, what is this value? What is the value of I? Is this 5 ampere, 0 ampere or infinite ampere? Three options are there. You need to choose one. 5 ampere, 0 ampere or infinity ampere? What is your answer? The current is 5 ampere only, right? If there is 5 ampere current, it will always give you 5 ampere current because this is a current source. And even if there is 0 volt across it, it will always give you 5 ampere current source. In case of voltage source, what happens? Even if there is 0 current flowing through it, whatever the current is flowing through it, it will always give you 5 volt. Even if the current is infinite, even if the current is 0, even if the current is 5 ampere, even if the current is 4 ampere, 3, 2, 100, 1000, it will always give you 5 volt. No matter whatever the voltage is there across the current source, even if it is 0, even if it is 100, even if it is minus 100, even if it is infinity, whatever the voltage is there, it will always give you 5 ampere current, right? So the current here would always be 5 ampere, always 5 ampere current will flow from here, right? So now tell me what will be the circuit at t equals to 0. Circuit at t equals to 0. This is 5 ampere current source. This is a resistance R, right? This complete circuit will be shorted. This complete circuit is shorted. So tell me what will be this current is IC, because at t equals to 0 capacitors will be short circuited. So tell me what will be the value of IC. IC value at t equals to 0 plus would be 5 ampere, right? Because this complete current will be flowing through the short circuit path. The current here is 5 ampere, right? The current here is 5 ampere. Now this 5 ampere current sees two paths, resistance R and a short circuit path. So it will go to short circuit path only. So the IC current is 5 ampere. It is not infinity. So the circuit looks like something like this. Circuit looks something like this, 5 ampere and a short circuit path, right? This is how the circuit looks like, right? Now you will not say there is infinity current. If there was a voltage source, we would have said there is infinity current, V by 0 resistance, infinity. But this is already a current, so it is 5 ampere only. So it is not the case of infinite current. It is the case of a finite current, that is IC equals to 5 ampere, right? So IC equals to 5 ampere. IC 0 is 5 ampere. What is the VC value at t equals to 0 plus? That is VC value or V naught. We are only commenting out V naught. V naught value at t equals to 0 plus, that is 0 volt. What is the IR value at t equals to 0 plus? Since no current is flowing here, the IR at 0 plus is 0 ampere, right? This is the condition at t equals to 0 plus. Now let's talk about the time constant. Tell me what is the time constant. Just make a small box here. We can talk about the time constant here. Tell me what is the time constant. For time constant, open circuit the current source. Open circuiting the current source, you will make a resistor. There are two capacitors this time. C1 and C2. This is the resistance. C1, C2 comes in series. So from wherever you connect the output, from here you connect the output, from here you connect it. In case of exponential response, the complete circuit will be exponential. Okay, this line is not actually completely true. So let's just forget that line. The previous line is wrong actually. So from wherever you connect the output, let's assume I am connecting my output from here. Okay, I am collecting my output from here. Okay, now tell me what will be my C effective. C1, C2 are in series, so C1, C2 upon C1 plus C2, right? What will be my R equivalent? C1, C2 will be one capacitance, that will be C1, C2 upon C1 plus C2. These can be converted into one capacitor, right? That's why it is a first order circuit, not second order. Even though there are two capacitors, but still it is a first order circuit. Okay, what is R equivalent? R equivalent is R. So what is the time constant? R into C1, C2 upon C1 plus C2. So this is our time constant. Okay, circuit at t equals to 0 we have discussed. Circuit at t equals to infinity. So what will happen? 5 ampere current source. Resistance R is there. The capacitor will be open circuited, right? Capacitor will be open circuited. Right? So this value will be V naught. The capacitors will be open circuited. So the complete current will be flowing through this resistance. So here the voltage drop would be 5R. Right? So now what will happen? Now tell me what will be the value of V naught. If this is grounded, what will be the potential of this point? 0. What will be the potential of this point? That will be 5R. Do you know the potential of this point? No, because they are open-ended, right? They are open-ended nodes. You don't know the potential of this point, but you know one thing, 5R voltage is applied to two capacitors. In the previous video, previous video it was there, or in the previous video only, when we solved the numerical example, we saw that finally the voltage was getting divided into two capacitance, and this is what is happening here. So 5R voltage, this 5R voltage is getting divided into C1 and C2. This 5R voltage is getting divided into C1 and C2, right? This is what your V naught is. So what will be your V naught? Your V naught, here I will write, V naught at t equals to infinity would be 5R into C1 upon C1 plus C2. I should write it in better manner. 5R into C1 upon C1 plus C2, right? This will be your V naught at t equals to infinity. What will be the value of IC at t equals to infinity? That will be 0 ampere. Now some students who think a lot, they may think that the current will be impulsive, IC, because they will say that 5R voltage is coming and then here the capacitors are there, so we can say the current will be impulsive. Is the capacitance shorted here? Capacitance are not shorted here. They are providing very high impedance. They are open circuited actually. The capacitance are open circuited, not short circuited. So you can't say the current will be impulsive. Okay, the capacitance are providing very high impedance. Okay, so 5R by very high impedance. That means very low current, that is equals to 0 ampere. Are you getting my point? For dividing the potential, I have made the circuit like this, but actually they are nearly open circuited. So IC infinity will be 0 ampere only, and what about IR infinity? That would be 5 ampere. You know the time constant, you know the values, you can make the graph, you can write down the equation. I will just make the graph. You can write down the value of equation of IC, because IC is starting from 5 ampere and going down to 0, from 5 ampere to 0. What about V naught? It is going from 0 to, it is going up to this value, 5R C1. Okay, I will just write it. So ICT, for ICT, initially ICT was 5 ampere and then goes down to 0. 5 into e to the power minus t upon 2 ut. What about VC V naught t? It goes up to 5R C1 upon C1 plus C2 and starts from 0 ut. What about IRT? It starts from 0 and goes up to 5 ampere. We are talking about IRT, right? IRT. So goes up to 5 ampere and starts from 0. This is ampere, this is volt, this is ampere. Now you can make the graph on your own. I will not make the graph now, or should I make the graph as well? No, you can make the graph from 5 to 0, from 0 to 5R C1 upon C1 plus C2, and for IR from 0 to 5. So these will be the graphs. Okay, so I will draw the graph as well. Why should I leave anything? 3 graphs I have to make. Like some people will be reading from notes only, they will not be reading from the lectures, so for them I am writing it down. Okay, ICT, V naught T and IR T. ICT from 0 to 5. What about V naught t? V naught t was also from 0 to ICT is actually from 5 to 0. So this I have made IRT actually. This is IRT, right? From 0 to 5. ICT I will make here. ICT is from 5 to 0. From 5 ampere to 0 ampere, right? And VCT, V naught actually from 0 to a certain value. The value is 5 C1 upon, it is 5 R C1, no? 5 R C1 upon C1 plus C2. 5 R C1 upon C1 plus C2. Okay, so these are the graphs. Okay, so we can see more examples since we have time left. So we will see more examples of RC circuit. Okay, now again with the voltage source. So how will you replace this circuit? Here we need to comment on only two things, that is V naught t and IT. Okay, so how will you replace the circuit? This is C1, this is R, this is C1, this is 5 UT. I guess now you guys are very much comfortable with whatever is happening in the circuit. I hope you guys are finding it now easy to comment on the circuits, right? Because we have seen many examples and very deeply we have studied. If we have just studied open circuit, short circuit, voltage is always conserved or all these things, we have studied very deeply. Impulsive current we have seen, step current we have seen, everything we have seen, step voltage we have seen. So I guess now guys are very much comfortable, right? So tell me, what will be the value of V naught? First tell me the time constant of the circuit. First we will comment about the time constant. Is it a second order or first order? It's a first order circuit only. Why is it so? Because the C1, C2 are in series. What will happen? We will short circuit the voltage source. Voltage source is shorted. This is C1. Then we will have a resistance R. Then we will have a C2. This is resistance R, C2. Right? So C1, C2 are in series. So R effective is R equivalent, I should say. Wherever you connect the output, if we are connecting the output here, so R equivalent is only R and C effective is C1, C2 being in series, it would be C1, C2 upon C1 plus C2. So what will be your time constant? R C1, C2 upon C1 plus C2. That will be your time constant. Okay. This will be your time constant, first order circuit only. Okay. Now comment on the things. Tell me, what will be the value of I at t equals to 0 plus? Tell me, what will be the value of I at t equals to 0 plus? IC you can say, or I you can say. I will call it IC. Okay, instead IC we should say. So IC at t equals to 0 plus. What will be the value? C1, C2 both will be shorted. The value will be 5 by R. It is not infinity. So 5 by R ampere. What will be the value of V naught t? Instead of V naught, should we comment on VCT or V naught t? We should, instead of that, we should comment on VCT. Okay, let's comment on VCT only. Let's call this VCT. Okay, instead of taking complete output, you can comment on complete output as well, but we are now commenting on VCT. Okay, so tell me initially what will be the value of VCT? VC at t equals to 0 plus, it will be 0 volt only, right? 5 by R current is flowing, so it will be 0 volt only, because the capacitor is shorted, C1 is shorted, C2 is shorted. So VC at t equals to 0 plus is 0 volt only. Okay, now the thing is circuit at t equals to infinity. circuit at, this is an interesting point now, circuit at t goes to infinity. 5 volt here, C1 will be open circuited, C2 will also be open circuited. C1, C2. How will you divide the potential now? Because if this is grounded, this is 0, good. This is 5. Do you know about this potential? Do you know about this potential? No, you don't know about these two potential. Why so? Because both are open-ended nodes. Open-ended nodes. Okay. So now how will you divide the potential? We know that potential is going to be divided, right? In the previous examples that we have seen, we saw only two things, capacitors. We saw only two capacitors, C1, C2. Now there is a resistance as well. So what you will do of this resistance? That is the main task. Tell me one thing. At t equals to infinity, that means steady state. So at steady state, omega is 0. That means resistance provided by the impedance provided by the capacitance, impedance by capacitor is very high, right? So the series combination of RC, RC2 it is, series combination of RC2 can be replaced with a single capacitor. Why so? Because this is a finite value and this is very high. So very high plus finite will be equals to very high only. So this will be replaced with a single capacitor, that is C2. So what will be your equivalent circuit? Equivalent circuit at t equals to infinity. So basically C1, that C1 will remain there as it is and C2 will come here, right? And there will be this 5 volt. Now will the current be impulsive? Current will not be impulsive, right? We are commenting on this, we see. Will the current be impulsive? No, current will not be impulsive. Why so? Because the capacitors are open circuited here, not shorted. Okay, so the current will not be impulsive. So what will be your VC at t equals to infinity? It would be 5 into, and yeah, here we can comment about IC actually. So IC at t equals to infinity would be 0 ampere. Why so? Because these are providing very high impedance, they are open circuited. They are providing very high impedance, they are open circuited. And what will be VC at t equals to infinity? That would be 5 C1 upon C1 plus C2. Okay, so from 0 to 5 C1 upon C1 plus C2 it is writing. So let's comment on VC. VC 0 plus is, first it was 0 volt because they were shorted, then it was rising to 5 C1 upon C1 plus C2. What about IC? IC initially was 5 by R ampere, right? And then it was rising to 0 ampere, right? So let's comment down the value of VCT. From 0 to some value it is rising. And what about ICT? From 5 by R to 0 it is going. What is the time constant? That is R. What is the time constant? R C1 C2 upon C1 plus C2. From 5 by R to 0 it goes. and from 0 to 5C1. Are you understanding those circuits? Okay, well and good, very easy. Let's move on to next circuit. You will solve it on your own. Okay, we will comment on VR2, we will comment on V0, also we will comment on the current. So you should solve the circuit on your own. IT. Okay. So initially tell me what will be the value of V0. First tell me the time constant. What will be the time constant? Time constant would be, this will be shorted, R1, R2 will come in series and C1, C2 will also come in series. So R equivalent would be R1 plus R2. And what will be C effective? C effective will be C1, C2 upon C1 plus C2. What will be your time constant? R1 plus R2 into C1, C2 upon C1 plus C2. Okay. This will be your time constant. Got it? Now we need to comment on the circuit at t equals to 0. At t equals to 0. I will not make the circuit this time. Tell me, what will be the value of IT? I at t equals to 0 plus. C1 will be shorted, C2 will be shorted. R1, R2 will come in series. The current simply be 5 upon R1 plus R2. What about the current we have talked about? What will be the V0 value at t equals to 0 plus? C2 is shorted, C1 is shorted. So R1 and R2 are in series, simply potential divider. 5 into R2 upon R1 plus R2. Simply potential divider, nothing else. 5 into R2 upon R1 plus R2. This is V0 at t equals. What will be the value of VR2 at t equals to 0 plus? VR2 at t equals to 0 plus and V0 at t equals to 0 plus will be the same because capacitor is having 0 voltage. So VR2 and V0 at t equals to 0 plus will be the same. That would be 5 R2 upon R1 plus R2. Now let's talk about circuit at t equals to infinity. At t equals to infinity. 5 volt is there. This is open-ended. This is a resistor. This is open-ended. Right? What will be the drop here? That will be 0 volt. This is R1. This is R2. This drop will be 0 volt. The current will be 0 ampere. Right? This is C1. This is C2. This is your V0 and VC2 we are not talking about. Okay. Yeah. So now you know the potential of this point. If this is 0, this will be 0 volt. You can use a different pen. This will be 0 volt and this will be 5 volt. Do you know the potential of this point? No. You don't know the potential of this point? No. Although the drop here is 0 volt, but you don't know the potential of these 2 points, right? The drop across the resistor R2 is 0. That means the drop of this point and this point will be the same, but you don't know what is the value. Why so? Because they are open-ended. Open-ended nodes. So what will happen? Open-ended nodes. At t equals to 0, now what we will see? If there is ambiguity, what do we do? At t equals to infinity, omega equals to 0. That means series combination of RC will be replaced with a single capacitor. Right? So simply 5 volt will be divided into C1 and C2. This is 5 volt, this is C1, this is C2. Right? Basically, this will be your V0 only now because your VR at t equals to infinity is, this was your VR, right? VR2, whatever we say, VR2 at t equals to infinity is 0 volt. What will be your V0 at t equals to infinity? that would be 5 C1 upon C1 plus C2. And what about I at t equals to infinity? That would also be 0 ampere, not impulsive, because they are providing very high impedance. Okay. So basically now we will make the graph. You can write down the equation on your own, but now we will make the graphs. If you can make the graph, if you know the time constant, you can write down the equation as well. Because you only need to know three things for writing down the equation: t equals to 0, t equals to infinity, and the time constant. These three things you need. V naught t, it, V naught t, it, and VR2 t. VR2 t and it. Right? What about, first we will comment on it. It is 5 r1 upon r1 plus 5 upon r1 plus r2, then goes down to 0. Okay, wait. We are talking about it now. So it is, first it has some value, that is 5 upon r1 plus r2. You can solve all this circuit by Laplace transform as well. Okay, every teacher teaches is with Laplace transform. Okay, but it will take a lot of time and it won't develop your brain. I want your brain to be developed. Okay, that's the important thing. You should have the intuitions so that you can solve the circuit correctly, also quickly. If you solve by Laplace, there is high chance you will get it wrong in the exam, because there will be a lot of pressure and you will be solving very quickly, and one calculation mistake will ruin all the hard work, right? But this is the intuition. Here you are just completely thinking and you won't get it wrong if you are thinking, right? I have given you enough intuitions. Now you can think of any circuit by your own. When we will solve this problem, you will understand why I have spent so much time on this. Okay. So this is about IT. Now let's comment on VR2t. VR2 goes down to 0 and starts from some value, that is 5 R2 upon R1 plus R2. It starts from 5 R2 upon R1 plus R2. Now what about V naught T? V naught T initial was V naught at T equals, okay, V naught T is the complete potential. So it is 5 R2 upon R1 plus R2. Then it goes to 5 C1 upon C1 plus C2. Now it depends on the value of RC, how the V naught waveform look like, right? So for V naught, I will have to take conditions. Because V naught T, in V naught T there is ambiguity. So let's see. V naught at T equals to 0 plus is what? 5 C2, 5 C1, or whatever it is. At T equals to 0, it is not C1. It is 5 R2 upon R1 plus R2. 5 R2 upon R1 plus R2. And what is V naught value at T equals to infinity? That is 5 C1 upon C1 plus C2. Okay. So there are two chances. It can rise, it can decay, it can be equal, right? You can write it down as 5 upon 1 plus R1 by R2. You can write it down as 5 upon 1 plus C2 by C1, right? There will be basically three graphs. First, in one graph it can rise R1 by R2, and in the other graph it can decay down in the third graph it may remain flat. third graph it may remain flat, right? This will be your V naught T. This condition we clearly know, R1 C1 equals to R2 C2, right? Because R1 C1 equals to R2 C2, then R1 by R2 is equals to C2 by C1. So this value and this value will be same. So initial and final value will be the same, right? Initial and final value will be the same. So in this case, what will be the time constant? That is also one important thing, and the time constant will be 0 second in this case, right? In all the other cases, the time constant would be the same. That is R1 plus R2 into C1 C2 upon C1 plus C2. R1 plus R2 into C1 C2 upon C1 plus C2. And here as well the time constant would be the same, R1 plus R2 C1 C2 upon C1 plus 2. Now tell the conditions. Here this value is larger, that means I guess it would be R1 C1 is lesser than R2 C2. If C2 by C1 is larger, this will be lower. So V infinity will be lower. So this condition will be R1 C1 greater than R2 C2. R1 C1 greater than R2 C2. Why so? Because R1 by R2 would be greater than C2 by C1. If this value is larger, that means overall value will be low. So at t equals to 0 plus we are having low value, and at t equals to infinity we are having high value. And this condition would be R1 C1 is lesser than R2 C2. Okay, that means C2 by C1 is larger, that means this value is larger, so overall value will be low, so infinity value is low and 0 value is high. So that's how the graph will go. Have you got the point? Have you understood the circuit? I hope you have understood the complete circuit. Okay, so these were also two good examples. If there are more examples left, let's see. Okay, so this is a whole new concept. There are three circuits A, B and C. The capacitor C1 is charged to 5 volt. You have to find the voltage across C1, C2 and the current. So there are three circuits. We will analyze the circuit one by one. Okay, so let's start with circuit A. We have time left, we can do it in this lecture as well. Okay, yeah, so this is our first circuit. C1 capacitor, C2 capacitor, IC1 current, IC2 current, VC1 voltage, VC2 voltage. VC1 is already 5 volt. Okay, the switch is closed at t equals to 0. What is happening at t equals to 0? Circuit at t equals to 0, or I should make it at low. Circuit at t equals to 0. This capacitor will be replaced with a 5 volt battery, right? Initial voltage will be replaced with its initial voltage, will be replaced with a 5 volt battery, right? This will be replaced with a 5 volt battery. Switch is closed, so short circuit. This capacitor is having no voltage, it will be shorted. Arey yaar, it will be shorted. Okay, this will be shorted. Okay, so now tell me, what is the current flowing now? This is 5 volt, this is shorted. Even if VC2 was 1 volt, what will be the current? Let's assume your VC2 initially was 1 volt. So 5 volt and 1 volt. What will be the current? Current is 5 by 0. Infinite. Impulse current. That means sudden change in capacitor voltage. Sudden change in capacitor voltage. We don't know the value of current, we don't know the impulse current, but there will be sudden change in capacitor voltage, that we know, right? Even if VC2 was having 6 volt, what will be the current? 5 minus 6 by 0. Impedance will be 0, na? There is no resistance involved, so impedance is 0, right? So the current would be infinity only. So the current would have been infinite only. So now the current is infinity, impulse current is flowing. That means there will be sudden change in capacitor voltage, right? So how you can find the sudden change in capacitor voltage? So this is your circuit. C1, C2. This will be VC1. This will be VC2. This is already charged to 5 volt. We will apply charge conservation. Charge conservation. How will you apply? Charge before switching. Switching equals to charge after switching. What was the charge before switching? It was C1 into 5. What will be the charge after switching? After switching, both of the capacitor has to have one single voltage, right? After switching, VC1 has to be equals to VC2, right? So C1 VC1 I will write plus C2 VC2 I will write. After switching, why it has to be equal? To follow the KVL, right? Potential has to be equal. So after switching, VC1 equals to VC2 equals to some voltage VC. So after switching, both of them has to be equal. So initial charge 5 C1 is equals to C1 plus C2 VC. So VC would be 5 C1 upon C1 plus C2. So from 0 to suddenly it will charge to this value. So this will go from 5 to this value. This will go down. VC1 will go down from 5 to this value, and VC2 will go up from 0 to this value. We will write down a short note here. Okay, note. Let's assume this was the condition. The switch is closed at equals to 0. This was C1, this was C2. This was having V1 voltage and this was having V2 voltage. And let's just call this potential as V naught. So V naught at t equals to, so how will you apply the charge conservation now? C1 V1 initial charge at this is C1 V1. What is the initial charge at this? C2 V2. What will be the final charge? C1 C2 both will come in parallel and both of them will have a common voltage, that is V naught. So your V naught would be C1 V1 plus C2 V2 upon C1 plus C2. Are you getting this point? Always see the direction. Okay, if V2 was negative, you would have written C1 V1 minus C2 V2. So initial voltage, always see the direction. C1 V1, C2 V2, initial voltage upon what will be the final. At final, both of them will be having V0 voltage. Both of them will be having the same voltage V0. So C1 V0 plus C2 V0. So that would be C1 plus C2 into V0. So V0 would be C1 V1 plus C2 V2 upon C1 plus C2. What we did? Initial charge plus final charge. So both of them will be having the same voltage. So this will happen. Okay. So let's make the graph. So if I make the graph of VC1, what will happen? And then I will make the graph of VC2, what is happening. Okay. So this we are talking about VC1 versus T, and then we are talking about VC2 versus T. So in case of VC1, first we are coming from 5 volt. We are coming from 5 volt, and then we are going down to 5 C1 upon C1 plus C2. This is 5 volt and going down to 5c1 upon c1 plus c2. And what about this? We are in case of vc2, we are coming from 0 and then we are going up to 5c1 upon c1 plus c2. No transient. 5c1 upon c1 plus c2. What is the time constant? 0 second. What is the time constant? 0 second. Now tell me what about IC1 and IC2. What is IC1? This is your IC1, right? And this is your IC2. One thing we know here is that IC1 is negative of IC2. IC1 is flowing in this direction, IC2 is flowing in this direction. Can you find IC2? IC2 will be actually positive because it is having the C2 capacitor is getting charged. If C2 capacitor is getting charged, that means the current is flowing into the C2 capacitor, right? C2 capacitor is getting charged, that means the current is flowing into the C2 capacitor, and C1 capacitor is getting discharged, that means current is flowing out of the capacitor, right? So I will write it down. C1 capacitor is getting discharged. That means current flowing out of the capacitor. Current flowing out of the capacitor. And C2 cap is getting charged. That means current is flowing into the capacitor. Current flowing into the capacitor. That means here what you will see, IC1 is negative, right? Because we are showing it flowing into the capacitor, but it is actually flowing out of the capacitor. So IC1 is negative and IC2 is positive, right? Now I will just make the waveform. Now how will you make the waveform? That's interesting. So this will be for IC1, this will be for IC2. The current will be impulsive. What will be the magnitude? I want you to tell me that. For IC1 we will have a negative value, and for IC2 we will have a positive value. This will be your IC1 and this will be your IC2. What will be the magnitude? C1 capacitance, like what will be IC? IC will be C dVc by dt. The change in capacitance voltage, the change in capacitance voltage from let's just call this potential as V dash. We are calling this potential as V dash so that we can actually write it. Okay, we are calling this potential as V dash. So what is happening? This is going from 5 to V dash. So what is the change? C, what is the change from 5 to V dash? Now, is this value positive? Yeah, this value is positive. So we have to take a negative sign. Actually, change is written as, let's forget it. Change is written as, how change is written? Change is written as final minus initial. What is final? V dash. What is initial? 5. So this will be your magnitude. So, and C1 will also be here. So C1, what is the change in potential? I should have written like this. Capacitance is C1. What is the change? Final voltage is V dash. What is the initial voltage? That is 5. So C1 into V dash minus 5. Right? So it will be C1 into V dash minus 5. That is already showing that this is a negative value. Okay. Here your V dash is, what is V dash? 5C1 upon C1 plus C2. 5C1 upon C1 plus C2. So actually solving this you will get, after solving this you will get 5C1 C2 upon C1 plus C2. Okay. So I think 5C1 upon C1 plus C2. What is your V dash? V dash is 5C1 upon 5C1 upon C1 plus C2. So let's see it. 5C1. I'm just trying to solve it. Okay. C1 upon C1 plus C2 minus 1. Okay. So it will be 5C1 C2 minus value will be there. Okay. So you will get, this is your actually V dash. So you will get minus sign here. Minus 5C1 just by solving it, nothing else. Now what will be the voltage here? It will be C2 into, and this is impulsive, so already an impulse is there, C2 into the change in the capacitance voltage. Change in the capacitance voltage. From 0 to it is going to V dash. Right? From 0 to it is going to V dash minus 0. So it would simply be 5C1 upon C1 plus C2. This we are talking IC2. Here also you can see IC1 is negative of IC2. Right? Understood? All the things you have understood? IC1, IC2, VC1, VC2. Right? Let's take next circuit, that is circuit B. Let me pause and make the circuit. So this is the circuit B we are having. Okay. So tell me what is happening circuit at t equals to 0. Circuit at t equals to 0. This capacitor will be replaced with a battery of 5 volt. Well and good. Battery of 5 volt. This resistance will remain there as it is. This capacitance will be shorted. So what will be the current IR or IC, you can say. IR. The same IR current is flowing through the capacitor, right? Okay. One thing here. What was the time constant? 0 second. Okay, we have told. Okay. Yeah. So what is the current at t equals to 0 plus? What is the current at t equals to 0 plus? That is 5 by R ampere, not infinite current. Okay. So the capacitor will hold its voltage. That means VC1 0 plus would be 5 volt and VC2 0 plus would be 0 volt. Right? Now what happens? This 5 by R current after t equals to 0 plus, after t equals to 0 plus, this is capacitor C which is having 5 volt. This is capacitor C1. This is resistance R and this is capacitor C2. Now what happens? There is this 5 by R current is flowing, right? This 5 by R current charges C2 and discharges C1, right? This 5 by R current is charging the C2 and discharges C1. Now at what point, till what point there will be some current? This charging and discharging will go on. This charging and discharging will go on until current becomes 0. Will go on until IR goes to 0. When IR goes to 0? At what point IR will go to 0? IR will go to 0 if VC1 is equals to VC2 equals to some potential. This is VC1 and this is VC2. If both of the potential are 0, that means there is 0 drop across the resistance. If this is V, this is V, that means there is 0 drop across the resistor. That means there is 0 ampere current. So if 0 ampere current is flowing through the resistor, that means 0 ampere current is flowing through the capacitor as well, because all are connected in series, right? So if VC1 and VC2 equals to 0, that means IR is equals to 0 ampere. That means there will be no current through capacitors, right? So what happens at steady state? So that shows at steady state Vc1 equals to Vc2 equals to some potential Vc. Now what we can do? Apply charge conservation. Right? We can apply charge conservation. So initially we were having 5 into C1 voltage, and then we will be having C1 plus C2 into Vc. Your Vc at t equals to infinity actually. Vc at t equals to infinity would be 5 C1 upon C1 plus C2. Okay. That means it will be equals to Vc1 at t equals to infinity and Vc2 at t equals to infinity. Actually, we shouldn't write Vc infinity because we are actually we should have written here at steady state Vc1 infinity is equals to Vc2 infinity is equals to Vc, right? So this is the condition. So Vc value is rising, this value is going from 5 to this value, but this time the response is not step, it is not going from 5 to suddenly that value, it is exponentially decaying. Why so? What is the time constant? Time constant. What is the time constant? This is C1, this is a resistance R, this is C2. C1 C2 are in series, so C effective is C1 C2 upon C1 plus C2. What is R equivalent? That is R. So what is the time constant? That is R C1 upon R C1 C2 upon C1 plus C2. This is the time constant. So what is actually happening here? Initially it was having 5 volt. So the current was 5 by R. Now what happens? This gives some voltage to this. Let's assume it has developed 0.1 voltage. So what will be the current? 5 minus 0.1, that means 4.9 by R. After that, let's assume it is developed 1 volt, then the current would be 4 by R. So slowly the current is getting reduced, right? Slowly the current is getting reduced and C1 is getting also voltage across C1, that is VC1, VC1 is also reducing and VC2 is increasing. At some point VC1 and VC2 goes equal. So this is what is happening in the circuit. I hope you have understood the complete concept. I will repeat it once again. Initially C1 was having 5 volt, that means 5 by R current was flowing, that means 5 by R current is discharging the capacitor C1 and charging the capacitor C2. So slowly the VC1 is going down and VC2 is going up. At some point of time both VC1 and VC2 will be equal. At that point of time the current flow will be 0. At that point of time current flow will be 0. And at that is the point when steady state is reached. So this is the point where steady state is reached. You can solve the circuit with Laplace transform as well. How will you solve the circuit with Laplace transform? You will replace this circuit C1 and 5 volt 5 by S volt battery with 1 by with 1 by C1S capacitance in series, then resistance R, then 1 by C2S capacitance in series, and then you can solve the problem, right? We will solve by Laplace transform as well. I will just make the circuit, then you can solve. Okay. So yeah, so this is what is happening. And what is the value of IC or IR? IR at t equals to infinity, that is 0 ampere, right? IR at t equals to infinity is 0 ampere. So it is starting from 5 by R and then going down to 0. So first make the graph of IR. What about IR? What about IR? And this is VC1 and this is VC2. What about IR? It is starting from 5 by R and goes down to 0. Okay, okay. With time constant R into C1 C2 upon C1 plus C2. I will also write down the equation of IR from 5 by R to 0 ut. Okay, and here if they had asked you what is the equation of, in the previous problem, here what is the equation of IC1T? IC1T, what is the equation of IC1T? That is minus 5 C1 C2 upon C1 plus C2 delta T, right? And what is the equation of IC2T? That is 5 C1 upon C1 plus C2 delta T, right? And here in this question, the equation is 5R e to the power minus t upon 2 ut. What about VC1? VC1 was, previously it was 5 volt, it was 5 volt, then it decays down to some value, but it decays down exponentially, right? From 5 volt to, it decays down to 5 C1 upon C1 plus C2. Okay, what about VC1? VC1 slowly it is 0 and then going up to 5 C1 upon C1 plus C2. Five C1 upon C1 plus C2. So write down the equation of VC1T. Let's just call this value as V dash. Okay, because we don't want the equation to be complex. So what is the value of V infinity? That is V dash plus 5 minus V dash e to the power minus t upon 2, right? And what about VC2? VC2 I can directly write, that would be 5 C1 upon C1 plus C2, 1 minus e to the power minus t upon 2. Of course, ut will be there, and here as well we will have ut. Are you understanding the point? Here the initial and final value are same, but there is one difference in the second circuit, is that the response is exponential. From first circuit to second circuit, there is only one difference, that is the response is exponential. In the first circuit, there was immediate response because there was no resistor involved. If there was no resistor involved, that means the current was infinity. Okay, now we will see the example where resistance is involved. Still there will be two kind of response. One response will be exponential and the other response will be the one response will be the sudden rise and the other response will be exponential. So in the third example we will see all two cases. Okay, so I hope you have understood this concept. We can like decay it down to what is the value of V dash, that is 5 C1 upon C1 plus C2. Here we will have 5 minus 5 C2 upon C1 plus C2, I guess, e to the power minus t upon 2 ut, like 5 minus V dash, right? V dash, what is V dash? 5 C1 upon C1 plus C2. That would be 5 C1, 5 C2. This would be plus. Okay, because at t equals to 0, you are having 5 volt. Yeah, that would be plus. So what you can take in common? Nothing. This is the final answer. Of course, you should make it like this. Okay, and this is also to complete ut. Okay, so these are the waveforms. Now we will take the final example, that is over third circuit, where both of the responses will come, that is this example. Okay, 5 volt RC2. Okay, so I will draw the circuit. So this was our third circuit. So circuit at t equals to 0. Now tell me what will happen at t equals to 0. You try to solve it on your own. Okay, this is very good example and you should solve it on your own because we have studied a lot of things, right? So the capacitor C1 will be replaced with a single battery. C1 will be replaced with a single battery of 5 volt. This will be replaced with the resistance R. And VC2 will be replaced with short circuit. What will happen? Tell me what is the value of current that is there here, here and here. Let's call this current as I and this current as IR. This current as IC1 I am calling. Actually IC1, wait a minute. Yeah, this is actually IC1, this is IC2 and this is IR. IC1 will be negative value of equal 5 by 0, that is infinite ampere current. Why so? 5 volt resistance is shorted, that means total resistance it C. From here what is the total resistance? R parallel with 0. R parallel with 0 will give you 0. So 5 by 0. So 5 by 0 that means infinite current, that is impulsive current. That means sudden change in capacitor voltage. So actually what is happening? Even though there is resistor connected, but at t equals to 0, the value of VC1 and VC2 has to be equal. Even though the resistor is connected, at t equals to 0, VC1 and VC2 has to be equal to follow the KVL. In the previous question, at t equals to 0, VC1 and VC2 doesn't need to be equal because if this is 5 volt, this doesn't need to be 5 volt. Even if this is 0, it is fine in the circuit. If VC1 is 5 volt, even though VC2 is 0, no KVL rule is broken here. If this is 5, this is 0, that is fine because the 5 volt drop R can take. But in this question, if this is 5 and this is 0, so what it will say? Here it will say, here it will say we have 5 volt, here it will say we have 0 volt. So by this also you can understand that at t equals to 0, they have to change their voltage immediately to follow the KVL. Or also you can see the infinite current is flowing, so it will change its voltage. So how it will change its voltage? Apply charge conservation. So charge conservation, apply charge conservation. So what I was saying, at t equals to 0, VC1 equals to VC2 equals to VC, some voltage. Again I am doing the same mistake. VC0 plus equals to, at t equals to 0 plus VC2 0 plus equals to some voltage VC. What will be that voltage? 5 C1 upon C1 plus C2, that will be your VC voltage. Are you getting this point? So first what happens? VC1 goes from 5 to 5 C1 C2, 5 C1 upon C1 plus C2, and VC2 goes from 0 to 5 C1 upon C1 plus C2. But is that the steady state? Let's see what happens after t equals to 0. After t equals to 0 plus, is this the steady state? That I need to know. This is capacitor C1, this is charged to VC voltage, right? At t equals to 0 plus, this is charged to VC voltage. This is resistor R, this is resistor R, and this is capacitor C, that is charged to VC voltage. So what is happening? And this current I am calling IC1 and this current I am calling IC2, right? This current is IC1, IC2. Now this VC, here we have VC, here we have VC. So this VC will come across resistance R. Same potential will come across resistance R. So because of this VC potential, there will be this current VCR flowing. VC by R is flowing. Are you getting my point? VC by R current is flowing, right? VC potential. So VC by R current is flowing. Now from where this current is coming? If there is, let's just assume there is some circuit. Here we have 5 ampere current. That means from here some current would be coming, from here some current would be coming, right? These two will make 5 ampere current, right? So if VC by R current is coming here, that means there would be some current coming from here and some current coming from here. Can you tell the value of these currents? IC1 would be at t equals to 0 plus negative value into C1 upon C1 plus C2. Did you understand it? Let me explain it. Let's assume there is this, okay, forget it. Let's assume there is this 5 ampere current. Okay, there is this capacitor C1 and this capacitor C2. Both are connected in parallel. Tell me what will be the value of IC1, what will be the value of IC2? 5 ampere current. Now both of them will be divided in the proportion, in inverse proportion of impedance. But since they are the capacitance, so the current will be divided in proportion to the capacitance. In case of resistor, what would happen? R2 upon R2 plus R1 in the inverse proportion. But in case of capacitance, they will be divided in the proportion, because the resistance provided by the capacitance is 1 by j omega C1. Or you can say, what will be IC1? IC1 would be 1 by j omega C2. The resistance provided by this impedance, this capacitance. The impedance provided by capacitance C2 upon total capacitance. So if you solve this, you will get C1 upon C1 plus C2. So basically the current is divided into 5 ampere. So basically the current is divided in the proportion. In case of capacitance, the current is divided in the proportion and the voltage is divided in inverse proportion. So the current is divided in proportion, right? So here we are having 5 amp VC by R current. So some current would be coming from here, some current would be coming from here, right? So 5 by R current would be divided in the proportion. So VC by R, C1 upon C1 plus C2. Why negative sign? Because the current direction would be this. Current direction would be this, but we have made the direction like this, IC1 and IC2. And what will be the IC2 value at t equals to 0 plus? That would be VC by R, C2 upon C1 plus C2, also negative sign. Are you getting this point? Now, what is happening? Both capacitor C1 and C2 are getting discharged. From both of the capacitor, current is flowing outward. That means both of the capacitors are getting discharged. Right? From both of the capacitors, the current is flowing outward. That means both of the capacitors are getting discharged. Till when it will discharge? The capacitors will discharge until IC1 and IC2 goes to 0, right? And if IC1 and IC2 are 0, if IC1 and IC2 goes to 0, that means 0 ampere current here, 0 ampere current here. That means IR goes to 0. IR goes to 0. That means if IR is 0, that means the resistance okay, I will write on the next page. If IR goes to 0, that means the voltage across the resistance is 0. If IR goes to 0, that means the voltage across the resistance is 0. if the voltage across the resistance is 0, the same voltage is across the C1, the same voltage is across the C2. So if VR is 0, that means VC1 and VC2 also 0. That means at steady state, VC1 infinity equals to VC2 infinity equals to VR infinity equals to 0 volt. Did you understand what is actually happening in the circuit? First 5 volt, immediately they change the voltage from 5 to, it goes to 5C1 upon C1 plus A2. Now because of this voltage 5C1 upon C1 plus A2, there is some current in the resistor, that is VC by R. Now this VC by R current is coming from two capacitance, that is VC by R into C1 upon C1 plus C2, and from here it is coming VC by R C2 upon C1 plus C2. So two currents are coming. Now what is happening? These two currents are discharging the capacitor. Now the capacitor are getting discharged. When it will discharge? Until the current through the both of the capacitor are 0. So when the current will be 0? If the current is 0, that means the current in the resistor is also 0. If the current in resistor also 0, that means what? The voltage across the capacitance is also 0. So this is what is happening in the circuit. Are you able to understand? Are you able to follow up? Very, very interesting analysis it is, right? So we will make the waveforms now. So what waveforms we have to make? VC1, I will see the question first. VC1, VC2, and also I guess we can make IC1 and IC2 as well. So we can make IC1 and IC2 as well. This is IC1, this is IC2. We can make all the waveforms. I will just take this circuit. I will call this current as IC1 and this current as IC2. Okay, so IC1 and IC2 also we can make. If we can make the waveform of IC1 and IC2, then we can make the waveform of IR as well. Okay, so first I will draw the VC1 waveform. IC1, IC2, we can make the waveform of IR as well. Then all the waveforms we will make. First I will make the waveform of VC1. Here I will make the waveform of VC1, and then I will make the waveform of VC2. So what is happening in case of VC1 and VC2? VC1 was initially it was 5 volt, then all of a sudden it drops down to 5C1 upon C1 plus A2. Initially it was 5 volt, then it drops down to 5C1 upon C1 plus A2, then exponentially discharges to 0, right? Exponentially discharges to 0. Yeah, what is the time constant? Tell me. We forgot to discuss the time constant. What is the time constant? Time constant. Forget about the initial voltage. C1, C2 are in parallel and R is one single R is there. So R equivalent is R and C1, C2 are in parallel. So it would be C1 plus C2. R into C1 plus C2. Right? The time constant is R into C1 plus C2. Okay. So what do you think? What will be the equation of VC? What should be the equation of VC1t? What do you think? How you should write VC1t? I will write it. Look, VC1t. I will write 5 u of minus t. This is ut. If this is ut, what will be u of minus t? This will be u of minus t, right? I am saying ut equals to 5. No, not ut. I am saying xt equals to, what I should say, xt equals to t. I am saying xt equals to t. What will be x of minus t? That will be minus t. What is the graph of this? This. What is the graph of this? This. So simply the graph is mirrored. If you take the mirror at y-axis, you will get this graph. If you take the mirror, you will get this graph. So whenever there is negation in the time, that means you will simply mirror. So if this is ut, this will be u of minus t, right? This is ut, then this is u of minus t. So you are having 5 volt for u of minus t. Then at t equals to 0, you are having this voltage and it decays down to 0. So 5 C1 upon C1 plus C2, and that is decaying down to 0 for u of t. Are you getting this point? 5 u of minus t plus 5 C1 upon 5 C1 upon C1 plus C2 e to the power minus t upon tau. What about Vc2t? This lecture is actually going to be of 2 hours, I guess. Yeah. So what about Vc2t? But I hope you didn't get bored at all. Right? You didn't get bored because this was very interesting analysis. We have seen many circuits and all were very interesting. So from 0 it will start, then it will go up to some value, that is 5 C1 upon C1 plus C2, 5 C1 upon C1 plus C2, and then decays down to 0. Then decays down to 0. What is the waveform of Vc2t? For t equals to 0 minus, you don't need to write because it is 0 only. So for next analysis only you will write 5 C1 upon C1 plus C2 e to the power minus t upon tau ut. This is your Vc2t. This is Vc1t. This is Vc2t. Okay. This is Vc1t. This is Vc2t. What about IC1 now and IC2? What is happening in IC1? First a negative impulse, then negative value that decays down to 0. Are you understanding? Look, it shouldn't be, it is too much, I know, but you should have it. Like if you revise it once again, it will be all clear to you. I am explaining very neatly, I guess. What will be IC1? Here we will have an impulse, right? From 5 to it is going down to some value 5 C1 upon C1 plus C2. So that because of that we will have an impulse because of the sudden change. Then Vc1 is going down. That means Vc1 is decreasing. That means we will have a negative current, and eventually the current goes down to 0. Right? So how will the dummy waveform look like for IC1? Negative impulse, then goes down to 0. What about IC2? A positive impulse, because voltage is increasing, then voltage is decreasing. That means negative value that decays down to 0. Right? Or if you already know the Vc1, you can simply differentiate it and then get the value of IC1 and IC2. Just differentiate it, you will get the value of IC1 and IC2. First an impulse, then decays down. Okay, but we can already know the value by our concepts. IC1, IC2. What about IC1? At t equals to 0, what is happening? At t equals to 0, it is having this impulse. From 5 to it is going down to 5 C1 upon C1 plus C2. Right? So the impulse will be 5 C1 C2 upon C1 plus C2, and negative sign will be there. How I have written it? C1 into the change in the voltage. What is the change in the voltage? 5 C1 upon C1 plus C2 minus the initial voltage. So what you will get? C1 into 5 C2 upon C1 plus C2, and negative sign will be there. So it will be minus 5 C1 C2 upon C1 plus C2. Okay. Now at t equals to 0 plus, what is the value of IR? IC at t equals to 0 plus, that is this value, Vc by R into C1 upon C1 plus C2. What is the value of Vc actually? Value of Vc is 5 C1 upon C1 plus C2. So let's just forget it. We will just write Vc by R C1 upon C1 plus C2. So this is the value, and then it decays down to 0. This value, and it decays down to 0. What is this value? Okay, I think I can make a better waveform. This is the value. What is the value? Vc by R C1 upon C1 plus C2, that is minus Vc by R into C1 upon C1 plus C2. What is Vc? Vc is what was Vc? 5 C1 upon C1 plus C2. Right, this is Vc. Now what about IC2? IC2, initially there will be an impulse. The impulse will be positive. Why so? Because the capacitor value is getting charged. So 5 C1 upon C1 plus C2 into C2. C2 into the voltage it has developed. C2 into the voltage it has developed. It has developed 5 C1 upon C1 plus C2 voltage. Now this current will be there. What is the value of this current? That is Vc by R into C2 upon C1 plus C2. Okay. So first it goes like this, and then it decays down like this. Okay. So I hope you have understood the concept. This is the IC2 graph. Now we will write down the expression. So what will be the expression of IC1t? Like these kind of questions are asked in the exam, but every time we have solved by Laplace transforms. And if you solve in by Laplace transform, it will be like very difficult for you to answer. Like they will ask you what is the value of current at t equals to 0. So you will solve by the Laplace transform and you will find the answer. But in the exam, if you know, you can simply tell the current will be impulsive. Then they can ask the value of f t equals to 0 plus. You will again solve by the Laplace transform and get to the final answer. But if you know the concept, you can directly tell. So that's why I am teaching so much deep, so that there will not be any problem for you. Okay. So first we are having an impulse, that's of minus 5 C1 C2 upon C1 plus C2 delta t. Then we are having an exponential decaying response. And for every competition exam it is necessary. Like now I have taught this concept, so many of the people will say this is not relevant for GATE exam. But if you pick up the questions from past of the question paper, you will see these kind of questions are asked. But every time we have solved by the Laplace transform, so we think that this is out of the scope. But this is not out of the scope. This is in the syllabus. So in the future, you can expect some very difficult question from these kind of analysis. So that's why I am teaching in very deep, and all the subjects will be dealing in the same way. Okay. So anytime any question can be asked in the like let's assume they are asking some question in GATE 2025. They ask this question in GATE 2025. The same concept will be there in your notes in GATE 2026. But we don't want that thing. जो आने वाला है वो पहले ही सीख लेंगे, right? But what really happens is sometimes like they teach later on, and then they say that yeah, I have taught this concept, but when it was asked, you didn't teach that concept. When it has been already asked, now you are teaching the concept, right? But this we will not let happen. We will not let this thing happen. Okay, we will teach all the concept that is necessary for the exam. Okay, and also for the placements. So this is the expression of IC2t, and this is the expression of IC1t. For IR, I leave it up to you. For IR, initially there was zero current, then suddenly the current was 5 C1 upon C1 plus C2 by R, then the current goes to 0. Okay, so IR waveform you can make on your own. I will just write down the equation of IR. What will be the equation of IRT? The current goes 5C1. What is the voltage that we develop? What is the voltage that we develop? 5. What is IR? VC by R. IR at t equals to 0 plus is VC by R. What is VC? VC is 5C1 upon C1 plus C2. So 5C1 upon C1 plus C2 by R. Then it goes down to 0. IR goes down to 0. So this is the expression of IRT. You can make the graph on your own. Simply from here to 0. Right? So this is the complete analysis of all the circuits. You can solve the circuit by Laplace transform as well. Let's just solve one of the circuit by Laplace transform. I will just make the circuit. You can solve the next part by your own. Okay, by your own. Solving the circuit by Laplace transform. Okay, so I guess I can copy the circuit. Tell me how this circuit will be replaced in Laplace domain. This capacitor will be replaced with 1 by C2S and a battery of 5 by S. A resistance R will be there. This C2 will be replaced with capacitance 1 by C2S. Right? This will be your VC1S. Okay, this will not be your VC1 I should write here. So this will not be your VC1S. Okay, this will not be VC1S. VC1S will be the complete one, because with the battery, because this is also a part of this complete is your capacitor C1. This complete is your capacitor C1. Capacitor C1. Okay. This is resistance R, this is C2. So this will be your VC2S. This will be your actually IC2S, IC2S, and this will be your IC1S. Now, if you need to know the value of VC1, VC2, you can apply the Laplace transform and get to the values. How will you apply Laplace transform? VC1, let's just write it one equation. VC1S minus 5 by S upon 1 by C1S plus VC1S by R plus VC1S by 1 by C2S is equals to 0. From here you will get the value of VC1S, and then you can find the value of VC2S and everything. So that's how you solve in Laplace transform, but this is not how we will be solving, because we have developed our brain, we have developed our concept. We are not just, we are the engineers, right? We are the engineers who don't believe in so much of mathematics. We believe in mathematics, but not so much of mathematics. When we can solve by your brain, by using our concepts, then why not we should solve the question by the concept? Why should we apply needless mathematical equations? Okay, so that's how you'll be solving in exam. They won't ask you that much deeper in exam, but they can ask you anything from this. Okay, so you should be able to write it down, and you will be able to answer very quickly if you have understood the concept very deeply. Okay, so I hope you have understood the concept. I hope you have enjoyed the 2-hour lecture. So it was an extensive lecture. Okay, so you must have gained a lot of knowledge. So there are a few more circuit left. I will deal those circuit and then we will move on to our questions. Okay. Okay. So meet you in the next video. Thank you. Hello everyone. So let's see this concept, the slope at t equals to 0 plus in RC circuits. But before that, let's solve a simple mathematical problem. Okay. They are asking, find the dxt by dt at t equals to 0 plus, or they can write it dx0 plus by dt, or they can write it x dash 0 at 0 plus. So tell me if I am doing right or wrong. What I am doing? I am putting x of 0 equals to I am putting t equals to 0. So x of 0 will be 6 into 0 square plus 3 into 0. So that would be 0. Now I am differentiating it and I am calling it this value, and differentiation of 0 will be 0. So is this analysis correct? This is wrong. Okay. So what should be the approach? If they are asking the slope at t equals to 0 plus, that means first you need to differentiate. First you will differentiate. Okay. First I will differentiate. What is the differentiation? That is 12t plus 3. Now I will put t equals to 0. Okay. Now I will put t equals to 0 or 0 plus, whatever I am putting. So my answer is 3. So basically dxt by dt at t equals to 0 plus or dx0 plus by dt or x dash 0 plus is 3. Okay. And one more thing you saw here is that note. What is that? Even if x of 0 is 0 volt, sorry, x of 0 is 0, then x dash 0 plus may not be 0, right? In the function, if you put t equals to 0, you may get 0 there. Okay, but it's not necessary that after differentiating and putting 0, you will also get the same value. Okay, it can be different. Here you can see, if you put t equals to 0 in this function, you get 0 voltage, 0 answer, you get 0. But if you differentiate it, you get 12t plus 3, and then you put 0, you get 3. So here in this example, x of 0 was 0, but x dash of 0 was 0 plus, you may say. X dash of 0 plus was not 0, it was 3. Okay, so I hope you have understood this concept. Okay, well and good. Just simple mathematical problem, but many times students get it wrong. Okay, that's why I have explained it here. Okay, let's see the questions now. You have to find VR dash, VR dash 0 plus, VC dash 0 plus, and IC dash 0 plus. It should have been written where VR dash 0 plus shows dVRT by dt at t equals to 0 plus. Okay, we just need to find the slope at t equals to 0 plus. Find slope at t equals to 0 plus. So from where I should start? Let's start with the simple equation. So let's just break down the circuit now. How will the circuit look like? The switch is getting close at t equals to 0. I will write 5 ut. At t equals to 0 plus they are asking. Okay. Both are grounded. You can make them like this and then make it ground. R and C. There is this current. IC is flowing. Okay. Capital IC they are calling it. So I will also write capital IC. So now I can write the equation. 5 ut is equals to IR plus 1 by ICR. 5 ut equals to ICR plus 1 by C integration IC dt. It would be better if I write ICT dt, and here as well if I write ICT. So ICT into R. Okay. Now what is my target? My target is to find the differentiation of the current. My target is to find that differentiation of the current. So what I will do? I will differentiate on both sides. Differentiating both sides. Right? I will differentiate both sides. So 5 ut will become 5 delta t. This will become R dic t by dt. And this will become, integration will be gone. So IC t by C. At t equals to 0 plus. At t equals to 0 plus. Now tell me what will be the value of 5 delta t at t equals to 0 plus. What will be the value? 0. Why so? What is the graph of 5 delta t? This is the graph of 5 delta t. At t equals to 0 plus, this is only at t equals to 0. At t equals to 0 plus, what will happen? It will go down to 0 only, right? So let's write it on next page. At t equals to 0 plus, what I will do, 5 delta 0 plus is equals to r into, this is at, and this is only the time domain value, by dt plus IC at t equals to 0 plus by c. Okay, I will just write down what is delta t? Delta t is infinity for t equals to 0 and 0 when t is not equals to 0. Okay, and what we are talking about? We are talking about t 0 plus. We are talking about t 0 plus. At t equals to 0 it is impulse, and at t equals to 0 plus it is 0 only. So this 5 delta t will go down to 0. So now this goes down to 0. This is r dic 0 plus by dt. Tell me what is the value of IC 0 plus? What is the value of IC 0 plus? At t equals to 0 plus, this capacitor will be shorted, the current will be 5 by R. So it would be 5 by RC, because IC 0 plus is 5 by R, right? So what will be my final answer? DIC dt is 5 minus 5 by R square C. This is my final answer. Or what will be the method 2? This is the method everyone expect you to answer. Okay, in the interview if they ask you this question, by this method you will solve. In written test you can solve by any method, but in the interview you will solve by this method. Okay, but in written test what you can do, but you shouldn't do in written test as well. Okay, but there is one more method. Just write down the equation of ICT. What is the equation of ICT? That is 5 by R e to the power minus t upon tau. What is tau? Tau is RC into UT. Just differentiate it now. Now many of the students will do the wrong differentiation, still they will get the correct answer, but we will do the correct differentiation. U into V will apply, because this is also a time domain function, right? U into V will apply first as it is, differentiation of second plus differentiation of second minus t by RC into 1 by RC, then RC will come t by 2. Yeah, differentiation we are doing. Okay, so t by RC it will go into second as it is. Now you will put t equals to 0 plus, right? This will already be delta t, like e to the power minus t by RC delta t can be replaced with delta t only. I have explained this concept a lot of time, right? Delta t minus 0 you can write, then 0 you will put here, so this will become 1 only. So this complete function can be replaced with delta t only, right? And if you put t equals to 0 plus, this delta will go down to 0. At t equals to 0 plus, this will go down to 0. So I am putting t equals to 0 plus by dt. So 5 by R, this will go down to 0. This will be 1 by RC, and this will be u of 0 plus. What will be the value of u of 0 plus? What is ut? This is ut, right? Ut is 1 for t greater than 0 and 0 for t less than 0. U of 0 plus will be 1 only, right? And here delta of 0 plus would be 0 only, right? Why so? Just make the graph. This is the graph, right? At t equals to 0 you can't define the value, but at t equals to 0 plus you are having 1 volt, right? So at t equals to 0 plus you are having 1 volt. Okay, I should have written it. At t equals to 0 plus, this value will be 1. So basically your answer would be minus 5 by R square C. So this is my final answer. Okay, so by this method also you can solve, but in the exam also, or in the written test, or everywhere I want you to solve by this method. This is just equation, you don't use your brain here. Okay, but you are using your brain here. Now let's find VRT and VCT as well. Okay, so we will find VRT now. So second what we will find? dVr 0 plus by dt, that we are finding. So 5 ut plus Vrt plus 1 by c integration I dot ic dot dt from 0 to t. Okay. One thing we can do here is that we can differentiate here and put the value as well. Okay. Yeah, we can do that. Differentiating on both sides. On both sides, what we will get? 5 delta t plus dVrt dt plus ICT, actually I should have written ICT here, ICT by C at t equals to 0 plus, this will become 0, this will be dVr 0 plus by dt at t equals to 0 plus. What is the value of IC? That is 5 by R, it would be 5 by RC. So dVr 0 plus, it would be minus 5 by RC. So this is my second answer. By equation you can solve on your own, or I should solve. What is VRT? VRT is, initially it is 5 volt and then decays down to 0. 5 e to the power minus t by RC ut. And then you can just differentiate it and put t equals to 0. Okay. So I will just differentiate it, this as it is, minus dVr at t equals to 0 by dt, that is 5 by RC. This is what you are getting, minus 5 by RC. Okay, by equation you can solve on your own, but here also I have solved. Okay, let's comment on dVct by dVc. Now let's comment on dVc 0 plus by dt. How will you write the equation? 5 ut is equals to ICR, ICTR. Now no one will write VCT here because you don't know the slope at t equals to 0 plus, right? ICTR plus VCT. Now if I differentiate it, what will happen? 5 delta t into R dict by dt plus dVct by dt. This will happen, right? And now I can find this value, but for that I need this value. Although I know this value now because I have already derived, but if I hadn't derived it, this was my first problem. So why should I write IC here? I can change it, right? So I will try to change it in terms of VC. So in terms of VC, I want to change my this value. So in terms of VC, I will change. So what is ICT? ICT is C dVct by dt. Okay. In the previous problem, I didn't use anything that I derived beforehand, right? I did not use anything that I derived beforehand. Here I derived this value, but I don't want to use this value. I am solving all the problems independently, right? So 5 ut is equals to RC dVc by dt plus Vc. Now I don't even need to differentiate, right? Because I already have this term. So for it's not necessary that every time you will be differentiating, right? For t equals to 0 plus 5 u of 0 plus RC dVc 0 plus by dt Vc 0 plus. What is the value of Vc 0 plus? Vc 0 plus is 0 volt only, right? Initial voltage at the capacitor, that was 0 only. What is the value of U of 0 plus? that is 1, right? So it would be 5 equals to RC dVc 0 plus by dt. So what will be the value of dVc 0 plus by dt? That would be 5 by RC. Okay, so this is my final answer. Got my point? Well and good. Easy question, right? You can solve by the equation as well now, but that's not a matter of concern now. So that's how we are advised to solve. In the interview, if someone is asking you this problem, they expect you to solve by this method only, not by the equations. And in the exam as well, if there is this simple RC circuit, this was very simple RC circuit, right? Very simple RC circuit. So if they are asking this simple RC circuit, you should solve by the equations only. Just try to solve as much as by the equation, by the method, by this method, not by the final equation, not by the final linear equation. Okay, that is not also linear equation. I want to say, don't solve the problem by the exponential equation. Just try to solve by the differential equation. Okay. Now this is the problem. So it may happen that in exam it doesn't click you so early how to solve this problem. So in the exam you can solve the problem by simply by writing the exponential equation, then just differentiate it and put t equals to 0 plus. Okay, but in the interview, if they are asking this question, they will not be happy if you solve the problem by exponential equation. So you need to solve the problem by writing the differential equation only. So just try to think as much as you can think, then just see the solution. Okay, so you have to think. I need the complete equation in terms of VC. That's my target, right? Let's just call this current is I. I can simply write 5 ut is equals to, what will be my differential equation? 5 ut is equals to IR plus VC, right? Now the main task is replace I in terms of VC. Now task is replace I in terms of VC, right? This is my task. So tell me, what is the current here in this circuit? What is the current? C dVc by dt. And what is the current here? If this is VC, the current will be VC by R. Well and good. So I is equals to VC by R plus C dVc by dt. Did you get this point? So in exam or in the interview, if you are able to crack this thing very quickly, okay, if you are good enough, if you have done good enough practice, you will be able to crack it. Okay, C dVc by dt, VC by R, that's it. Okay, so I will just replace it. This is equation 1, this is equation 2. By equation 1 and 2, 1 and 2, 5 ut is equals to 5 ut is equals to, what is the value of I? That is VC by R plus C dVc by dt into R plus VC, right? 5 ut is equals to VC plus RC dVct, I should write actually, dVct, VCT. Even this current will be a function of time only. Okay, this will be also a function of time, ITR. Why it will be a function of time? Because this is a combination of the capacitor current and the resistor current. So both will, so capacitor current is a function of time. So this current will also be a function of time. RC dVct by dt plus VCT, right? So 5 ut 2 VCT plus RC dVct by dt, where they are asking at t equals to 0 plus, at t equals to 0 plus 5 u of 0 plus 2 VC of 0 plus RC dVc 0 plus by dt. So tell me, what is the value of VC0 plus? That is 0 volt only. And what is the value of U0 plus? That is 1. Right? VC0 plus. The capacitor initially will act as short circuit. Right? Initially it will act as short circuit. So it will be 0 only. Or one more thing, this would have been very easy if I did not replace it with I did not need to replace it with VC, and I did not need to replace I with VC. I can solve it from here as well, right? 5 UT, can I solve it? No, I can't solve it because I will have to differentiate, and then I don't know the value of this thing. I don't know this thing, right? dit by dt I don't know. So I will have to differentiate. So I can't really solve it from here. Okay. I just thought I can solve it. Yeah. So 5 will be equals to RC dVC 0 plus by dt. So dVC 0 plus by dt is 5 by RC. This is my final answer. Got it? This is my final answer. Okay. And method 2 will also be there. What is the method 2? By using the equations. So how will you write down the VCT equation? VCT equation is initially it is 0 volt and then we are going to 2.5 volt, right? From 5 to 2.5 we are going. So 2.5 into 1 minus e to the power minus t upon 2 ut. What is the value of tau here? Tau value is RC by 2, right? Tau value is RC by 2. So simply differentiate it, dVC by dt, that would be 2.5, this as it is, into differentiation of the other one plus the plus second as it is and ut as it is and differentiation of this. So it will become e to the power minus t upon tau ut. And we are talking about t equals to 0 plus, so this will be 0 only. So dVC 0 plus by dt, this will go down to 0, so this complete factor will go down to 0 only, right? So 0 plus 1 by tau, and this will be 1 only. 0 plus 1 by tau. What is the value of tau? That is RC by 2. So basically your dVC 0 plus by dt is coming out to be 5 by RC only, right? Well and good, just the equation, but you just need to take care of the mathematics. Okay, well and good, easy problem. Okay, this method I would like more rather than this method. Okay, yeah, so this was the problem, finding slope at t equals to 0 plus. So in any circuit you need to think and find the values. Okay, so you can think on your own and then find the value. Okay, let's move on to the next concept, that is switch capacitor concept. Okay, this is very important concept and no one teaches this concept. Okay, so I will teach very deeply. Okay, so we have a capacitor C1 with initial voltage V1, then we have a capacitor C2 with initial voltage V2. Both are connected in series, then both are connected in series and there is no switch, nothing, both are open ended, so no current is flowing through them, so they will hold their voltage, right? So basically what I am saying, your VC1 0 minus is V1 volts and your VC2 0 minus is V2 volt, right? Now what is happening at t equals to 0, the switch is getting closed. At t equals to 0, switch is getting closed, that means V voltage is there and a complete path is there. So now the current will flow. So what will happen at t equals to 0 plus? At t equals to 0 plus, circuit at t equals to 0 plus, what will happen? This V voltage will come, this will be replaced with the battery V1 and this will be replaced with the battery V2. There are no resistor, only the voltage source. So what will be the current? The current would be V minus V1 minus V2. This is the voltage divided by 0. That means infinite. Impulse current. That means capacitor will change its voltage immediately. So how they will change? That's the main task. So let's draw the circuit now. Okay, let's draw the circuit. So this is the circuit. Now both of the capacitors are connected in series. So let's just call this current as IC1 and this current as IC2. Since both capacitors are connected in series. Capacitors are connected in series. That means IC1 is equals to IC2, right? IC1 is equals to IC2. That means C1 dVC1 by dt is equals to C2 dVC2 by dt, right? Change in charge will be the same. Change in charge will be the same. Or I can write C1 delta T to dt to dt get cancelled. So C1 delta Vc1 is equals to C2 delta Vc2. I can write, right? So let's just assume because of voltage source, because of voltage source V, because of voltage source V, if the change in Vc1 is delta V, then change in Vc2 will be what? What that will be? C1 by C2 delta V. That means if C1 develops its voltage by delta V amount, then C2 will develop its voltage by C1 by C2 into delta V amount. Let me repeat the statement. Because of voltage source V, if C1 develops its voltage by delta V amount, then C2 will develop its voltage by C1 by C2 delta V amount. Initially it was having V voltage. So basically what is happening now? This is capacitor C1, this is capacitor C2. This is voltage V. This is C1, this is C2. Initially it was having V1 voltage, right? But now I am saying it has developed. Now I am saying initially it was having V1 voltage. Now it has developed V1 plus delta V. Now what will happen to this voltage? Initially it was having V2 voltage. Initially it was having V2 voltage, but now it has developed C1 by C2 delta V voltage. If it had developed delta V, it would have developed C1 by C2 delta V, right? If it had developed, if Vc2 had developed delta V, then what will be the change in Vc1? If the change in Vc2 was delta V, then what would be a change in Vc1? That would be C2 by C1 into delta V, right? But here the change is delta V, so it would be C1 by C2 into delta V. So now you can apply the KVL. Applying KVL, and this is Vc1, this is Vc2. At t equals to 0 plus only we will reach the steady state, right? Applying KVL. Because there is no resistor involved and infinite current is there. So at t equals to 0 plus we will reach the steady state. Applying KVL, V equals to Vc1 plus Vc2. Right? So V equals to V1 plus delta V plus V2 plus C1 by C2 delta V. Our task is to find the value of delta V, right? So it would be C1 plus C2 by C2 into delta V. So from here you get the value of delta V, that is, what is the value of delta V? Is there anything wrong in the calculation? No, nothing is wrong. So delta V you get is C2 upon C1 plus C2 V minus V1 minus V2. That is the delta V you get. Okay. So what will be the value of VC1? So VC1, VC1 would be V1 plus delta V. V1 plus delta V. And what is the value of delta V? Delta V is C2 upon C1 plus C2 into V minus V1 minus V2. This is VC1. This is VC1 we are getting, right? What will be VC2? VC2 would be V2 plus C1 by C2 delta V, right? It would be V2 plus, people are celebrating Diwali after 2 days of Diwali. That too at 12 p.m. at 12 a.m. at night. I don't understand this. Okay, no problem. So what will be VC2? It is V minus V1 minus V2. So it would be V2 plus C1 upon C1 plus C2, V minus V1 minus V2. This will be your VC2 value. That's the steady state value. Okay. So if we draw the graph of VC1 and VC2. Okay, so now we will draw the graph, but we can't really draw the graph here because we don't know if this value is greater than V1 or less than V1. Like initially we are having, if we draw the graph for VC1, so initially we are having V1 voltage, then we are having V1 plus this voltage. Now we don't really know what is the value of this voltage, right? We don't really know what is the value of this voltage, right? So we can't really draw the graph. Okay, so let's forget drawing the graph because it can be greater than V1, it can be lesser than V1. We will solve a problem, then we will draw the graph. Now we have derived this thing, but in the exam you are not going to do this derivation, right? So how will you write the value? That I will tell you now. Okay. So now the thing is, again, anytime the firecracker may burn, okay, anytime sound may come, okay, so please bear with it. Okay, so yeah, so in one step I need to write the value of VC1 and VC2. So how will I write? First I will write the initial voltage. So first I am writing the initial voltage, that is V1, plus I will see what is the total voltage in the circuit. What is the total voltage in the circuit? From here I will start 0 plus V minus V1 minus V2. Total voltage is V minus V1 minus V2. Now for C1 I am writing, so I will divide the voltage in the inverse proportion, because in case of the capacitance we divide the voltage in the inverse proportion. So for C1 I am writing, so I will write C2 upon C1 plus C2. What did I do? First I wrote down the initial voltage, plus then I saw the total voltage, that is V minus V1 minus V2, then I just divide in the inverse proportion. So that's it, that's my final answer. So that's how you will write it. Okay, in one step only. Initial voltage plus total voltage in the circuit and divide in the inverse proportion. That's it. Okay. And how did we reach to the formula? In the interview, if they ask you how you are writing this formula, then you can tell them that if this is given delta V, this would be given C2 by C1 delta V, then you can just derive it and get to this answer. Okay. So this is VC1 and VC2 we are getting. Okay. So now let's see a question. So it will be easy for you. So I will just write down the question. In the question as well, you just need to find VC1 and VC2. Steady state. Okay, I will just pause it and then write down the question. So this is the question, you can read it. You need to find the VC1 value at t equals to 0 plus and VC2 value at t equals to 0 plus. Just as you close the switch, steady state will be reached. That we already know. Okay. So VC1 0 plus and VC2 0 plus we need to find. Okay. Yeah. So initial voltage are 2 volt and 1 volt. VC0 minus is 2 volt. VC20 minus is 1 volt. Okay, so 2 volt and 1 volt are the initial condition, and also we need to draw the waveform of IC. What is IC? This is IC. Okay, this is IC. So let's just write the value of Vc1 at t equals to 0 plus. What will be the value of Vc1 at t equals to 0 plus? Initial voltage, that is 2 volt. What is the total voltage in the circuit? 6 minus Vc1, that is minus 2 minus 1 into inverse proportion 2C by 3C, right? So this is 3, 2. So it would be 4 volts. What will be Vc2 at t equals to 0 plus? Can you tell? Without writing the equation, it will be 2 volt, because if this is 4, this will be 2. Or you can write down by the formula as well. 1 plus, what is the total voltage? 6 minus 2 minus 1. In the inverse proportion you will divide, right? So it would be 1 plus 1, 2 volt. So basically, what is the waveform? Okay, in the next page I will draw. What will be the waveform of Vc1 and Vc2? Vc1, first it was 2, then it went up to 4 volt. First it was 2, then it went up to 4 volt. Two volt to 4 volt. What about Vc2? First it was 1, then went up to 2 volt. First it was 1, then went up to 2 volt. From 1 volt to 2 volt, right? Now you need to write down the equation of IC1 and IC2. So you can write it down, right? IC1 is equals to IC2 is equals to IC actually. IC1 is equals to IC2 is equals to IC. So I can write IC is equals to C1 dVc1 by dt. That would be C1 is the value having C capacitance, right? Or I can write C2 dVc2 by dt, and C2 is having 2C capacitance. So dVc2 by dt. So these expression I have. So C into change in the voltage. Change in the voltage is 2 volt. So my answer would be 2C delta T, right? And here 2C into change in Vc2 voltage. What is the change in Vc2 voltage? That is 1 volt. So it will be also 2C delta T. So basically, what will be my waveform for IC? Simply an impulse of 2C. And what does 2C show here? 2C shows here the charge, right? That means we are giving 2C charge to both of the capacitors, right? So this is my IC, that is 2C delta T, or I shouldn't write 2C delta T, I should just write 2C, because this shows the magnitude, this shows the magnitude. So my ICT is 2C delta T. Okay, these questions may look easier to you, but whenever these questions comes in exam, everyone, some tries Laplace transform, some do something. Now everything that can be asked in the exam, we have first seen the complete derivation, whatever the concept, then we have just narrowed it down to one formula. Initial voltage, complete voltage in the circuit, divide in the inverse proportion, that's it. There can be multiple options. First you can solve it by Laplace transform as well. Okay, well and good, very easy method, solve by Laplace transform, you can do that. Another one, you can solve by superposition theorem as well. That's also a good method. How will you solve by superposition? First you will see the effect of voltage V only, then you will see the effect of voltage V1 only, then you will see the effect of voltage V2 only. That's how you will solve by the superposition. So you can try that on your own. Okay, if there are multiple capacitors, if there are multiple voltage sources, so how will you solve? So at that point of time, superposition will be in action. Okay, so you can try on your own by superposition. Maybe in the end of the lecture, or in the end of the complete transient lecture, I can bring those videos. Okay, So, but you should try on your own by the superposition theorem. This method I have told, well and good, right? Easy method. This question also we have solved. We have drawn the waveform. We have also write down the equation of current, right? So this was an easy concept. This concept is called as switch capacitor. Okay. So how the voltage in the capacitor is changing instantaneously. That's what we have studied. Now let's solve this simple problem. You have to find the expression of I1 and I2. Okay. Try doing it on your own first. So tell me, what will be the value of I1 at t? First tell me the order of the circuit and time constant. What will be the time constant? Open circuit the current source. Open circuit the current source. This C1 and C2 will come in series, right? So time constant will be R into C1 C2 upon C1 plus C2. So this will be the time constant, right? This will be the time constant, right? Now what about I1? So let's see I1. I1 at t equals to 0 plus. What is the value of I1 at t equals to 0 plus? What is the value of I2 at t equals to 0 plus? Initially what will happen? This capacitor will be shorted, this capacitor will also be shorted. So simply 5 ampere current, one resistor and a short circuit path. So the complete current will be flowing like this, right? So the complete current will be flowing through the C2 capacitor only. So I2 at t equals to 0 plus would be 5 ampere. And what will be I1 at t equals to 0 plus? That would be 0 ampere. Now what will happen? I think I should write it on next page only. At t equals to 0 plus. At t equals to 0 plus, I1 at t equals to 0 plus was, I1 was 0 ampere because no current was flowing through it, and I2 at t equals to 0 plus was, I2 at t equals to 0 plus was what? 5 ampere, right? What will happen at t equals to infinity? Both capacitor will be open circuited, right? Okay, both capacitor will be open circuited. This is C1, this is C2. Is there any ambiguity? Can you say in both of the resistor, in both of the capacitor, the current will be 0? Can you say that? This is I1 and this is I2. In both of the capacitor, the current will be 0. Can you say that? No, you can't say that. Why so? Because from here we are having 5 ampere current. That's for sure that we are having 5 ampere current here. Here we are having 5 ampere current. So 5 ampere has to be equals to I1 plus I2. You can't say that I1 and I2 both are 0. If both are 0, where is 5 ampere current going? 5 ampere current is coming. This is also 0, this is also 0. So where is 5 ampere current going? So both I1 and I2 are not 0. So what will you do? In case of ambiguity, at t equals to infinity, what is the frequency content? Omega equals to 0. That means Zc is very high. That means what? Series combination of Rc can be replaced with a single capacitor, right? So how will the circuit look like now? Not here, I should make it here only, with a single capacitor. So how will the circuit look like? 5 ampere current source. This series RC will be replaced with a single capacitor C1, right? And this series RC will be replaced with a single capacitor C2. This is 5 ampere current. This is I1 and this is I2. What about I1 at t equals to infinity? 5 ampere current will be divided into C1 and C2 in the proportion, because in case of capacitance the current is divided in proportion. So 5 C1 upon C1 plus C2. And what about I2 at infinity? That is 5 C2 upon C1 plus C2. So what about I1? It is rising from 0 to this value 5 C1 upon C1 plus C2. So if I am writing the expression of I1t, from 0 to it is rising to 5 C1 upon C1 plus C2, 1 minus e to the power minus t upon 2 u of t, with time constant being r C1 C2 upon C1 plus C2. Okay, well and good. What about I2t? It is rising from 5 to some value 5 to some value, that is 5c2 upon c1 plus c2, and it is coming from 5, right? So it is coming from 5. So initially the value has to be 5. So it has to be 5c1 upon c1 plus c2 e to the power minus t upon tau ut. How did I write this expression? Look, if I know the value at infinity, I just need to make sure that at t equals to 0, I need to have 5 voltage. So I know that I will be putting t equals to 0 here. So this would be 1. So I need to write the expression such that this value becomes 5. So I just thought I should write 5 c1 upon c1 plus a2. If it doesn't click to you, you can simply use this formula, y of infinity, y of 0 minus y of infinity e to the power minus t upon 2. But how did I write it? I am telling that thing. Okay. You know the value at t equals to 0. You just need to write down the expression such that it becomes the same value at t equals to 0. Okay. So at t equals to 0, we are getting 5 only. So that's how I wrote it. Okay. Otherwise, you can use the formula. It will take one more step, but it will be the same as this. Okay. So these are the expression of I1t and I2t. Okay. Well and good. I just took this example so that like you understand the concept. In current source as well it can happen. So whenever there is an ambiguity, you will always go with omega equals to 0, omega equals to infinity. Parallel combination of RC will be replaced with the single capacitor in case of omega equals to infinity, and series combination of RC will be replaced with the single capacitor in case of omega equals to 0. Okay. So in case of ambiguity, you will go to this thing. Okay. Well and good. So in the before going to the next lecture, this we will be dealing in the, okay, this is impulse voltage input. Okay. So we will deal this in this lecture only. So we need to see RC circuit with impulse voltage input now. Okay. What will happen for impulse current input? Step, right? If impulse current input is there, we will have a step that we have already studied, right? But now if impulse voltage input is there, so what will happen? So you need to draw the waveform of V0 and IC. Okay. So this is your voltage input. So what is your voltage input? What is your voltage input? This is your voltage input. That is having a magnitude of Vs, right? So what does this Vs shows? This Vs is flux. I have explained this concept, right? Why is it flux? What is EMF? EMF is d by dt, d phi by dt. So EMF into time, voltage into time, voltage into second brings the, what is the flux, right? Voltage into second is the flux. So Vs is the flux. Okay. So what is happening at t equals to 0? At t equals to 0, you can say at t equals to, yeah, at t equals to 0, at not at t equals to 0 plus, at t equals to 0. At t equals to 0, capacitor will be short circuited. Capacitor will be shorted, right? So let me draw the circuit at t equals to 0. This is R, and here we have this impulse voltage, that is Vs delta t. Tell me what will be the value of IC at t equals to 0 plus at t equals to 0. What will be the value of IC at t equals to 0? Vs delta t by R. That means impulsive current. Impulse current. What will happen? This Vs by R delta t current will flow through the capacitor and it will charge the capacitor, right? So what will be Vc value? Vc value from t equals to 0 minus to t equals to 0. From 0 minus to 0 you can write. So Vs by R, because this current is only there at t equals to 0 only, right? So Vs, I will write it in 1 by C ICT from t equals to 0 to t equals to 0 minus to 0 only, delta t. So it would be 1 by C from 0 minus to 0 Vs by R, Vs by R delta t dt. So basically our voltage at t equals to 0 would be Vs by Rc from 0 minus to 0 delta t dt. It would be Vs by Rc. What is the differentiation of delta t? That is sorry, integration of delta t, that is ut from 0 minus to 0. So Vs by Rc u of 0 minus u of 0 minus. Look, you don't really define the value of u of 0, but you can take it as a 1 for now, because the voltage at t equals to 0 and 0 plus would be the same. At t equals to 0 minus, Vc is 0, but at t equals to 0 plus it will be different. So you can take it as 1 for now and this as 0, because u of 0 minus is 0, right? This is Vc 0. What is Vc 0? That is Vs by Rc. So because of the impulse current, it develops some voltage, that is Vs by Rc. Right? We have applied an impulse. Vs by R delta t current is flowing. That means it has developed Vs by delta t, Vs by Rc. Circuit at t equals to 0 plus. What is happening at t equals to 0 plus now? Input is gone. Vs delta t is gone. V in t, that is Vs delta t, will be 0 after t equals to 0, right? That means V in at 0 plus is 0 volt. Input is gone. So now what will happen? This resistor will come, one end of the resistor will be grounded and the other end of the resistor will be connected to the capacitor, but the capacitor is having initial voltage of Vs by Rc. Now what will happen? This is Vc, right? Yeah, this is Vc. Now what will happen? This Vs by Rc voltage will get discharged with time. Vs by Rc voltage will be discharged exponentially. Like we have solved this circuit, right? A capacitor is having V voltage with C capacitance and resistance R in parallel. What will happen? This V will be discharged through this resistor from V to 0, right? So this Vs by Rc voltage will be discharged with the time constant Rc, right? So this Vs by Rc voltage will be discharged with time constant Rc. So finally, what will be the Vct expression? It was 0, then suddenly it rises to Vs by Rc, then it discharges to 0 volt, right? Are you getting my point or not? With time constant Rc, so time constant being Rc. Okay, so basically I want to say Vc infinity would be 0 volt. Vc 0 plus was Vs by Rc, then it discharges to 0 volt. From Vs by Rc, it discharges to 0. What about Ic? Ic was shown like this. Ic was shown like this. So this is Ic. Commenting on Ic. Ic 0 was Vs by Rc, right? Sorry, not Vs by Rc, Vs by R, right? Vs by R delta t you can say, or Vs by R delta 0 you can say, or Vs by R delta t you say. There is one thing only. So initially it is impulsive, then because of this capacitor, the Ic value at t equals to 0 plus is what? Minus Vs by R square C. Are you getting this point? This voltage by the resistance. Vs by Rc voltage by the resistance, that is R. So Vs by R square C. So this is the current, but in the negative direction. Vs by R square C. So this is the current. Then the current goes down to 0. So Ic infinity goes down to 0. So basically what is Ict? Initially an impulse at t equals to 0. Then value becomes Vs R square C and goes down to 0. Right? So this is the expression of Ict. I hope you are getting my point. I will tell you one more method, but in the interview this method should be used. Okay? Other methods I will tell you. Okay, no problem. So for Vct and Ict we will draw the waveforms. So in case of VCT, from 0 to suddenly it rises to some value. Zero initially, then suddenly it rises to this value and then decays down to 0, right? From 0 to it rises to Vs by Rc, then decays down to 0. What about the current? Current, this axis I should have made much better. This I should have made. So initially there is an impulse current that has the magnitude of Vs by R. Not the magnitude, sorry, the area, Vs by R. Then suddenly the current goes down to minus Vs by R square C and then discharges to 0, right? With time constant being tau equals to Rc. This is the time constant, tau equals to Rc. Are you getting my point or not? So this was the one method that we solved without using anything, any Laplace transform, anything, by simply by the concepts. Let's go to the method 2 by Laplace transform. By Laplace transform also you can solve this. So what was your input? Forget about the input. First let's make the circuit. That is the resistance, that is the capacitance, that is 1 by Cs. And now we have the input. Okay, my input was Vs delta t. So simply the input would be Vs only. V in t was Vs delta t. So what will be the Laplace transform of V in t? Laplace transform will be Vs. So Laplace transform would be Vs only. This is I of s. So basically your I of s would be Vs upon, because of the impulse input, it would be simply Vs upon R plus 1 upon Cs. R plus 1 upon Cs. So Is would be Vs Cs upon RCs plus 1. Okay. So I need to break it down. CVS I am taking common and then I am writing S upon RCS plus 1. What I can do, I can multiply and divide with RC. Multiply and RCS it will become. Then I can do plus minus 1. Did you get what did I do here? CVS I took common. Instead of S I wrote SRC and then divided by the SRC. Then I did plus minus 1. If it's a solid, plus minus 1 will be 0. RC and RC will be cancelled. You will get the same expression. So that's how we did. So CVS by RC 1 minus 1 by SRC plus 1. This is your IS. So I can write it like this: CVS by RC minus this RC I can take outward, right? Okay, C and C are getting cancelled actually, right? So I will not cancel it actually. C and C are getting cancelled, so I can write Vs by R minus Vs by R, and I am taking RC common from that. So it would be R square C into 1 upon S plus 1 by RC, right? So now taking the inverse Laplace. Now I am taking the inverse Laplace. This is Vs by R, so it would be Vs by R delta t, right? Now for this, Vs R square C e to the power minus t by RC, ut. What did I do? Inverse Laplace of a constant. What is the inverse Laplace of constant? That is a delta t. What is the inverse Laplace of this value? 1 upon s plus a, that is e to the power minus at ut. This is what I did here. Okay, vs by r delta t minus vs by r square c e to the power minus t by rc ut. Okay, so this is what I did here. Okay, so this was for is. Now for vcs, shall I leave up to you? Vcs, no, I should solve it on my own. So vcs would be 1 upon cs upon 1 upon cs plus r into the input voltage, that is vs only, in Laplace transform, right? So it would be 1 upon rcs plus 1 into vs. So you can write vs by rc into 1 upon s plus 1 by rc. So this is vcs. So what will be in time domain? It would be vs by rc e to the power minus t by rc ut. This will be the answer in time domain. Okay, so this was the method 2. Okay, this was method 2. There is one more method. Let's see method 3. Method 3. So I will just if this is an LTI system is linear time invariant system. I don't actually remember if I have told you this concept of linear time invariant system. I have told you what is linear system, what is time invariant system. That I have told. So if there is this linear time invariant system, so if I am applying a step input, I am getting a step response, right? Now if I differentiate the input, okay, what I am doing, I am differentiating the input. Differentiate the input. So if I differentiate a step input, what will happen? I will have an impulse input, right? Impulse input. So if there is this impulse input, I will, if I am differentiating the input, I can differentiate the output as well. So I will get an impulse response. So are you getting my point? If you know the response for a step input, then you can simply differentiate it and get the response for impulse input as well. Let's just see one thing. This is my R, this is my C. Okay, this is my R, this is my C, and this is V in. This is T equals to 0, 0 to Vs. Okay, what will be my output? What will be my V naught for this input? What will be my V naught? Step response. V naught T would be, it will rise Vs 1 minus e to the power minus T upon tau ut. This will be my final answer, right? Now what I am doing, I am differentiating it. Differentiate. What is the differentiation of a step? That is impulse, right? So I will have an impulse of magnitude Vs. Vs, right? This is my input only. So my V in T would be Vs, not the magnitude, area. Okay, Vs delta T. This is my input. Now for getting the output, what I will do, I will also differentiate here and get my output. Differentiate you will get your impulse response. Impulse response. So what will be my impulse response? Impulse response. What will be your impulse response? Simply it will be d by dt of Vs into 1 minus e to the power minus t upon tau ut. So first as it is, differentiation of the second, plus second as it is, differentiation of the first. Oh, sorry, second as it is. So this value will become delta t only. First as it is, differentiation of the second. So this value, okay, this value will become 0 because 0 you will put here and this will become 1. So this will go to 0. Are you getting my point? Xt into delta t, what is xt into delta t? That is x of 0 delta t, right? If you put 0 in this equation, this will become 0 only. So 0 into delta v will be 0 only. So this is what is happening here. Okay, so this will become 0. So your final response is Vs by tau. Tau is Rc. So Vs by Rc e to the power minus t upon tau ut. Right? So this will be your final impulse response. So this is how also you can solve by the equation. Okay, this is also a good method. Same you can do it with the current. Right? Same you can do impulse response for current. Response for current. Same thing can be done with the current as well. What was the expression of step response? To step response for current. Step response for current. What was the expression? That was Vs for step response. What was the expression? Initially Vs by R, then decays down to 0. Right? Vs by R and then decays down to 0 into ut. Into ut. If you just differentiate it, you will get your final answer. So Vs by R will come in common. First as it is, differentiation of second plus differentiation of this e to the power minus t upon tau by tau ut. Basically Vs by R delta t, because this will be 1, minus Vs by tau is Rc, so R square c e to the power minus t upon tau ut. That is the impulse current response. Impulse current response. F a current response for impulse voltage input. Right? This is also a final answer. Okay. So have you understood all three methods? Right? So in the interview, you will be solving with this method. Okay. Method 1. If the interviewer tells you to solve by this method, that integrate the output or differentiate the output, then you will solve by this method. Okay. And in the exam, you can solve by this method because this will be complete mathematics only. So I have told you all three methods. So I hope you are comfortable with all the concepts that I am teaching. Right? Switch capacitor we have seen. In this lecture, we saw switch capacitor, we saw impulse input, we saw the simple example. Right? What else we saw in this lecture? We saw the slope at t equals to 0 plus. So these three things we saw. Okay, these are very, very important as well. Okay, so in the next lecture will be the last lecture for the concepts, at least for written test and gate students. But for interview, there are few more concepts left that I will add on. Okay, but next lecture will be the last one for the gate aspirant and for written test of interviews. But in the interview, they can ask much more concept from transient. So that concept we will discuss from, not from transient, from RC. From transient, RL is left, RLC is left, LC oscillator is left. So transient is not completed. Only RC circuit is completed. Okay. So From next onward, we will see one more concept, then we will solve many problems, then we will move on to RL circuits. Okay, thank you. Hello everyone. So now we will see RC circuits with the pulse input. Okay. So first we were applying a step input, like it was 5 volt for t greater than 0 always, right? For t greater than 0, 5 volt always. But now what will happen? 5 volt, 0 volt, 5 volt, 0 volt, 5 volt, 0 volt. And now there will be two conditions. That one condition is that the time period is very greater than the time constant. What is the time constant of the circuit? RC, right? So time period is very greater than RC and time period is very less than RC. So there are these two conditions. For both of the condition, we have to analyze the circuit. So first take the first condition, T very greater than RC, then we will take the second condition. Okay. So let's take the first condition, T very greater than RC. That means the time constant is very small. Okay. Time constant is small. So let's analyze the circuit. Given T is very greater than RC. That means time period is very large than the time constant. Like they may not give this condition. What they would do, they will set the value of RC such that, let's assume RC is 2 seconds. They will set the value such that, like they can put R equals to 2 ohm and C equals to 1 farad. So they will put RC equals to such that, and they will put T equals to 20 seconds. Okay. So what will happen? T by 2 will be 10 seconds. So now this 5 volt input remain there for 10 seconds. T by 2 is 10 seconds. That means 5 volt input remain there for 10 seconds. So if RC is 2 seconds, so how much time it will take to stabilize? 5 to time, right? So nearly it will take 10 seconds. So in 10 seconds you will completely get the, in 10 seconds you will completely get the 5 volt. If 5 volt is there at the input, the capacitor will charge from 0 to 5. How much time it will take? Nearly 10 seconds, right? So nearly it will take 10 seconds. So 5 volt will be completely charged. Okay. So this is what we were writing. So I will just write down the value. Okay. Let this thing R equals to 2 ohm, C equals to 1 farad, and RC would be 2 second, and T equals to 20 second. So I will just put it in a box and I will just write this would be given. This would be given. Okay. This thing would be given to you. Now let's analyze the circuit for 0 to T by 2. For 0 to T by 2, what is the value of V in? That is 5 volt. So this is your circuit, right? This is R, this is C, this is your V node, and here I have 5 volt. Here I have 5 volt. So now what will happen? The capacitor will charge to 5 volt. Since T is very large, the capacitor will have enough time. The capacitor will have enough time to get charged to 5 volt. So for 0 to T by 2, what will happen? The V naught value will rise to 5 volt, right? So this is what will happen. You don't know the exact time it will take, but we can make the approximate graph. So here our target is just to make the final graph, not to analyze the circuit, not to numerically analyze the circuit actually. For numerical, to realize the circuit numerically, we will solve some problem in the next video only. So we will solve assignment, there you will solve the numerical problem as well. Okay. So here we are just understanding the concept. So from 0 to T by 2, it is charged to nearly 5 volt, right? So just take T by 2 and it is charged to 5 volt. Now what is happening? The capacitor is charged to 5 volt. Now for t by 2 to t, what is happening? V input is 0, right? The input is gone. This input is gone. Input is 0, and the capacitor is already charged to 5 volt, because here Vc at t by 2, it will be 5 volt, right? So Vc at t by 2 would be equal to Vc at t by 2 plus is 5 volt, but the input is gone. But input is gone. That means there is no input. So how will the circuit look like? One end of the resistor will be connected to the ground. One end of the resistor is connected to the ground, and the other end is connected to the capacitor. And capacitor is already charged to 5 volt. And this we are calling Vc or V naught. Whatever we are calling that V naught. V naught. So now what will happen? This 5 volt, this capacitor will get discharged through the resistor. So the capacitor will get completely discharged. Why completely? Completely discharged because T is very large. Because T is very large. So the capacitor will get completely discharged. So it is already charged to 5 volt, then it will be discharged to 0. So from 5 to 0 it will go. Right? I hope you are able to understand the concept. It was charged to 5 volt. From 5 volt to 0 volt it is discharged. Now what will happen? For 3t by 2 to for 3t by, not for 3t, sorry, for t to 3t by 2, for t to 3t by 2, for time t to 3t by 2, what will happen? First thing is that Vc at t is 0, that would be equals to Vc at t plus, or V naught you can say. So now the capacitor is having 0 voltage, and again V in is 5 volt, right? So again this circuit is there, RC with capacitor having 0 voltage, right? And here we have 5 volt. Now what will happen? The capacitor will again charge. Capacitor will again charge to 5 volt. So what will be the value of Vc at 3t by 2? It will be charged to 5 volt, right? And what will happen for 3t by 2 to t? Or 3t by 2 to t? V in is 0. Initial capacitor voltage is 5 volt. The capacitor will discharge to 0. The capacitor for 3t by 2 to t, capacitor is charged to 5 volt, input is gone. Input is gone. So what will happen? This 5 volt will be discharged through the resistor to 0 volt. So the capacitor will discharge to 0 volt. So 0 volt. And this cycle goes on, right? 0 to 5, 5 to 0, 0 to 5, 5 to 0. So this cycle goes on. Goes on. So how will the final graph look like? So I will make input, output, both of them on one graph only. Okay. So let's first make the input. So V in and V naught both are there. Okay, V naught with green pen. Okay, V in and V naught both will be there. And this is the time. This is T by 2. This is T. This is 3T by 2. This is 2T. This is 5T by 2. This was 5 volt. So what is actually happening? It is charging from 0 to 5, then discharging to 0, discharging to 0, then again charging from 0 to 5, then again discharging to 0, then again charging and again discharging, right? Again discharging, right? And this cycle goes on, right? This cycle goes on. And what is the time constant? Time constant here is RC. Tau is RC, right? So this is the final output waveform. Okay. So now there are two more methods to analyze the circuit. Okay, two more methods are there. One would be the with the concept of low pass filter. Okay, and integrator concept. So all these concepts are there, but that is out of the scope of gate aspirant. Okay, you don't need to dive that much into network analysis only because you have 10 more subjects to study, right? So that is out of the scope of gate aspirant. So I am not teaching that here. For placements guide, that is very necessary. Okay, placement students, like for internship and placements, companies do expect that you know that analysis. Okay, so for them I will make a separate video and add that part in the course only. Okay, so, but for gate aspirant, that is out of the scope. You will be asked to solve the question. If you know this analysis, you will be able to solve the problem. Okay, and if you are a gate aspirant and very much interested in knowing those methods, then you can go to the placement playlist. There you will find. Okay, I have also uploaded that on YouTube as well. So from YouTube as also you can find that. But for that, you first you need to know the Fourier series concept. Then you need to know what is filters, what is the Bode plot, how do you draw the frequency response. After that, you will be able to analyze the circuit. So once I teach all these things to placements guys, then I will teach them that method. Okay, so all these things you will study in signal system and control system. So placements guys should study that method, but gate aspirant don't need to focus on that method much. Okay, so whatever the circuit that I am dealing, first I have uh, told the concept of T very greater than RC, then I will tell the concept of T very less than RC. So all these questions can be solved with some other method as well, that I will not be telling here, but in some separate video I will be telling that. Okay, so let's see the second condition, T very less than RC for the same input. Okay, so this is the condition given, T very less than RC. So let's just assume RC is some 2 seconds. Okay, RC is some 2 seconds. So how much T you would expect? T is some 0.2 second. Okay, very less. So that means let's just assume first you apply 5 volt, but that is applied only for 0.1 second. Okay, T by 2 would be 0.1 second. So 5 volt is applied only for 0.1 second and the time constant is 2 second. So what do you think? What will happen? Will it charge to 2 volt? No. Sorry, will it charge to 5 volt? No, it will charge very less. Okay, we shouldn't write 0.2 second. That would be very less. Let's just write T equals to 2 second. Okay, that is T equals to RC. That would be, let's just write T equals to 1 second. Okay, so T by 2 would be equals to 0.5 second. So what will happen? So in 0.5 second, it will not be charged to 5 volt completely, because what will happen? VCT would try to go up to 5 volt. The equation will be something like this: 5 into e to the power minus t upon tau. Now tau is your RC, but at t by 2, what will happen? E to the power minus t by 2. What is t by 2? 0.5. And what is time constant RC? That is 2. So it will gain only this much value, this much of value. So let's just calculate what is this value. So 0.5 by 2 plus minus e to the power plus minus minus 1 into 0.5 by 2 e to the power, let me solve it. So after solving it, we will get around 1.1 volt. So it wanted to charge up to 5 volt, but it is charged to only 1.1 volt only, right? Because the time given is very, very less. So are you getting my point? So this is what we are going to write. This thing would be given to you, would be given. Okay. So now see what will happen. For 0 to t by 2, V in is 5 volt, right? And time t is less than RC. So what will, oh. Yeah, so what will happen? This is R, this is C, this is R, this is C, this is 5 volt, this is V naught. Okay. Now since t is less and time constant is large, is large, the capacitor will try to go up to, the capacitor will try to charge up to, capacitor will try to charge up to 5 volt, but will not be able to reach there, be able to reach there. Now depending on the values of T and RC, depending on the values of T and RC, T and RC, let VC T by 2 is 1 volt. Okay. Although we calculated here in the previous analysis that VCT is 1.1 volt, right? VCT by 2 is 1.1 volt. So let's just assume it is 1 volt. Okay. So the capacitor started to charge, but it didn't get charged to complete 5 volt. It is charged to 1 volt only. So we are making the V0 waveform. Okay. The capacitor will try to charge, but it is charged to 1 volt only. Okay. Like it was trying to go here, it was trying to go like this, but it is charged to only 1 volt. So actually I can't, I have to make it something like this only. It was trying to charge, but till this point only it is charged. So it is charged to 1 volt. Okay. Charged to 1 volt till T by 2. Okay. One more thing I want to write. What is IC at t equals to 0 plus? What is IC at t equals to 0 plus? Tell me. At t equals to 0. 5 by R, right? 5 by R. Okay. Because initially capacitor is having 0 volt and here 5 volt is there. So 5 by R current is there. Why did I write this? You will know later on. Okay. Let's just make the waveform. So V naught is charged from 0 to 1 volt. Now what is happening? For 0 to, for t by 2 to t, for t by 2 to t, V input is gone, that is 0 volt. Now what is the voltage across the capacitor? That is 1 volt. So what is the circuit now? This is the resistance, this is the capacitor that is already having 1 volt. Now this will charge to discharge to, this will try to, this 1 volt will try to discharge to 0 volt, but since time is very less, since t is very less, capacitor will not be able to discharge to 0, will not be able to discharge to 0. Actually tell me what will be the equation of capacitor voltage? It is going like this, I should, yeah, okay, fine. So what is the what will be the voltage? 1 into e to the power minus t upon tau. So how much time it is getting? It is getting t by 2 to t time. From t by 2 to t time, that means it is getting 0.5 second, right? It is getting 0.5 second. So in 0.5 second, and what is the time constant? That is 2 second, right? Time constant is 2 second. So from 1 to, it is trying to discharge to 0, but it is getting the time window of, this would be the equation, right? It is getting the time window of only 0.5 second and time constant is 2. So that's why I wrote this equation. So let's just see what will be the answer. So 0.5 by 2 plus minus e to the power. So nearly it is 0.8 volt. Okay. So it is discharging. Let's first from 0 to 1 volt it is charged. Now it will discharge from 1 to 0. Sorry, it will try to discharge from 1 to 0, but it is not getting discharged to 0. It is getting discharged to some value that is 0.8 volt. Okay. But will not be able to discharge to 0. So let's just assume Vc at t would be 0.8 volt. Okay. So let's just make the waveform. This is your V naught versus time t. At t by 2 plus it was 1 volt. Okay. At t by 2 plus it was 1 volt. It was 1 volt. Now from 1 to it is discharging to 0.8. This is t by 2 and this is t. This was 1 and it is discharged to 0.8 volt. Okay. And the time constant is RC. Now just tell me one thing. IC at t equals to t by 2 plus. What is IC at t equals to t by 2 plus? Like this I am calling IC. Let's just call this one as IC2. Okay. This is IC2. What was IC1? Let's just call this was IC1. So this is the discharging current. What is the value of discharging current at t by 2 plus? That is 1 by r, right? So this is 1 by r. Why am I writing this? You will get to know later on. So what did we see? First it is charged from 5 to, so from 0 to it was going to 5 volt but could go to up to only 1 volt. Then from 1 to it was trying to go to 0 but could go up to only 0.8 volt. Now it is having Vc at t is 0.8 volt. Okay, this is already written here, so I don't need to write. Now what is happening for t to 3t by 2? For t to 3t by 2. For t to 3t by 2. Your V in is again 5 volt. Now your capacitor is already having some voltage. What is that voltage? That is 0.8 volt. What is the difference in this analysis versus the previous analysis? In the previous analysis here, your VCT was 0 volt. 0 to 5, 5 to 0. 0 to 5, 5 to 0. But now you are having some initial voltage here. Now you are having some initial voltage. Okay. So what is the circuit now? This is the capacitor. This is the resistance. It is having 0.8 volt and this is 5 volt. You need to draw the V0 waveform. Okay. Now what will happen? It will try to charge, right? The capacitor will try to charge. The capacitor will try to charge but can't reach up to 5 volt. Up to 5 volt. 5 volt. Now what is the equation actually? Initially 0.8 voltage, right? And steady state it is trying to go to 5 volt, right? E to the power minus t upon tau. Initially at t equals to 0 we have 5 volt, 0.8 volt and steady state it is trying to go up to 5 volt but since the time is very less, what is the time? Time is t to 3t by 2, that means only 0.5 second. And what is the time constant? Time constant is 2. So it will try to go down. So how much down it will go? Sorry, 0.82 it will charge, but till what point it will charge? 0.5 by 2 plus minus e to the power into 4.2 minus 5 plus minus 1.72. Yeah, so now what will happen? The capacitor will charge from 0.8 to some voltage. Now whatever the value we get after solving, we don't care much about it. Let's just assume we got the value Vc at 3t by 2 plus. From 0.8 it is charging. Let's just assume we go to 1.5 volt. Okay. So the same thing is happening here, but the difference is that it is not getting charged up to complete value. Okay. So don't just skip the video. One twist will come. Okay. There will be one twist that I will be explaining because I am writing the value of current, right? So tell me what will be the, let's just call this current as IC3. So IC3 at t equals to t plus. What is the value of current? 5 minus 4.8, 5 minus 0.8 by R. So 4.2 by R current. Initially when the circuit is starting, the current is 4.2 by R, right? And now it is charging from 0.8 volt to some voltage that is 1.5. We have considered let. It will charge to some value that would be 1.5, 1.6 that we don't know. But let's just assume it is charged to 1.5 volt. Okay. So it is charged to 1.5 volt. That's where it is charged, right? This is T, this is 3 by 2. So what is happening? First it is charging, trying to charge to 5 volt but getting charged up to 1 volt. Then it is discharging, trying to discharge to 0 volt but getting discharged up to only 0.8 volt. Then again charging, trying to go up to 5 volt but again charged up to only 1.5 volt. Now what will happen? Again it will try to discharge to 0 but cannot discharge to 0. It will try to go down to 0 but will remain at some voltage only. Okay. So for 3t by 2 to t, for 3t by 2 to t, V input is gone and Vc at 3t by 2 plus is your 1.5 volt. So now what will happen? It will try to discharge. This is the capacitor, this is the resistance, this is the capacitor, this is 1.5 volt. Okay, this will discharge. Let's just call this as IC4. So tell me what is the value of IC4 at t equals to 3t by 2 plus. What is the value? That is 1.5 by R. Okay, will Vc will try to go till 0 voltage but cannot reach there, but can't reach there, right? So let's just assume Vc at t equals to t plus. What should, no, not t plus, at t only. So what should we assume? So till where I should let it discharge? Let's just assume it is discharged to 1.3 volt. Okay. How much, till how much it should discharge? 1 point. We don't know the exact value. We are not considering the value as well. We are just making a rough waveform. Okay. For numerical example, we will see examples. So there you will understand. But now the understanding the concept is important. So let's just assume it is discharged to 1.1 volt. So what is happening here? From 1.52 it is discharged to 1.1 volt. This was 1.5 volt and discharged to, this was 1.5 volt, it discharged to 1.1 volt till here. This is your V naught. This was 3t by 2 and this is your 2t. From 3t by 2 to t, why I am writing t? It is 2t. From 3t by 2 to 2t. It is discharged to 1.1 volt. And this I should have written here. Now tell me, what is this? This is a discharging current, right? This is, what is happening? So what I was saying, this is a discharging current, right? Because the capacitor is discharging. So this is discharging current. What about this? This was charging current, because here the capacitor was charging. So this was charging current, right? Look, the concept may seem complex to you, but it is very important to understand. Okay, I'm not gonna teach you easy things and then tell you, look, I teach very well. A real teacher is the one who teaches tough thing in a very easy manner. Okay, first thing is that in gate industry no one teaches these concepts, and if you go to previous year questions, these kind of questions are asked, and anytime in the future they can ask these kind of questions. Okay, so my duty is to teach you everything in a comprehensive manner and by making it easier. Okay, I'm not writing so much of equations or anything that makes it complex. I'm trying to break it down to very low levels, right? So this is charging current. So tell me, what is the thing that you are noticing? So first, it is charging from 0 to 1 volt. The initial charging current was 5 by R. Then when it was charging from 0.8 to some voltage, the charging current was 4.2 by R. Now the capacitor has discharged to 1.1 volt. Now for further cycle, for for 2t to 5t by 2, what will happen? What will be the value of charging current? Tell me. It will be 5 minus 1.1 by R, right? Because here I have 5 volt and here I have 1.1 volt. So the charging current would be 3.9 by R, right? 3.9 by R, right? Let from 1.12 it is getting charged. So let's just assume the capacitor is charged to 1.6 volt. Let capacitor charges from, now the capacitor will charge from 1.1 to some voltage, right? 1.12 it will try to go up to 5 volt, but let's just assume the capacitor charges from 1.1 to 1.6 volt. So this was the charging current from 1.1 to 1.6 we are assuming. Okay, so now what will happen? For 5t by 2 to 3t, what will be the discharging current now at 5t by 2? Because the capacitor is having 1.6 voltage, so the discharging current would be 1.6 by R, right? This would be the discharging current. So my point is, what is actually happening in charging current? Initially it was, when it started it was 5 by R. Then what happened? It went down to what value? First it was 5 by R, then it went down to 4.2 by R. Then here it went down to 3.9 by R, right? So the charging current is getting reduced. What is happening with discharging current? What is happening with discharging current? Tell me. First it was 1 by R, because it was only charged to 1 volt. It was 1 by R. Then the capacitor was charged to 1.5 volt, so it was 1.5 by R. Now the capacitor was charged to 1.6 volt, so it is 1.6 by R. So what is happening here? Slowly the charging current is getting increased. Now tell me, in the next cycle what will be the charging current? 4 minus 1.6, that means 5 minus 1.6. What is the value? Okay, here if it is 1.5, okay, so we don't really know, like now 1.6 will also discharge, right? At this time at 3t we are having 1.6 voltage, and this is the resistance, so this 1.6 will also discharge. We don't know till what value it will discharge. Let's just assume it is discharged to 1.4, so the current would be 5 minus 1.4, that means 3.6 by R, right? So again the charging current is getting reduced. So with the continuous cycle, with the continuous cycle, with the continuous cycle charging current is getting reduced, charging current is reducing and discharging current is increasing. With continuous cycle, this charging current is getting reduced and discharging current is increasing, right? So at some time charging current would be equals to discharging current. Charging current would be equals to discharging current, and that we will call steady state. So what will be that value? That value will be 2.5 by R. Are you getting my point? When your capacitor is charged to 2.5 volt, at that time when your capacitor is charged to 2.5 volt, let's just assume this is our circuit. This is RC. Okay, RC. Same input is there. Same input is there. First it is 2.5, then it goes to 0, then again 2.5, then again goes to 0. Okay, from 2. So not 2.5, sorry, 5 volt, 0 volt, 5 volt, 0 volt, because this cycle keeps on coming 5 0 5 0 5 0. Now this is charged to 2.5 volt, right? So this is the charging current, this is the discharging current. When V in is 5 volt, what will be the charging current? Charging current would be 5 minus 2.5, that would be 2.5 by R. This is the charging current. And when V in is 0 volt, what will be the discharging current? That would also be 2.5 by R. That would also be discharging current, right? So this is what we call, this is the steady state. Steady state. So if they can ask you in this complete analysis, what will be the VC value at steady state? VC value at steady state, that would be 2.5 volt, not 5 volt. Okay, in an RC circuit there is an input that is applied, that is square wave input. Okay, square wave input or pulse input 5050, but at the given time, this time period is very less than RC. In this case, if they are asking what is the steady state value of the capacitor voltage, it will not be 5 volt, it will be the average value of the input. Okay, the average value of the input is, what is the average value of this input? This input, that is 5 by 2. Okay, so the steady state value is 2.5, not 5 volt. Are you getting my point or not? I hope you have understood. Let's make the waveform now. Okay, so this will be our final waveform. What I will do, I will just copy. So this is our input. So how will the output look like? First it will try to charge, will charge up to only 1 volt. Then it will discharge, will try to discharge, but discharge up to 0.8 volt only. Then again it is charged, will try to charge, let's just assume it is charged to 1.5 volt. Okay, here it is charged to 1.5 volt. Then it will try to discharge, let's just assume it is discharged to how much voltage, I don't remember, from 1.5 to 1.1. It is discharged to 1.1 volt. Then again it will try to charge, again discharge. So that's how the cycle will go on. Okay, and at steady state, the average value here would be, the average value will be at steady state, average value will be 2.5 volt. This will be 2.5 volt. Okay, this is the steady state. Are you getting my point? So this is the complete analysis of this second configuration. No, the configuration is the same, but the condition is different. The condition is T very less than RC. So in exam, it is not asked yet, but they can ask anytime. Okay, so for gate aspirant it is very very important. So we just need to know what is the steady state value. Okay, so let's just write it down in the conclusion. So what is the conclusion? RC circuit is given to you. Okay, RC. This input is applied. This input is a periodic signal. Okay, so if they are asking what will be the steady state value of V naught, that would be the average value of the input. Okay, and what about the current? What is the IC average at steady state? IC average at steady state. Tell me what will be the IC average at steady state? At steady state, what will happen? Charging current is 2.5 by R, discharging current is 2.5 by R. So 2.5 by R minus 2.5 by R. Are you getting my point? I have made two diagram here. If I had just made this, so what is the charging current? 2.5 by R. What is the discharging current? That is minus 2.5 by R. So plus 2.5 by R, then minus 2.5 by R, then plus 2.5 by R, then minus 2.5. What is the average value of this? That is 0 ampere. Right? So at steady state, the average capacitor current will be 0. At steady state, average capacitor current will be 0. So the capacitor can be considered as a open circuit. I will repeat the statement. At steady state, average capacitor current will be 0. Average what is there? Okay, the capacitor current is not 0. Capacitor current is 2.5 by R minus 2.5 by R. 2.5 by R minus 2.5. If you take the average of this waveform, what will be the average of this waveform? This plus this by time. So this is equal, so total average will be 0. So at steady state, total average current through the capacitor will be 0. So the capacitor can be considered as a open circuit. Okay, so this capacitor can be considered as a open circuit. So IC average will be what? It will always be 0 volt. So tell me what will be the VR average voltage? VR average at steady state. What will be VR average at steady state? If the capacitor current is 0, that means the same 0 current is flowing through the resistor R as well. So it will also be 0 volt. This will be 0 ampere. Okay, and this will be 0 volt. Are you getting my point? At steady state, there is average 0 current is flowing through the resistor, right? Because it would be VR average would be IC average into resistor R. So if this is 0, this will also be 0 volt. Okay, so at steady state, what will happen? At steady state, what you can do, you can simply replace the capacitor with the open circuit. But the logic is at steady state, the average capacitor current is 0. That's why we can replace this as a open circuit. Okay, so this capacitor can be replaced with the open circuit, and this is the input applied. So whatever the average value of the input is there, the same average value will be reflected at the output. The same value will be reflected at the output. So I just assume this question is surely going to be asked in some time in gate examination or in written test, that they will ask average, some waveform they will give, and they will ask what will be the output average voltage. So what you need to do, you just need to find the average of the input voltage. The same voltage will be appearing across the capacitor. Are you getting my point? I hope you have understood the point. Okay, so I guess I can write a question. Okay, so let me pause it and I will write a question. Okay, so this is the question given to you. CR circuit is given. Okay, you have to find the steady state value of the capacitor voltage and the resistor voltage. Okay, this. So at steady state, what will happen? IC average would be 0 ampere. right? So this is the input. The capacitor can be considered as a open circuit. This is a resistor, right? And this is your VR average. Okay, this will be your VC average, right? And this is your input voltage. So tell me, what will be the value VC average value? VC average would be, since it is open circuit, there will be no current through the resistor as well. So VC average would be simply equals to V in average at steady state. Oh, everything is happening at steady state. So VC average will be equals to V in average. What is the average value of the input? Average value of the input is 10 into t by 3. For t by 3 time it is 10, and for rest of the time it is 0, divided by time period. In one time period you need to see, it is 10 for t by 3 time and it is 0 for 2t by 3 time, right? 0 into 2t by 3. For t by 3 time it is 10, for rest of the time it is 0. So 10 into 2 t by 3 plus 0 into 2t by 3 divided by time period. So it would be 10 by 3 volt. So this is your answer for VC average. And what is VR average? VR average is 0 volt, right? VR average would be 0 volt because the current through the average current through the resistor is 0. So VR average would be 0 volt. So here we have 0 volt, here we have 10 by 3. So 10 by 3 volt will be the final answer. Are you getting my point or not? These kind of questions they may ask, and everyone think that it will charge up to 10 volt. The capacitor will charge up to 10 volt. But in reality, the capacitor will not charge up to 10 volt. It will have a steady state value of 10 by 3 volt only. Okay. So this is the final answer. So I hope you have understood the concept that I am trying to deliver here. Okay. Let's move on to the next circuit. This is a very simple circuit. Current source is given. You need to draw the VC waveform. You need to draw the VR waveform. Okay. Just two waveform you need to draw. Okay. I haven't written here. VC and VR you need to draw. This is an easy question. You should try it on your own. What will happen? This same current IS would be flowing through the capacitor forever, right? The same current IS would be flowing through the capacitor forever. So this resistance R makes no impact in capacitor voltage. We have seen this question, right? In practice problem, when there was some current was flowing, the capacitor was getting charged. Then some other current was flowing, the capacitor was getting discharged. So the resistance has no impact, right? So let's just solve the problem. This is the current source you have. Then you have a resistor. Then you have a capacitor. Resistor and capacitor. This is your VC and this is your current source, right? IS we are calling, right? IS. So this is the current source only. I guess I can copy it here. This is the current source. The same IS current is flowing through the capacitor forever, right? IS current flows through the capacitor and resistor forever. That means what? Constant current is flowing through the capacitor. Constant current is flowing through the capacitor. So what will be VCT? VCT would be 1 by C integration IS dot dt. From some time, from any time, we just don't know. Let's assume I'm writing from 0 to time t. Okay. So first it will linearly charge. When there is no current, it will stay there. When there is another current, it will charge, then stay there, charge, stay there. Okay. So let's see by one cycle. And I have also given t is equals to RC. Okay. So for 0 to t by 2, what is the capacitor current? That is 1 by C integration IS dot dt from 0 to some time t. So 1 by C. What is the value of Is? That is 0. Sorry, I naught from 0 to t. So it would be I naught t by C. That would be your VCT. Okay. So what is your VCT? VCT is linearly charging from 0 to some value, right? From 0 to some value it is charging. This is your VCT. Till t by 2 it will charge. From 0 to t by 2 we are. What will be this value? So what will be VC at t equals to t by 2? It would be I naught t by 2 C. What is the value of t? Given t is equals to RC. This is given. T is equals to RC is given. So I can put I naught into RC by 2C. So it would be I naught R by 2. From 0 to I naught R by 2 it will charge. Now what will happen? This is already charged to I naught R by 2. For t by 2 to t. For t by 2 to t. For t by 2 to t. What will happen? Is is 0 ampere. So input is gone. Now what is the circuit? This is a resistance R. The capacitor will hold its voltage, right? The capacitor is holding its voltage. The input is gone. There is no input. The input is gone. So there is no input. The capacitor is holding its voltage. What is the voltage the capacitor is having? That is I naught R by 2. I naught R by 2. Now, what is the current through the capacitor now? Input is gone. One end of resistor R is open-ended. It is open circuited, not connected to ground. So you wouldn't say that I naught R by and I naught R by 2 voltage will get discharged. No, the voltage will not get discharged because one end of resistor is open-ended. So it will not discharge. Since it is open-ended, there is 0 ampere current flowing through it. Right? So the current is 0 ampere. If it was grounded, then we would have said that capacitor will discharge through the resistor. But since it is open circuited, that means there is 0 ampere current. So the capacitor will neither discharge nor charge. Capacitor will neither discharge and nor charge. Right? So what will happen to VC voltage? It will remain at I naught R by 2 only. Right? From T by 2 to T, it will remain at I naught R by 2. Right? Because the capacitor is neither getting charged nor getting discharged. For T to 3T by 2, what is happening? VC at T is already I naught R. Now the current is 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 I naught ampere. Now the current is there, right? Sorry, it is not I naught R by 2, it is I naught R only. It is I naught R by 2. It is R naught R by 2. This is already I naught R by 2. Now again, this same current is flowing through the capacitor. So again the capacitor will charge. I naught current is flowing through the capacitor. So the capacitor will charge. Capacitor will charge. So how it will charge? Capacitor will charge. I can write down the equation. ICT would be initially you are having how much voltage? Not ICT, what I am doing, VCT. VCT. What will be VCT? Initially I am having I naught R by 2 voltage, then from T to 3T by 2, right? From T to 3T by 2, so I will write some time T. From T to 3T by 2, I am having 1 by C integration I dot dt. So it would be I naught R by 2 plus I naught by C T minus T. Okay. So it will be I naught R by 2. This would be the equation. Okay. Simply it will charge linearly. Okay. And if I want to know what will be the voltage at 3T by 2, VC at 3T by 2. What will be VC at 3T by 2? So it would be I naught R, I naught C, 3T by 2 minus T. It would be T by 2. T is RC. So if T is RC, so it would be I naught R. So in first cycle, it reaches from 0 to I naught R by 2. So it develops I naught R by 2 charge. So let's just make the complete waveform. So what was happening? Initially from 0 to T by 2, it is I naught R by 2. Then it is constant, right? From 0 to T by 2, it is developing 0 to T by 2, it is developing I naught R by 2 voltage, right? This is VC. Then from T by 2 to T, it is constant. Then from T to 3T by 2, it is developing again more I naught R by 2. So from I naught R by 2, it is developing till I naught R. Till this is 3T by 2, right? Then what will happen for 3T by 2 to T? It will again remain constant. Then what will happen after that? Again it will charge 3T by 2 to T. Again it will charge, and how much voltage it will develop? I naught R by 2, right? This voltage developed is I naught R by 2. Here how much voltage was developed? I naught R by 2, right? So even if there is some initial voltage, that's not a matter of concern if there is constant current. So this constant current will give the capacitor I naught R by 2 amount of voltage. So in T by 2 cycle, it is giving it I naught R by 2 amount of voltage. In the next T by 2 time, it is giving it I naught R by 2 amount of voltage. And here for this time, it is remaining at the same voltage because input is gone. Okay. So again what will happen? Again it will charge. Again it will charge. Then it will remain constant. Then again it will charge. So the cycle will keep on repeating, right? So in the exam, what they can do, they can ask you questions like, what will be the capacitor voltage after 3 cycle? So tell me, what will be the capacitor voltage after 3 cycle? So in every cycle, it is developing I naught R by 2 voltage, right? Like this will be 5T by 2 and this will be 3T. So in one cycle, it is developed I naught R by 2 voltage. In another cycle, it has developed more I naught R by 2 voltage. And then in another cycle, it has developed more I naught R by 2 voltage. Right? So in every cycle, it is developing I naught R by 2 voltage. In every cycle, capacitor is developing I naught R by 2 voltage, right? So capacitor voltage after n cycle, capacitor voltage after n cycles of input, that would be n I naught R by 2, right? So they can ask you what is the capacitor voltage after 10 cycle. So your answer would be 5 I naught R. then they will give you some value of R, they will give you some value of C. So this kind of question they can ask in two marks, right? Charge constant, and linear charging is there. Okay. Now the next is VR waveform. Let's just comment on VR waveform. What do you think? What will be VR waveform? It will be the same as input. Why so? Because voltage across the resistance is always I naught R, right? This is the current. This is VR. Okay. This IS current is always flowing through the resistor, so your VR would be IS into R, right? So your VR would be IS into R. That means how will your VR waveform look like? It will be the same as the input waveform. This waveform, it will be the same as this waveform, right? What different will happen? Only the current will be replaced with the VR. So what I will do, I will just replace this IS to VR, and I will just write I naught R, I naught R, and I naught R. Okay, are you getting my point? The same input current multiplied with the resistor, so that would be VR voltage. Okay, and if someone asks you what is VS voltage, this is the VS voltage, this is the VS voltage. If someone asks you what is the VS voltage, that will be the addition of VR and VC. So you can just add them up, right? This waveform plus this waveform. So it will start from I naught R. It will start from I naught R because initially VR is I naught R. Then it will rise to 3 I naught R by 2. Then again it will come down to I naught R by 2. Are you getting my point? For 0 to T by 2, what will happen? For 0 to T by 2, I naught R plus this waveform, I naught R plus this waveform. So from I naught R2, it will charge to 3 I naught R by 2. For T by 2 to 3 by 2, for T by 2 to T, what will happen? This is 0 plus only this voltage, that is I naught R by 2. So from I naught R to 3 I naught R, it will charge, then it will come down to I naught R by 2, then remain there. Then what will happen? This waveform plus this waveform. Then you can draw the waveform. Okay. Are you getting my point? Shall I draw the waveform? Okay, I will draw the waveform on my own. What will be the VS waveform? How will your VS waveform look like? Let's understand it directly. So initially the resistor will be having I naught R voltage. Okay. So initially this resistor is having I naught R voltage, and the capacitor will develop more I naught R by 2 voltage. So from I naught R2, we will reach till 3 I naught R by 2. 3 I naught R by 2. Right? Then what will happen in the next cycle? Input is gone. So the voltage across the resistor is gone. Right? So voltage across the resistor is gone. So VS voltage will be only with equals to the capacitor voltage, and that is I naught R by 2. Wait. That is I naught R by 2. So it has come down to I naught R by 2. Now what will happen? Again, the capacitor is having I naught R by 2 voltage, and the resistance is having I naught R voltage when input is there. So I naught R plus I naught R by 2. That means it will start from 3 I naught R by 2. I naught R by 2 plus I naught R. So it will again start from 3 I naught R by 2, and the capacitor will again develop more I naught R by 2 voltage. So the waveform will go something like this. You have to use your brain. Okay, if you are just watching the lecture and just thinking that everything will be in my mind, so I guess I'm not a good teacher for you. You should move on to some other lectures, because there they will teach you easy things and you will think that I know everything. But in the exam, teachers going to ask these kind of questions. Okay, and then it will be a problem. So again, from 3 I naught r by 2, it is developing more I naught r by 2 charge, so it would be 2 I naught r. Right, now what will happen? The capacitor is having I naught r voltage, and input is gone, so the resistor voltage is gone, so only I naught r voltage will be there, so it will drop down to I naught r. So it will drop down to I naught r. Okay, so these kind of waveform will go on. So it will drop down to I naught r and will remain there for next cycle. Okay, so in exam, what they can ask? They can ask you these questions, that what will be your Vs voltage at t equals to 30 by 2. 30 by 2 plus. They can ask you what is the Vs voltage at 30 by 2 plus. That is V naught R. Okay. Sorry, I naught R, not V naught R. I naught R. Okay. So this cycle keeps on going. Okay. So I hope you understood the concept. Well and good. Right. What is happening? Very easy. This question is very easy. This is not tough actually. Like capacitor current, you can see linear charging is there. Charge constant, charge constant, charge constant. In case of resistor, same as the input voltage, same as the input current, same value. That's it. Now they can ask you these questions, like what will be the Vs voltage at 5t by 2, 5t by 2 minus. So Vs voltage at 5t by 2 minus would be equals to the resistor voltage at 5 to, like they can ask you Vs at 5t2 by 2 minus. So what you will do? I naught r 5t by 2 minus I naught r plus what is the uh, what is Vc at 5t2 by minus, that is 3 I naught by r plus 3 I naught by r. So your answer would be 5 I naught r by 2. So that would be your answer. These kind of questions they can ask in the written test. Okay, or in the gate examination. So I hope you will be able to answer every question. No matter how much tough question they ask, you will be able to answer that. Right? Every tough question you will be able to answer. Why so? Because we have understood the concept very deeply now. Right? So let's just see if there are some concepts left. Yeah. So this concept will be used in the further analysis, initial value theorem and final value theorem, and then we will see one more question. So that's it. Like these much concept is necessary. Like these much concept will be sufficient to answer every written test question, no matter how much tough they ask. We have seen a lot of questions. We have seen a lot of concept. So I hope you are comfortable with transient analysis very deeply now. Now we will see RL circuit in 1 or 2 lecture only, because it won't take much time, because we have studied RC so deeply. RL we will be able to do it very quickly. The same thing that is happening in the RC, the same kind of thing will be happening in RL. Okay, so let's just see this thing. So there is this thing called initial value theorem and final value theorem. You will be studying this theorem in signal system as well, in control systems as well. Okay, so this is a very important theorem. So let's just first study what is initial value and what is final value. So this function is given to you, ft equals to 1 minus at ut, and they are asking write down the initial and final value of this function. So what is the initial value? Initial value means we need to find the value at t equals to 0, right? Initial value means t equals to 0 plus I can write or t equals to 0. Okay, so this is what initial value means. I hope you have already guessed it, right? This is the initial value. So f of 0 plus, just put at time t equals to 0. So 0 and u of 0 plus. The value would be, this would be 1, so 0. Okay, and what will be the final value? Final value means steady state value. Okay, final value or steady state value, or DC value also we can say sometimes, DC value. That means t equals to infinity. F of infinity, that would be 1 minus e to the power minus a into infinity u of infinity. U of infinity will always be 1, so it would be 1. Okay, so 0 and 1. But now if something is given in Laplace transform, let's just assume fs is written, not fs, capital Fs, capital Fs is written as s plus 3 upon s square plus 2s plus 1. Now they are asking what is the initial value of this function. So what you can do, you can convert this Laplace domain to time domain and then put t equals to 0, or you can apply initial value theorem. Okay, so if you know the initial value theorem, you wouldn't have to convert it from s domain to time domain. Okay, you will not have to convert it from s domain to time domain if you know this theorem. So but this theorem is applicable only when the signal is existing for t greater than 0 only, or you can say that ft should be some function f1t into ut. Are you getting my point? Ft should be 0 for t less than 0. That means this cannot happen. This cannot happen. This kind of waveform cannot be there. Only these kind of waveform can be there. These kind of waveform cannot be there. These kind of waveform cannot be there. Here it will not be applicable. Here not applicable. Here not applicable. Only here applicable. That ft should be 0 for t less than 0. Okay. And it shouldn't have any discontinuity. It shouldn't contain any impulse or discontinuity. Not of. It should be or any discontinuity. So tell me, will this theorem be applicable for this function ft equals to ut? For ut, will it be applicable? Will it be applicable for ut? No. Why so? Because at t equals to 0, we are having a discontinuity. Here we are having 0 volt, here we are having 5 volt. So what is the value at t equals to 0? Discontinuity is there, right? Discontinuity is there. So it cannot be applied for ut, right? Or it can be applied 1 by s. What do you mean by discontinuity? Discontinuity means this I am talking is differentiability actually. This is not discontinuity. Like there are two things, continuous function and differentiable function. So this is non-differentiable, but this is continuous actually. This function is continuous. Like this is not breaking down like this. This function is not breaking down. So here it will be applicable actually. Okay, for ut it will be applicable because this is not discontinuous. This is non-differentiable, because at t equals to 0 you can't differentiate it. If you differentiate it, you will get an infinite value. That means you will get an impulse. So this is non-differentiable, but the theorem is applicable for non-differentiable functions. Okay, so it is applicable for non-differentiable function, but it is not applicable for discontinuous function. So discontinuous would be the signum function. These kind of functions you will study in signal system. So these kind of function, but like it is not defined at t equals to 0. So for them you can't apply it at t equals to 0. Okay. So two conditions are there. The signal should exist only for t greater than 0. First thing is that. Okay. And the second is that it shouldn't have any impulse or discontinuity at t equals to 0. Like it wouldn't be applicable for delta t, right? Ft equals to delta t. For that it will not be applicable. Why so? Because at t equals to 0 we are having an impulse, right? Okay. So let ft equals to, let Laplace transform of ft is f of s. So what will be your initial value? This is in time domain. Okay, I should have written it like this, like limit time t tends to 0 plus f of t, or you can write f of 0 plus, you don't know the function in time domain, you only know the Laplace form. So what you will do, limit s tends to infinity s into f of s. That would be your final answer. Are you getting my point? Like you need to find the initial value of this function. What is the initial value of this function? In time domain only you can find. Put t equals to 0, that is 1, right? like there can be two methods. Initial value f of 0 plus would be e to the power minus 0 u of 0 plus, that would be 1. So this is one method. What about the second one? What is f of s? F of s for this function is 1 upon s plus 2, right? So in time domain f of 0 plus, or I should write limit t tends to 0 plus f of t, or f of 0 plus would be equals to limit s tends to infinity s into f of s. So limit s tends to infinity, what is s into f of s? What is s into f of s? That is s upon s plus 2. So s is very large, so s upon s plus 2 can be approximated to s only. So this and this will get cancelled and the value we will get 1. Look, s upon s plus 2. Now s is tending to infinity, that means s is very large. S is very larger than 2. So I can replace s plus 2 as s only. So s and s will get cancelled and you will get 1. Right? So here you can see, here also I am getting 1 and here also I am getting 1. Okay? Let's just see example number 2. You have to find the initial value for this function. So before applying the theorem, what I am doing, what is f of s? This function can be replaced with s plus 6 whole square, right? By s plus 6. So after cancelling, I am getting s plus 6. Now convert it into time domain. What is the Laplace transform of delta t? That is 1. Laplace transform of differentiation of delta t would be s into 1. That means s. Like whenever I am differentiating in time domain, what do I get? S into x, s of x. So if this is 1, so d by dt into delta t. So differentiation of this is 1. So I will only get s into 1, right? So in time domain, what is the differentiation of impulse function? That you don't need to think. What is the practical meaning of differentiation of impulse function? That also you don't need to think. Okay. So what is the final form? That is delta dash t plus 6 delta t. So what do you see here? Impulse at t equals to 0. Initial value theorem is not applicable. Initial value theorem is not applicable. Right? Did you understand? Now solve this one. Before going there, before applying the theorem, let's just break it down. It would be s plus 4, s plus 3, right? By s plus 2. I can break it down like this. S plus 2 plus 2 by s plus 2 into s plus 3. So it would be 1 plus 2 by s plus 2 into s plus 3. I am breaking it down. I can break it down like this. S plus 3 plus 2 into s plus 3 by s plus 2, right? Now s plus 3 can also be broken down into s plus 2 plus 1. Just simple mathematics I am applying, nothing else I am doing, right? So it would be equals to s plus 3 plus 2 into 1 plus 1 upon s plus 2. It would be s plus 5 plus 2 upon s plus 2. So it would be delta dash t plus 5 delta t plus 2 e to the power minus 2t ut, right? So this would be my f of t. So here what do I see? Impulse at t equals to 0. At t equals to 0. Right? Impulse at t equals to 0. Did I do the calculation right? Let me check. 2 1 plus 1 s plus 3, s plus 3 comes here, 2 s plus 3 goes there, s plus 2 plus 1, 1 upon 1 plus s plus 2, 2 upon 1 plus s plus 2, 2 comes here, 2 upon s plus 5, 2 upon s plus 2. Yeah, the calculation is correct. Okay, so impulse at t equals to 0, again initial value theorem is not applicable. Is not applicable. Okay, so what do you see here? Note, in Laplace transform function, when degree of numerator is greater than degree of denominator. Okay, this mark it. Degree of numerator is greater than degree of numerator. Degree of numerator is greater than degree of denominator. Time domain function will, for this, time domain function will always have an impulse. Always have an impulse. Here in this example, degree of numerator was higher. Degree of numerator was 2. Here it was 1. Here it was 2. Here it was 1. So degree of numerator was higher and degree of denominator is lower. So whenever there is this case, always there will be one impulse for sure. Take any example and solve it. Or you can think as well, like what you are doing, you are dividing this function by this. You are doing the division, right? 12s plus 6 or 36, whatever it is, right? Then s plus 2. So s will come there for sure, and one constant value will also come. Or if constant value doesn't come, only s will be there. So it will be the differentiation of a delta t, and that is also a discontinuity. So I should have written in the better manner that will always have an impulse or differentiation of impulse, or differentiation of impulse. Differentiation of impulse. That is a discontinuity at t equals to 0. That is a discontinuity at t equals to 0. So for applying the initial value theorem, degree of numerator, so I think I can add a page and write down that f of s is numerator upon denominator, then degree of numerator should always be less than degree of denominator. Okay, even if they are equal, the final value will not be applicable. For initial value theorem to be applicable, for initial value theorem to be applicable. Okay, so always remember this point. Many times teacher miss this point and they just teach this formula. Okay, only I have seen many of the students just knowing this formula, but they don't know this concept, that if the degree of denominator is higher, you can't apply initial value theorem. Okay, so always remember this. If the degree of numerator is higher, you can't apply initial value theorem. You have to break it down to f of t. Then you need to see that at t equals to 0, I am having a discontinuity, so I can't really tell what is the initial value theorem. So initial value theorem is not applicable. So when initial value theorem is applicable. So let's just assume f of s is given as s plus 6 upon s square plus 7s plus 12, whatever it is. You just need to find the initial value. Okay, so find limit t tends to 0 plus f of t, or initial
value, right? So what you will do? What will be your answer? So f of t equals to 0 plus would be limit s tends to infinity s into f of s, limit s tends to infinity s into f of s. So s square plus 6x upon s square plus 7s plus 7s square plus 12s. What you can do, you can take s square as common, or what you can think that s is tending to infinity, so s square will be very very large, so this upper function can be replaced with s square only, and this s square is very very large. Okay, this will be s cube actually, already there is square, so this will be s cube upon s square 12s. So this s cube will be very very large, so this will be replaced with s cube. So finally you are getting 1 upon s, and if you put s equals to infinity, it will be 0. Okay, are you getting my point? Like for the numerator part s square plus 6s, so s square will be very very larger than 6s, so it will be s square. And in the denominator part, what is happening, s cube, that will be very very larger than s square and s, so it will be replaced with s cube only. So we are left with limit s tends to infinity 1 by s, that would be equals to 0. Or you can do, you can take s square common, so it would be 1 plus 6 by s, or you can take s cube common from here, so it would be 1 plus 7 by s plus 12 by s square. Now if you put infinity, this will go to 0, this will go to 0, this will go to 0, so finally you will have 1 by s. Now if you put infinity, this complete function will go to 0. So this you can do. Also you can think like this, that this s square will be very large, so just replace it with s square. S cube will be very large, so just replace it with s cube, and then this will be. Or you can do this, because most of the students solve like this, by this method, but I usually solve like this, a very large, then just replace that. So your f of 0 plus is 0. Okay, so your initial value is 0. So without finding the time domain function, you can tell that initial value will be 0. The graph will start from t equals to 0. Okay, so this is initial value theorem. Now what about final value theorem? So first thing is, the signal should not be unbounded or periodic. What is unbounded? This is your ut, right? This is function ut. Is it bounded? At t equals to infinity, are you having a finite value? Like you are having a finite value, that you know that at t equals to infinity it will be 1 volt only, but it is never going, like it is not completing anywhere, right? So that means bounded function means at infinity you are having 0 voltage. This is what bounded function means. Like this is unbounded function, because it is getting increasing and increasing. You don't know the steady state value, right? Look, I shouldn't, let me rephrase my statement. Okay, wait. Yeah, so I'm really sorry for the mistake that I said that ut is an unbounded signal. It is a bounded signal. What is the definition of unbounded signal? Is that it shouldn't reach infinity value at any time. Okay, so I will just write it. What is unbounded signal? Unbounded signal. That f of t goes to infinity at any point of time. At any point of time. Point of time. What is the example? Example is f of t equals to e to the power 2t into ut. So how will the waveform look like? It will just keep on increasing, right? The waveform will be like something like this. So it just keeps on increasing. Like this, right? So it just keeps on increasing. So it is an unbounded signal. Okay, ut is not unbounded, because always it will give you 1 volt, and that's a finite value. Okay, so it is not unbounded signal. So this is what unbounded signal is called. Okay, this is your unbounded signal. Okay. Okay, so the signal should not be unbounded or periodic. Periodic signal, you know, right? Periodic,
the same period it follows, periodic. So these are the condition, okay, because in periodic signal the cycle goes on, so you can't really tell what is the final value, okay. And the pole of Fs should lie in the left half of S plane. Now what is pole? So let's just assume your Fs is this value, 1 upon S plus 2 into 1 upon S plus 3. So just put the denominator equals to 0, okay. Like all this concept you will be studying in control system and signal systems, but here it is necessary, that's why I am telling. So what is the pole of a system? Let's just assume this is your f of s, okay. What you will do, you will put the denominator equals to 0. If you put denominator equals to 0, what is the value of s you are getting? -2 and -3. This is S plane, one is sigma, one is j omega. So the real value is called sigma, this is real, and imaginary value will be called imaginary. Imaginary value will be shown at j omega axis. So you are getting -2 will be somewhere here, and -3 will be somewhere here. So the pole of Fs should lie in the left half of S plane. Okay, so here we can apply the final value theorem. Are you getting my point? Here you can apply the final value theorem. Why so? Because the poles are getting in the left half of S plane. Now let's just assume my function was something like this. My f of s was s square plus, not s square, my function was s plus 2 into s minus 2. So where will be my poles? I should write s minus 3. So where will be my poles? One pole will be at -2, one pole will be at 3. So 3 will be somewhere here, sorry, -2 will be somewhere here, and 3 will be somewhere. That's how we show the pole, by cross sign, okay. And 3 will be somewhere here. So one of the pole is lying in the right half of S plane. So this is what we call right hand plane, and this is left half. So actually this is shown at left hand pole, right hand pole. So this is lying in the right hand side of the S plane. So if this is there, that means you can't apply final value theorem, okay. So strictly it should lie, can't apply final value theorem, okay. So strictly it should lie in the right half of S plane and maximum one pole at origin, okay, maximum one pole at origin. So where if I write 1 upon s into s plus 2 into s plus 3, so what will be my pole? -2, 3 and one pole will be at 0. So maximum one pole at 0 is allowed. If there is two poles at 0, origin means 0. If there are two poles at 0, this will not be allowed, okay. If there are two poles at 0, this will not be allowed. Are you getting my point? Final value theorem will not be allowed if there are two poles at 0, okay. So what is final value theorem? So instead of this, I should write limit t tends to infinity. Actually in network analysis, what happens is that whatever the questions you will encounter, no, like, and in every question the final value and initial value theorem will be applicable, okay. In network analysis, whatever the question, whatever the problem you see, in every problem you will be able to apply initial value and final value theorem. So while teaching network analysis, teachers don't teach all these concepts. Why so? Because the theorem will always be applicable. So they just teach the statement, okay. So in conclusion, you just need to remember the statement. What is the statement? Limit t tends to 0 f of t is, for initial value what did we do? S tends to infinity, but for final value we will do s tends to 0, s into f of s. Same thing we will do, s into f of s, that we did here, s into f of s, just s tends to infinity. For initial value s tends to infinity, for final value s tends to 0, okay. You don't need to mug them up because in control system and signal system you will be studying this again, but just to see that your function should not be unbounded, it should not be unbounded, okay. All the poles should be lying in the left half of S plane, okay, left half of S plane, not in the right half of S plane. If there is a pole at origin, this should be only one pole at origin, not two or more than two, okay. Are you getting my point? I hope you are understanding. So let's just see some examples. This is the first example. What is the steady state value or final value? So what is f of infinity? That would be e to the power minus infinity upon u infinity. So that would be 0, right? Here you can see more example, and by Laplace transform, what will be f of s? It will be 1 upon s plus 2, right? What will be f of infinity? That would be limit s tends to 0 s into f of s, right? So it would be limit s tends to 0 s by s plus 2. So if you put 0, this will be 0 only. Just 1 upon s plus 2 in just multiply it with s and put s equals to 0. So if you put s equals to 0 here, you will get 0 only. Now apply the theorem in this. So before applying the theorem, just make the s plane. What will be your s plane? Sigma and j omega. Okay, this is sigma, this is j omega. Find the poles. Find the poles. Poles will be s square plus a square goes to 0. So what is the value of s? That is plus minus ja. That means one pole will be here, ja, the other pole will be, sorry, pole we make, this is j omega upward. So one pole will be here and the other pole will be here. Are you getting my point? This is j omega axis, j omega imaginary, this is imaginary axis. So one pole will be here and the other pole will be here. So the poles are lying on imaginary axis. Poles are not in left hand side of the plane, right? So final value theorem is not applicable. Theorem not applicable. Okay, this is the first thing you can see. Or what you can see, what is f of s? That is a upon s square plus a square. Tell me what will be f of t? You should know it. What will be f of t? Sin at ut, right? So this is what? A periodic signal, right? The waveform will be like this, periodic, keeps on going, periodic signal, keeps on going like this, right? This will be your f of t. So because of this periodic signal, the signal is periodic, that's why you can't apply final value theorem here. Okay. Okay, so shall we take another example where you can apply the final value theorem actually? So I guess I can take an example. What example shall I take? Let me think. So this is the example. Okay, so we can write f of s as s upon s plus 3 s plus 4. If you make the pole zero diagram, one pole will be at 0, this is sigma, this is j omega. One pole will be at 0, one will be at minus 3, one will be at minus 4. So final value theorem is applicable. Value theorem applicable, right? So f of infinity would be limit s tends to 0 s into f of s. So limit s tends to 0 s into f of s and s will get cancelled. So s square plus 6 upon s plus 3 into s plus 4. So 0, if you put s equals to 0 here, this will be 6, right? And if you put s equals to 0 here, this will be 4 into 3, that will be 12. So 6 by 12, that means it would be 1 by 2. So final value will be 1 by 2. Okay, so this is your final answer. So this is the initial value theorem and final value theorem. So that's it, I guess. Okay, so for gate aspirant, knowing this much is more than enough. Okay, for placement guys, there are few more concepts left. Okay, what are those concepts? Like the current thing that I told you, Then you need to know basics of control system as well, like what is Bode plot, what is transfer function. Like transfer function we have already studied. This is only a transfer function. This is what we call a transfer function. Output by input is transfer function only. So these things you also need to know. Then you will draw the Bode plot also. Then you will tell the pole zero as well. Gate aspirant will learn all this in control system. For network analysis, this is enough for them. All this will be studied in control system for gate aspirant. Like gate aspirant will study control system very deeply. They will study root locus and Nyquist criteria, RH criteria, all these things. But placement guys will not have to study all these things. So whatever from control system that is necessary for placement guys. So that I will tell in some other video, and then I will put more of network analysis. So for gate guys, here the RC circuit part gets end. Now we will solve question, then we will move on to RL circuits. So for placements as well, now we will solve the question and move on to RL circuit, but we will again come back to RC circuit in the last. Okay, when I give the concept of control systems, then after that we will be studying RC circuit again. Okay, because few more concepts are left that you will understand only after studying the basics of control system. So first we will study that basics of control system, that we will move on to again that RC circuit part. Okay, so I hope you are enjoying the lectures. This lecture was a bit tough, like this in the initial analysis was a bit tough, especially this one. So I hope you have understood the concept. Okay, I tried to teach the concept in as deep manner as I could. Okay, and then we saw this simple RC circuit. This was very easy. Then we saw this initial value and final value theorem. So I hope you are enjoying the lecture. I hope you have understood a lot of concept, a lot of new things here. Okay, this question is left, but I guess I don't need to teach this. I will leave up to you. Okay, in some doubt class or anything I can discuss this problem, but I'm leaving up to you. Try solving it. Not an easy problem, like not a straightforward problem. Like if I tell you the final answer, it will be very easy, but I want you to think about it. What will be your V naught value? What will be your VC value? Okay, I want you all to think about all these circuits, and then we can discuss this in doubt class. Okay, or in any class. But for as of now, I'm not going to discuss the problem. I am leaving up to you. You need to draw V naught waveform, IC2 waveform, IC1 waveform, and IR waveform. First, try thinking about the current. If you think about the current, you will be able to draw the VC, V naught, IC, IR, and IC2 waveforms. Okay. So let's meet in the next class. There we will be discussing a assignment. Okay. Thank you.